I recently uploaded a 12-hour video to YouTube that explains how computers work by building a conceptual processor from scratch. When I uploaded that video, I had no expectation that it would get traction, and so I told myself if the video got 10,000 views, or ever reach that amount of viewership, I would continue with a follow-up video. At the time of this recording, that video has over 480,000 views, and my goal of 10,000 was hit within 24 hours of uploading. I've been humbled by the responses, and checking my inbox every day and reading all the new comments or emails I get has been a joy. Since my goal was hit, I'm here to make true to that self-promise, and so let's do that by go ahead and continuing with another video. So, for context, I am not making any assumption that you watch the prior video, because I know that's a 12-hour commitment that many people just don't have time for. But if you did watch that video, the goal is for this video to be a direct continuation. And if you didn't watch that video, I'm going to bridge the gap by explaining a quick, high-level recap of where we left off in the last video, and that'll actually come a little bit into this video. So, we ended last video with a conceptual computer that could execute these very atomic and small instructions. Things that were seemingly trivial, like add or subtract, or moving a value from a register into memory or memory back into a register. But we also saw that when we tried to write any complicated program, not even a complicated program, something trivial like counting numbers in a sequence, it required a lot of these very small atomic instructions to actually get the program we wanted. And so there's two issues with this. One, it's very slow to write code in these machine level format. And the second issue is that it's really hard given a program to figure out what it's actually doing. And for recapping, I'm on this same set of notes that we were looking at way back when. These were the instructions we had for our really small hypothetical toy computer. And, if I gave you a program that had a bunch of these instructions just in a list, it wouldn't really be clear to you what's actually happening. And if you are a software engineer or know someone who's a software engineer, one of the primary responsibilities of their job is to write code. But it's not actually this type of code that they're writing. They're writing code that looks more like English, but there's a contradiction where we know that most computers only read these low-level instructions. These load A's, these adds, these subtracts, these stores, and these jumps, these conditional jumps. So how do we reconcile the fact that humans write code in these files that look like English, but something has to happen to transform those programs into these lower-level instructions that work on a specific computer architecture? So in this video, I'd like to answer that question, if I can ever find where my notes are, of what exactly is coding, what is programming. Many of us have probably heard the concept of a programming language, but what exactly is a programming language? And then also, I want to try, at the end of the video, touch on some more philosophical questions, like why do we have so many different programming languages? What is the need for this? And what do we mean when we say certain programming languages are faster than others, or this programming language is faster for this specific task versus this other programming language is conceptually better for a different set of tasks? I'd like to try to tackle all of that in this video, which is yet another ambitious topic. And I think the best way for us to actually do this is to invent our own programming language from scratch and figure out how we can formally specify what that language is, and then also translate code written in our higher level, closer to English language, to the machine instructions that a real CPU can actually understand. And another thing that surprised me in the past years as I've worked as a software engineer is how important of a topic this is, but how few people actually understand it. For me, this concept that we're going to look into is called a compiler. A compiler, without getting too far ahead of myself, is a program that takes code written in a high-level English-like language and translates it down to these really small, machine-friendly instructions that the computer can actually execute. Most people don't even know how to use a compiler. They just write code in some text editor, and that editor happens to have a green run button, and that when you click it actually deals with the process of compilation and executing that code. And I think on one hand it's pretty cool that we can abstract a lot of that away from the user. On the other hand, I'm shocked by how many people who are full-time engineers who spend a significant amount of their waking hours writing code don't actually understand how the computer understands what the code you are writing is meant to do and actually goes about executing that. As a student, I majored in computer science, and I was also very surprised to find out that there's a class for this. I think most every college offering a degree in computer science will probably have a class for this concept of compilers or programming languages. My school had two separate classes, one that looked at programming languages as a whole, and one that looked at this tool that we're going to focus on this video called a compiler. And neither of these were required. It's very surprising to me that you could walk away with a bachelor's of science in computer science without actually understanding how a programming language works, or like what really a programming language is. So I'm hoping to cater to both software engineers and generalists in this video and explain just exactly what a programming language is. So in my last video, I started by taking numbers that we already were very familiar with and complicating them. And I think it turns out if we do the same thing at the start of the video, intuitively you kind of know a lot of the core concepts of how this compiler that we're going to build works. Just baked into your head through years of schooling. And so we're actually going to unwind some of that to try formalize some of the intuition that's just so naively or concretely packed into the back of your head. And once again, I will make no assumptions of prior knowledge for this video. I will have to write code for that. I'm not going to assume that you know how to program, so I will do my due diligence to explain the code that I write. The only thing that you need to know going into this video is how simple addition, subtraction, multiplication, and division works, which I'm assuming if you're here or you made it through the last video, both of those are necessarily true. Cool. So let's go ahead and get back into the math. And take a sip of water. Let's start with something like 6 plus 8 plus 5. If I asked you how you would evaluate this expression, you'd give me a very straightforward answer. You'd say you take 6 plus 8, you see that's 14, and then you add 14 to 5 to get 19. And addition is interesting, where we usually read the mathematical expressions left to right, but addition, it doesn't really matter. A plus B plus C, you could shuffle that around and that's the same as C plus A plus B or any permutation of those numbers. So I could have actually done 8 plus 5 to equal 13 and then add 6 to get 19, and the result is the same. So that's true of addition, where we can read it left to right or right to left. But let's actually take a look at subtraction. If I say 16 minus 5 minus 3, if I read this left to right, I could say 16 minus 5 is 11, and then minus 3 is 8. But if I actually do this subtraction first, let's see what happens. I would take 5 minus 3 and get 2, and then 16 minus 2 is equal to 14. These are not the same answers. And we know that reading left to right is how we should approach things. So we know that the first answer is correct, but it's a very interesting question. A younger version of yourself probably wondered, well, what exactly is wrong with the second approach here? So if we know that we need to read this subtraction left to right, there's an interesting hypothetical question of, well, what if we actually wanted the 5 minus 3 to happen first? And the way we would answer that is we would use parentheses. So we loosely recall from school something called PEMDAS. There's many acronyms for this, so now I've been taught a different way, but this gives us an ordering of precedence of operations. The P stands for parentheses, the E stands for exponents, then multiplication, then division, then addition, and then subtraction. And we usually read this left to right. So it means if we have a mathematical expression, I know we're only looking at addition or subtraction, but it can include any number of things. You would evaluate whatever's in parentheses first. Before you do any addition or subtraction, which happens at the end, you do parentheses. And we also know that multiplication and division should happen before addition and subtraction. For example, if I had 6 plus 8 times 2, according to PEMDAS, this 8 times 2 should happen before the plus 6 is evaluated. So it is not the case that we are doing 6 plus 8 times 2. That's wrong. We are doing 6 plus 8 times 2. So using parentheses is really useful here when we actually want to show the ordering of operations. And if we don't have parentheses, we rely on this like implicit like ordering specified by PEMDAS. But I want to actually present another way of maybe looking at these mathematical equations. And it might be a little bit strange, so bear with me, but let's say we wanted to do 7 plus 8. Rather than writing this as a left to right equation where everything is on one line, we're actually going to look at making this into a tree. And you'll see why I'm going to call this a tree. The spoiler is that this structure, instead of reading left to right, is going to read top to bottom, and it's going to grow bushier and wider the more expressions we have, but you'll see that in just a few examples. So I will actually say we have a addition operation, and the two operands are 7 and 8. So we know that the plus sign is an operator, meaning it operates on some input, and the things it operates on are called operands, just in expression speak. So this is a slightly weirder way to look at it, but this would say we want to evaluate the addition of whatever is on the left and whatever is on the right. There's two children to this addition symbol, and we are going to evaluate the value of those children, and then once we have the children resolved as exact numbers, we can just add them together trivially. In our case right here, 7 and 8 are already both numbers, so this trivially just evaluates to 7 plus 8, which is equal to 15. Let's add a third term in here. Let's say I wanted to do, let's come back to this 16 minus 5 minus 3. 16 minus 5 minus 3. If I wanted to write this in this tree format, well, we know that this 5 minus 3 has to happen after the 16 minus 5. So we could phrase it like there's a subtraction up here, and then we know we're going to subtract whatever the result of 16 minus 5 is. We're going to subtract 3 from it. And then to actually figure out how we'd represent 16 minus 5, instead of making this an 11, that would be the result, we'd actually use another subtraction item in our tree, and that has the children 16 and 5. So we're actually seeing in this case that for a subtraction operator, or for any operator, there are always going to be two operands in our world, because we know that addition, multiplication, subtraction, division, they all operate on two numbers. It's a plus b, it's a minus b, it's a times b, or it's a divided by b. So you know that for each of these operators, there will be exactly two children of it. And then what's interesting is that the children themselves can also be expressions that need to be evaluated, meaning that they don't have to just be straight numbers, they could also be expressions. And so if we had this tree, this is what we're calling this, an expression tree, how would we actually figure out what the correct value is? Like, how do we actually evaluate this? So we know that we want to evaluate this, the top of the tree, and if we had two numbers as the children, it'd be a trivial subtraction operation. And for the right child, that is the case. 3 is just a number, so we could trivially subtract that out. But the left child is not a number, it's actually an expression itself. So in order to be able to perform this top level subtraction up here, we actually need to figure out what this second level subtraction evaluates to. So if I took this tree, then I'd actually, instead of wanting to be able to start up here, I need to work my way from the bottom up and evaluate this first. This child needs to be evaluated before the parent can be evaluated, which is very interesting. And I know it might seem like I'm overcomplicating this specific example. It's just a foreign way of representing things, so I want to make sure I'm as clear as possible. So, if I evaluate 16 minus 5, it becomes 11. So what I can actually do, I'll show how the tree progresses. So, oops, I want to copy it, and then I will paste it. Okay, so we know we need to evaluate the 16 minus 5. This is actually easy to operate, and it's straightforward because both of the operands, 16 and 5 are the operands to the operator of the subtraction sign, means we already know that that's just 16 minus 5. So this, everything I have in this circle right here, is equivalent to 11. So I can actually just replace what's in that circle with 11. So I went from this to this. I took a tree, some part of our tree, and actually simplified it and squashed it down. Now I can come back to this top level subtraction. This operator now has two operands, both of which are just numbers, so we can evaluate it directly to get 8. And so this is interesting. And so that is how we actually represent compound expressions. And now you might be wondering, I said we wanted to evaluate 16 minus 5 minus 3. And when we did it this way, when we structured our initial tree the way we did, we got the right answer. But there's an interesting reason where you might have said, why didn't we phrase the tree in a different way? So this was one way that we could have taken our initial tree. Let's look at the other way, because there's actually another way we could have structured this initial tree. And that is, we could have said, we have 16 minus something. So we could say we have a 16 minus something. And the other expression that we were trying to evaluate is 5 minus 3. Okay, so for some of you, this might already smell. You can probably already see the issue. Let me walk through and figure out how we'd evaluate this tree to get the final result to prove that we're not going to get 8, and therefore something is wrong in this initial tree setup. So, in order to evaluate this top-level subtraction, we need both of the operands to be numbers. 16 is a valid number, so that's fine, but the right-hand child is not. It is yet itself another expression, so we need to evaluate this expression to get a number before we can evaluate this top-level subtraction. So, I can evaluate that, and we know that this tree is trivially 5 minus 3, which is 2. And so then I could take this subtraction operator now has two children. The left child is a number and the right child is a number, so we can just evaluate it directly, and that would give us 14. But we can see that 8 is not equal to 14, so these trees did not get us the right answer. So when we're taking an expression and trying to get it into a tree, it's actually very important that the way the initial tree is structured is correct. But there's kind of this question of like, well, how do we know how to structure this tree correctly? And so to figure that out, let's actually use a little bit of intuition. We kind of see that when we have a complicated tree, like if I had something like, let me give a tree with more than 2 levels. Like, let's say I had something like this. Then let's actually look at this 3-level example and figure out how we'd actually evaluate it. And let's figure out how we'd evaluate it, and then let's figure out what the expression is, i.e. how we would phrase this in this very human way of structuring an equation on one line of text would be. So we've seen before that we'd like to start by executing this top level operator, but we can only evaluate an operator if both of its children are numbers themselves. In this case, the left-hand side is a valid number, but the right-hand side is actually this whole other sub-compound expression. So we need to evaluate that right-hand side before we can evaluate this top-level operator right here. If I look at the right-hand side, I see we have a plus sign up here, but both of its operators are not children. Are not integers, sorry, numbers. an integer is just a whole number. I don't want to get don't want to make sure I'm using terminology that's not readily defined to everyone. So I will try to catch myself throughout the video if I find myself using terminology that I have not defined. Otherwise, I will have some sort of correction sheet in the comments where I can call out things that I either catch when looking at this video in retrospect, or someone in the comments can catch. But we see that the left-hand side is an integer, but the right-hand side is not an integer. So we actually need to evaluate the right-hand side to make it an integer before we can evaluate this. And once we evaluate this, then we can evaluate this. So if I come down here, I see that the first thing we do is we finally reach this operator that is a 10 minus 2. So that's the thing we're going to evaluate. And we know that trivially resolves to 8. So if I rewrite this tree after one-step evaluation, we see that this becomes 8. And now we can see that this operator is the next and only operator that we can evaluate, because 7 and 8 are both integers, i.e. whole numbers, so we can evaluate the addition without needing to do some sort of sub-processing, is kind of the word I described it. So now we know that evaluates to 7 plus 8 is just 15. So I'll copy over this, and we have this. And finally, we only have one item left in our tree, which is just a simple addition. Both operands to this addition operator are integers, so we can just evaluate it directly. And we know that 16 plus 5 is 21. So I know that this tree evaluates 21, and let's figure out the mathematical expressions we executed in what order to get there. So I know I started with a 10 minus 2. So I started with a 10 minus 2. I'm going to wrap that in parentheses just for making it clear. Then I added 7 to that result. This result resulted in an 8, and we added a 7 to it. So let me undo that so we don't have too many circles. I added a 7. And I'll also wrap that in parentheses. And then we know that this entire thing right here is equal to this circle right here, which is a 15. So if I look at this final tree over here, you see that I just take whatever the 15 was, whatever expression, i.e. this is the expression that got us 15, and we add 6 to it. And so this is the expression that got us this tree right here. And so one interesting thing is you might be noticing for the past two instructions, I chose to put the 6 and 7 on the left of the expression that we had, but I could have also put the 6 plus 6 on the right. This is because for addition, we know that 6 plus 15 is equal to 15 plus 6. This is not the case for subtraction, where if I had 6 minus 15, that is not equal to 15 minus 6. So this means if we have some sort of operator, a plus b, in our English speak, this evaluates to a plus b, but if I had something a minus b, it looked like this. It'd be represented as this structurally. So I'm keeping the left side of the tree on the left side of the equation, and the right side of the tree on the right side of the equation. So when I take this expression right here, which got us 15 in this final tree over here, and we're adding 6, just to be very precise, the 6 is the left-hand child operator of this tree, and this whole compound expression that got us 15 is the right-hand child. So I'm putting 6 here. You are correct for addition, it does not matter, but for every other operator, or for some of the other operators, it does. For addition and multiplication, a plus b is equal to b plus a. They're kind of symmetric. And the same is true for multiplication. A times b is equal to b times a, but this is not the case for subtraction and division. So it's just going to be easier for us to generalize by being very consistent and actually respecting the order. So this is how we took a tree and figured out what expression came from. And I can also drop some of the parentheses now. I was adding those to be verbose, but this is equal to this right here. And we still have not answered the question of, if I had an expression that I was comfortable with like this, how would I have known to get the tree that I did? And so this is where things get a little more interesting. And I'm going to lean on an observation that we've done 2 or 3 examples now. And that has been that we would like to start by taking the top of the tree and working our way down it. But the only way we can actually do that is that we've been performing the actual additions and atomic additions and subtractions working upwards the tree. So we've been taking things that are at the bottom of the tree and simplifying those into numbers, and then that cascades upwards and lets us then evaluate things further up in the tree. So the tree itself is represented top down, but to actually evaluate it and get a number as the result, we're walking the tree bottom up. And so this is interesting because it means things that are lower in the tree will get executed first, versus things that are higher up in the tree are going to get executed later. And so I'm going to avoid answering the question that I've just posed one more time by looking at an example that involves multiplication and division, because we know that those should be executed before addition and subtraction. And so kind of intuitively, if I had some expression like let's say I had an expression 7 plus 8 times 2, then because of PEMDAS, what we saw earlier, we know that multiplication comes before addition, so we actually need to execute this multiplication first. So we know that if we wanted to represent that 8 times 2, we could do that using our new way of representing things, this thing that I'm calling the tree, and it becomes an 8 times a 2. And so then we know that we need to evaluate this 8 times 2 first, and once we do that, we can add 7 to the result. And we know that things that are lower in the tree will be executed first, so I want the plus 7 to happen afterwards. So what I'm actually going to do is make this the child of a addition with a 7. And so now if I gave you this tree, the only way you could execute it is by finding the expressions where both of the operands are already integers, and those are the things that are necessarily going to be lower in the tree, and evaluating those first. So even if you wanted to try evaluate this addition first, you couldn't, because not both of the operands are numbers. This is already a valid number, but this right here is actually another expression that we need to evaluate to get a number. So now we know that to evaluate this, we'd have to evaluate this sub-problem first. And so this tree would then become, if after we evaluate the 8 times 2, we get 16. And then we have a simple operation where 7 plus 16 equals 23. And so we've now taken this tree and found the correct value. And this is the correct answer. And this is interesting because this shows that when you represent a mathematical expression in this tree-like format, there's no ambiguity. We only have one way we can really operate this tree, and that'll get us the correct result. Versus if we're looking at this expression here in this kind of notation that we use for English, we kind of rely on whoever is evaluating it to make sure that they know their precedence orders correctly, or else they won't be able to actually evaluate things correctly. They'll get the wrong response. So then there's still this question that we're trying to get at of, given a expression in our normal format, i.e. this, how do we get the correct parse tree? How do we figure out how to order it and structure this tree so that one way to evaluate this tree does give you the correct results? I think we've made it pretty clear how you can evaluate a tree once you have it in that format to get a number that is the correct result. So let's actually take some time to figure out how we go from expression to reverse. So there's approach number 1, which is we just kind of use our own intuition. Let's take an example to see what that means. So if I had 7 minus 2 times 3 plus 9, then one approach is I could actually, and I knew PEMDAS existed, I could use parentheses to make the ordering of things very unambiguous and make that very clear. So in this example here, we know that parentheses, there's no exponents, there is multiplication. So 2 times 3 would need to happen first. And then after that, we have an addition and subtraction. And we know those are of equal precedence. So those just run left to right. So we'd want to evaluate the 7 minus the 6 first. And then after that, take the result and add 9 to it. Because we know if we have a series of operators that are of the same precedence, here addition and subtraction are pretty much the same precedence, we execute those left to right. So I could take this very well parenthesized equation, and then making the tree becomes a little easier from that. We'd start at the innermost parentheses, which is the 2 times 3. Represent that in tree format. And then we could work outwards. So we know that the next outermost parentheses from there is this 7 minus. So we could rub that in. And then the outermost parentheses involves this plus 9. So this is one way of getting the tree. And this would actually totally work. If we evaluated this tree, we'd see that the 2 times 3 becomes a 6. 7 minus 6 becomes a 1. And a 1 plus 9 is equal to 10. And so that's if we evaluate the tree. And if we evaluated it using our intuition of PEMDAS, we know that multiplication takes the tightest precedence. So we're left with 3 times 2 first. We evaluate that to 6. Then we're left with 7 minus 6 plus 9. We read this left to right. So 7 minus 6 is 1. And then we add 9 to that to get 10. And we see that we get the same 2 results here. So clearly, this parse tree was derived correctly. Now, I'm going to present a different way of an option 2 pretty much of how we could take these expressions and get the right parse tree. So the reason I'm being overly verbose here is because we're eventually going to teach a computer, and not too long from now, how to take an expression and generate this parse tree, this tree-like structure we've been discussing, and then also how to then take that tree and evaluate it to get the correct result. But as we saw in the last video, and if you've not watched the last video, and if you program computers, you know that computers require a very clear specification of how to do problems, how to solve problems, how to evaluate things. And using any hand waviness is going to create some confusion. So I'm actually going to take us down a slightly different route that will, again, seem a little bit obscure at first. And once we actually code this up in a real programming language, it'll make sense why I'm forcing this down this route. So for the next few minutes, let's jump back to just addition and subtraction and think about when we had expressions that were just addition and subtraction, how we could formally specify a set of rules for this. So I'm going to write out a set of rules where we know an expression is just a series of additions and subtractions. So something like 7 plus 8 minus 3 plus 2, something like that is just a series of additions and subtractions. We're going to come back for multiplication, division next, and then parentheses afterwards. But I'll spill out an answer here, and we'll try to figure out like what this means. So I'm going to say an expression is either an expression followed by a plus followed by a number, or an expression is a expression minus a number. So then let's jump back to an original expression we looked at earlier. 1 minus, or we'll make this, keep it to whole numbers, positive numbers, sorry. 7 minus 2 minus 3. And let's then look at the set of rules we have right here and figure out how we could kind of take these rules and expand it out to get the expression. And I know I'm being hand wavy here, that's intentional. So if things are a little bit ambiguous, just bear with me. And once we have more building blocks together, it'll all make a little bit more sense. And hopefully a lot of sense by the end of the video. But I know that a number, oh, there's one other rule. A number, we're going to be very specific, is, for now, we'll just leave it to single digit evaluation. It's either a 0, a 1, a 2, up to a 9. Just some number, some digit. So what I want to do is take this set of rules, and I can keep expanding them until I have a full representation of what I'm looking for. So I'm trying to take these rules and figure out if this expression right here is valid. So one thing I see is that both of these two rules up here, they end with a plus or minus a number. So we can kind of see that our overall string or text over here ends with a -3. So I'm kind of going to bias towards this second expression first. I also know there's no addition in my expression, so I kind of have to go with the subtraction route. So I'm going to take this expression rule, and I'm going to say it's going to be expression minus a number. And in our case, the number is just going to be 3. So I can rewrite this as expression minus 3. And now we have this other part. So this part's kind of been accounted for. Can we now expand an expression term again to match this 7 minus 2? And the answer is kind of, yeah, we can take this exact rule that we had before and replace expression using this rule. We know expression can equal expression minus number. So I'll replace this expression with expression minus number. And we still have this -3. And here, we know that minus number, well, this looks like a -2. So I'll replace the number with 2. So this expands to expression -2 -3. And so it looks like we've hit a dead end almost, because we know we want to get this 7 in here, but an expression, we've defined it to be either an expression plus a number or an expression minus a number. But there's actually a trivial change we can make here. I wouldn't call it trivial, actually. It's very important. In that that's an expression can also just be a number itself. You know, if we're evaluating mathematical expressions, we normally think of something akin to operators, like 7 plus 6 would get us 13. But also just a number itself is also technically an expression. 13 just evaluates to 13. There's no math being done on it. So a single number can also classify as an expression. And if we have that, then that lets us get this final parse tree where we replace this final expression with a 7 minus 2 minus 3. And the parentheses are just something I added in. And so that really means we get the 7 minus 2 minus 3. So, according to this set of rules we've defined above, we can derive this string. This string is valid according to the set of rules. And this is pretty cool because this is a formal specification of rules that we can use to figure out if a certain expression is valid or not. This right here is called a context-free grammar. And we have just created a context-free grammar that lets you determine if simple mathematical expressions containing additions and subtractions are valid or not. And so this lets us not only answer is something this lets us answer two things. This will let us say, given a string, which is representing a mathematical equation using numbers and symbols, is this actually something we consider to be valid? And then we just saw how you can do that using expansion. The second thing is that this actually helps us get parse trees, because what I can then say with we took the approach of manually replacing terms, but replacing the terms actually gave us some amount of precedence that we saw when we added parentheses in here. So what I'm going to do is, let's reconstruct the same example, or just a different one. Let's say we're looking at the string, and string just means some text here. 5 minus 2 minus 1. Then let's figure out how we can, let's actually take a more interesting one. Let's do 5 minus 2 plus 1. Let's figure out how we can do two things at once. Let's figure out if this is a valid string according to this quote-unquote context-free grammar. And then we'll actually, in the process, figure out how we can get a parse tree out of this, i.e. the tree that we saw in the previous examples that we got pretty comfortable working with. So I see that our expressions, we start with expressions, and an expression is either a number or it's an expression plus or minus by another number. But what's interesting is that all three of these routes end with a number. So if I'm trying to match, I'm pretty much trying to find a series of rule expansions that'll let me match this target string right here. And if I can't do that, then this string is not valid according to this context-free grammar. And if I can, then this string is valid according to this context-free grammar. And I'm making the claim, I'm spoiling the fact that this actually is a correct grammar. So whatever matches here is a valid mathematical expression we can try operate. We can come back and look at an example of one that fails to parse. You already know that 5 minus 2 plus 1 is something that is a valid math expression. If I said something like 5 plus 2, then that's not really that's not a valid mathematical expression, and we'll see in a bit that that actually doesn't parse according to this tree. But I see that there is this plus 1 to end the expression, so I'm actually going to pick this rule, this second rule, to try expand from. So I'm going to say expression goes to expression minus number, and we know number goes to 1 in our case. We just evaluate that. This expression right here, we then have a 5 minus 2 we want to evaluate. Oops, sorry, I used the wrong. This should be expression plus number. This one right here, we know we have now left a 5 minus 2 we want to deal with. And to do that, we know that only one of our rows here and one of our rules in our grammar actually supports this subtraction. So we're going to use that one. So we're going to replace this expression rule with this second row right here. And so what this grammar is, because I haven't said it explicitly, is just a series of rules. You start with an expression term, and you keep using replacements by picking some item from this list and saying that, hey, you can either choose an expression to map to this, or an expression can map to this, or an expression can be a number. And based on what you replace with, you can keep doing replacement over and over while you have valid replacements that you can make according to this set of rules. So in this case, I'm going to take this expression term and replace it to the second rule we have here, which says expression minus number. And I'm just going to replace this with the number 1. In our case right here, we're dealing with 5 minus 2. So this number just gets replaced to 2. And then this expression right here, we want to be able to replace it with a 5, and then we've done our full replacement. And so we have the third rule, which says an expression can be remapped to a number. So let's do that. Expression becomes number. And we know number is just a digit 0 through 9, and that becomes 5. And so then we successfully now have been able to parse this entire string according to this context-free grammar. And so we know the first question's been answered, that this string is valid according to this context-free grammar. So then the second question becomes, I claim that we can make a parse tree out of this, and it turns out if we kind of just rotate what we have, we're pretty darn close. So I can rotate exactly what we have up here, and I expanded my terms horizontally. If I had done it top down, we'd actually get an item that looks pretty close to what we were dealing with before. So I could say expression becomes this plus sign plus a number. The number in our first case evaluated to 1. Then I had this expand to another expression. And this expression evaluated to, we chose to do expression minus number. So we have expression, a literal minus sign, and then a number. And in this case, the second row, we took that number to be 2. And then the last thing we did is we replaced the expression with a number, and we took the number to be 5. And now it looks like we have this tree-like syntax again. And if this tree shows all the replacements we took using the rules that were made available to us in this grammar to get the final result. If we actually abstracted that away and took away all the rule replacements and just looked at the syntax, we would see that this right here is just at the very top of the tree is an addition expression. We can see that the right-hand child is a number 1. And we can see that the left-hand child is another expression. This expression's operator is a minus. So we take the minus sign. We see the right-hand argument is a 2. And the left-hand argument is an expression which became a number, which became a 5. And so if we remove all the grammar stuff, all the rules of the grammar away from this, we actually took our expression here and got the correct parse tree. How do we know this is correct? To evaluate this parse tree, we realize that 5 minus 2 has to happen first. And we also see 5 minus 2 is deeper in the tree. And the observation we had earlier in this video is that things that were deeper in the tree would get evaluated first. So we know this 5 minus 2 becomes a 3. And we're left with a 3 plus 1. And that just becomes 4. And that's exactly the right thing we know we'd expect here, because if we looked at this, then what you learned in elementary school math, probably, or before elementary school, is 5 minus 2 is 3 plus 1 is 4, which is the exact result we got here. So this weird little thing called a context-free grammar is how I knew, or is how we can both, 1, take an input and verify that it is valid, and 2, given a valid input, helps us formally explain how we could get this parse tree. So let's look at an example of something that would fail, and we'll just give a simple example. If we had the string 5 minus minus, we know this is not a real mathematical string. It doesn't mean anything. But if I tried to parse this using the grammar rules, I would say, hey, I'm going to use the second rule. I start with an expression. I'm going to replace it with an expression minus a number. And pretty quickly you see we get stuck because there's no way. We have to replace this with a number. And we actually want to replace it with a minus sign, but there's just no set of rules that lets us get 2 minus signs in a row. So you could try to play around with that. I don't want to use too much time to prove that on the camera, but if you play around this, you'll actually see there's no way you could keep expanding this expression rules that we have to get this string right here. And so this is why people like context-free grammars. When we actually go to build this in code, we'll see that the way we structure things here might seem a little weird, but it actually makes the job of implementing it in code a lot easier. So then there's one last thing I want to answer just to beat this down before we consider how do we expand this to include support for multiplication and division. And that is, let me actually just do some erasing. The thing I'm going to take a stab at is, how did I know to say expression plus number and expression minus number instead of number plus expression? I drew a little more than I thought. Actually, I'm going to keep this because we can reuse the same example. So let's actually suppose, my question was, why did I say expression equals expression plus number and expression equals expression minus number? Why didn't I do expression equals number plus expression, or expression equals number expression equals number minus expression? Let's actually flip it around and try parse the same string we looked at earlier and see what happens. So I will take this and flip these around. Okay, and the string we were working with was 5 minus 2 plus 1. 5 minus 2 plus 1. Okay, let's try go ahead and parse this. So we know we start with an expression rule, and we're going to say, I'm actually going to give a slightly different string. this one would parse fine, but I'll give you a slightly different string that would prove that this doesn't work. 5 minus 2 minus 1. And let's say we start with an expression rule. We'd say expression becomes number minus expression. And so we would have this number become a 5. And then this expression, we could use the same rule again, where you'd say an expression becomes a number minus an expression. I'm just going to use expr for short. And this time we had 2. This expression term, we just want to replace with a 1, so we can use this last right here where an expression can just, or the third rule, where an expression can map to a number. And that would get us the number 1. And so this looks fine. According to this context-free grammar, we're able to parse this expression, which means 5 minus 2 minus 1 is a valid mathematical expression. We know that's true, so there's no issue here. But then let's go ahead and actually convert it to the parse tree that we were looking at earlier. The same way we kind of took this and got this final tree. Let's do the same thing here. So I'm actually going to delete everything we have. And let's see what we got. So we started off with a expression. I'm just going to use expr for short. We said that's equal to num minus another expression. We said this number was just 5. And then this expression right here we replaced with number minus an expression. We replaced this expression with a number, which was 1. And we replaced this number with the literal 2. And so that's our full parse tree. If I simplify this to the tree structure we looked at earlier, we see this as equal to a minus up here, a 5, and then a minus right here, a 2, and a 1. So we get a tree out of this. Now let's actually evaluate the tree. So we evaluate the 2 minus 1 first because it's lower in the tree, and we need to evaluate that to evaluate the top level subtraction. So we end up with a minus 5, 2 minus 1 is 1, and so that leaves us with 5 minus 1, which is 4. But if we look at this expression up here, we actually know that the correct answer should be 5 minus 2, which is 3, minus 1, which is 2. So this should equal 2, but according to this parse tree, we ended up with a 4. And the issue is if you look at the parse tree, we're evaluating 2 minus 1, taking that result and subtracting it from 5. So if we use parentheses to get this back to regular equation form that we're familiar with, we see that we've actually parsed this as such, when in reality, we should have parsed this like this. And so, it turns out, I'll let you prove this for yourself off camera, that the ordering of number and expression here gives us something called, in this example, it gives us right associativity. When we flip it and things work totally fine, it gives us left associativity. And if you play with a few examples in both setups, you'll see that the reason this works is that it forces when we have operators of the same precedence, i.e. addition and subtraction are the only two operators we're looking at now, but they have the same precedence. When you read them right to left, we'd want to be able to parse it in such a way that the tree makes sure that they're actually evaluated right to left. In the tree, in the rule setup we have right here, they're actually being evaluated right to left. Sorry, I just misspoke. We want to evaluate them left to right. In the example we just looked at, our grammar forces them to be evaluated right to left, which is incorrect. That's not how we actually process things in the math that we're familiar with. So that's why we actually roll with this grammar right here, where we put the expression part first. And if that's still not clear to you, the way you can start reasoning about this is actually the fact that we know that we start with an expression rule and we keep expanding it. By expanding on the left-hand side first and forcing the right-hand side to happen afterward, the number part afterward, it actually means that we're taking the right-hand component and forcing it on the right-hand side, and then we're letting this part be the part that gets expanded deeper. And we know intuitively that things that are deeper in the tree will get evaluated first. So I would encourage you to play around. It's very easy to contrive some examples and play around this to verify why this works. But it turns out that this is actually a very powerful tool, the context-free grammar. And what we're going to do now is add in support for multiplication and division. And what's interesting is that we know for addition and subtraction, this setup right here works, and that it'll force things to be evaluated left to right. But that works because addition and subtraction kind of have the same precedence. For multiplication and division, we know that any multiplication and any division should happen before all addition and all subtraction. So we're going to find a way to actually bake that into our grammar to make sure that when we include multiplication and division into our valid syntax, that there is no ambiguity in the way that we expand our grammar rules out to get a final result, and that the only way you can actually get a valid result is if the result is also the correct syntax tree whose mathematical evaluation would get you the right expression answer. I'm going to go ahead and spill out the answer, and then we'll see how that comes to be. So let me rewrite the grammar down here. Okay, so I actually cut the video because I realized I didn't formally define what a context-free grammar was, and it turns out they're actually so important that it makes sense for me to go ahead and pause and give a formal definition, a formal explanation before rushing to add multiplication and division in. So let's go ahead and do that. So a context-free grammar, we kind of saw this in the previous example. It's effectively a set of rules for describing the structure of a language. It defines what counts as a valid sentence or expression in that language, and it turns out that every single programming language out there is defined by some context-free grammar. You can look up, if you use Java, for example, you can look up the context-free grammar for Java after I explain this, and you'll be able to read it. Those programming languages are very complicated, and they have many language features, so the grammars will be many pages and way more complicated than what we're going to derive here. But the reason I'm actually trying to get us to think in terms of a context-free grammar is because once we get our ability to understand mathematical expressions in a context-free grammar, we're going to be able to go build a programming language based off of this. And what we're going to do over the rest of the video is keep adding more and more features to our context-free grammar, and then figuring out how we can implement those until we have a full-fledged working programming language. And it turns out if you can understand how we deal with mathematical expressions in a context-free grammar, you've understood the most difficult part, and everything else afterwards is not trivial, but significantly easier to understand. It's just an extension on top of what we already know. So if this is the most difficult part of the video, do not feel overwhelmed. The more we look at this and the more features we end up adding to our fictitious programming language, the more you'll be able to digest it and kind of understand why things are the way they are. So with that, let me go ahead and give a formal definition for a context-free grammar. The specification of a context-free grammar has 4 components. The first component is called a variable. And you'll also, if you do research online, you'll see these being called non-terminals. And you can think of these as placeholders. So in the example we looked at above, expression and number are examples of non-terminals. They never actually appear in the final output string. You don't see the word expression or number here. They're simply variables that we use for replacement to derive a final string. What does appear in the final output string, however, is called terminals. These are the actual words and symbols that end up in the final output. In the example we looked at above, all that would be is every digit 0 through 9, and then the plus symbol and the minus symbol. And you notice that all the input strings we looked at were just combinations of those. The third thing that's part of a grammar is called rules. So rules are the substitution recipes that we actually use to take a non-terminal and replace it with something else. So a rule is usually in the form of a non-terminal followed by a right arrow, followed by any combination of terminals or non-terminals directly. And we can kind of see that here. Everything on the left-hand side is a non-terminal, and it's followed, each of these rules are followed by some number of terminals and non-terminals. It could be one terminal, one non-terminal, a few terminals with one non-terminal, vice versa, any number of the two. And the very last thing that's important for context-free grammar, which I totally glanced over and kind of only stated by assumption, was that there has to be a start symbol. So you have to be able to start with a non-terminal, and from there, using the rules that are available to you, you should be able to expand into only terminals, and all the possible outcomes of what you could expand to represent all the possible strings that are valid according to that language. Conversely, if there is a way to take the starting symbol and expand it to some string of interest, in this case 5 minus 2 minus 1, of purely terminals, then that string is said to be valid to the language specified by this context-free grammar. So, what I'm going to do now is we looked at the context-free grammar that supported addition and subtraction. Let's go ahead and add in multiplication and division. And I'm going to spill out the answer, and then we'll actually go see why it works. But the one thing that I do think you should note, and that you should be able to follow along on your own, is that we're going to want multiplication and division to appear further down in the syntax trees and our parse trees. So they're going to be further away from the start symbols. So we're going to be able to take our start symbol and expand to addition and subtraction first, because those should happen up earlier, because we know how parsing works from the past examples, is that has the implication that the addition and subtraction components will end up high up in the tree. And then if we have the multiplication and division be rules that happen later on in our parsing, then those will implicitly and explicitly end up lower down in the tree, which means those have higher precedence because those will get executed first, and we know that we need to walk from bottom up to evaluate the actual syntax tree to get the final result. So what I'm going to do is spill out the answer, and then we'll actually take a look at why it works. So I'm also not going to use, I used full words here, expression and number. Because my handwriting's terrible and there's a lot to write, I'm actually going to avoid doing that. I'm just going to use letters, because it doesn't really matter what a non-terminal is. We know it gets replaced by a terminal. Just the non-terminal helps us kind of understand the semblance and the meaning of what the non-terminal is supposed to do. So this is the context-free grammar. Let me also help try give some meaning to these. So I'm using E as shorthand for expression, T is shorthand for term, and F is shorthand for factor. And E, T, and F are all non-terminals. The only terminals are the plus sign, the minus sign, the multiplication sign, and the division sign, and then integers, i.e. digits, whole numbers. So what I'm going to do is let's take a string. Oh, the other thing is that the starting symbol, this is what I need to specify, for this grammar is E. So we see that we've defined this context-free grammar because we have variables, we have terminals, we have all of our rules listed out, and we now specified a start symbol. So this is a valid context-free grammar, and I'm making the bold claim that this is the correct context-free grammar that represents arithmetic expressions using just the operators addition, subtraction, multiplication, and division. We're also going to claim that this is called an unambiguous grammar. So this means for every string that's valid according to this context-free grammar, i.e. every valid mathematical expression, there's only one way you can derive it using replacements in the context-free grammar. This is desirable. There are some context-free grammars that are called ambiguous, meaning that there could be two different ways to replace non-terminals and non-terminals to get the same parse string. It's actually undesirable because that means you end up with two different syntax trees, and we just saw in a previous example how two different syntax trees that look to contain the same operations actually get you a different result when operating. So this one is called unambiguous because it means every expression will have exactly one unique syntax tree that gets you that expression, assuming the expression is valid according to the language specified by this grammar. And I previously said that context-free grammars can be used to specify programming languages, and that's how we will use them in this video. For now, our context-free grammar will be used to specify mathematical expressions that we'd like to evaluate. So I'll stop rambling. Let's go ahead and evaluate 3 plus 4 times 2, a simple expression that involves both multiplication and addition. And so the other thing I'm going to do, which I kind of used but didn't explicitly say earlier in the video, is we're going to take an approach to parsing called leftmost derivation. And what that means, we'll see it how it plays out in practice, is that we are always going to be taking the leftmost non-terminal in whatever our current string is and replacing that to try get the expression that we want. In our case, this is the target expression we're interested in. And I'm using string here, just string meaning text as I said earlier. So we start with E. We're going to use this rule of leftmost derivation. We only have one non-terminal in our working string, which is just E. So I'm going to look at it. My options, I can either replace any of the first three here. I make the observation that if I went down E to T directly, then my only options from T are going to include division and multiplication, but I clearly have this addition sign in my input string, so I need to take the rule. I'm intuitively going to know that I should look at the rule that includes the addition sign, which is this very first one. So I'm going to use the first rule and replace E with E plus T. Now our working string has a non-terminal, followed by a terminal, followed by another non-terminal. And here's where I mean that I'm going to use leftmost derivation. Because to try to figure out if this string is valid, which we know it is, because it's real math, we could either start by replacing the E or the T. In our case here, because we're using leftmost derivation, we say we're going to start with the E because it's more left than the T is. It appears first in our string. So this E, I can see intuitively that I have in my input, I have 3 plus something. In my input, I now have E plus something. So ideally, I'd like to be able to replace this E with a 3. The way I'm going to be able to do that is by leveraging E to T, T to F, and then F to the number 3. So let's go ahead and do that. I'm going to replace E to T, so that we're left with T plus T. Then I'm going to replace T to F, which gives us F plus T, and then F to the actual integer of 3. And so now we have 3 plus T. And now we can see we've successfully matched the first two characters in our string. That's neat. Now what I'm going to go ahead and do, using leftmost derivation, we only have a one non-terminal in here, and that's a t. So I'm hoping that I can remap this t to become a 4 times 2. If I look at the options for what I can match t to, there's only one thing that looks like it would be right, and that's that very first one where you replace it with a t by f. So let's go ahead and apply that here. 3 plus t by f. And so I kind of see I have the shell of our expression where I have an addition followed by a multiplication. I'd like to be able to convert this t to a 4 and the f to a 2, and that would get us the correct input string. Let's see how we can map this t. We know t can go to an f, and an f can just remap to an integer. So I'll go ahead and do that. 3 plus f times f. And once again, the reason I chose to replace this t instead of replacing this f directly with the 2 is because we're using a principle called leftmost derivation. We don't have to use that. I'm just trying to be very consistent in how I derive these parse trees. So I'm working with the leftmost non-terminal, which is t in this case. Now the leftmost non-terminal is the same position, it's now an f, and so I can replace that with a 4 using this very last rule. And so that gives 3 plus 4 times f. And now we see that we have the first 4 characters of our input string matched, and the only thing we need to do left to match this entire string and know that's valid is figure out if we can replace this f with a 2, and that is clearly true because of the very last rule. And so we replace, and we get this. And so we can see that by taking our start symbol and leveraging the rules we have here, we are able to end up with a string of purely terminals that is 100% identical to the target string we were trying to parse. Therefore, according to the language specified by this context-free grammar on the left, 3 plus 4 times 2 is a totally valid string. Let's do one more trivial one. Let's just see, I said earlier, the number 6 is a valid mathematical expression because it's just a number. So 4 plus 2 evaluates to 6, but 6 is also just a valid expression on its own. Let's figure out, taking the starting non-terminal, if we can remap it to get to 6. And it turns out the route is pretty straightforward, and we already did it as part of the problem before. But I take the e and replace it with a t, according to this rule right here. Then I take the t and replace it to an f, according to this rule right here. And I take the f and replace it with an integer, the integer being 6, according to that final rule down there. And so I can see that this is also a valid string according to this language. Let's look at one that's not a valid string just to make sure here. And that could be 6 plus plus. So I start with e. I know I want to replace with e plus t because there's an operation. E is the leftmost non-terminal, so I'm going to work with that one first, and I'm hoping to get that to a 6. I do that by mapping it to a term, and then to a factor, and then to the integer literal 6. And so then I've matched the 6 and the plus already. And so the question is there a way I can remap t using a series of these rules to just the literal plus sign? And the answer is no. The only way you could try to do that is by using this replacement rule right here, but then there needs to be a way for e and t to both remap to empty strings, which there's no such way. You can try to play around with this on your own, but you'll quickly see that it's not possible to actually get this derivation. Therefore, the string 6 plus plus is not valid according to the language specified by this context-free grammar. You already knew that, but that was just a formal way of looking at it. Let me go ahead and clean up the screen here. And the last thing we're going to do is, the next thing we're going to do is figure out, using this context-free grammar and this leftmost derivation, can we generate the parse tree and actually verify that if we evaluated the parse tree, we'd get the correct answer? Because right now what we've done here, it looks like we have verified that 3 plus 4 times 2 is a valid string according to this language. We actually have to go look at the tree and make sure that the 4 times 2 appears lower in the tree to make sure that that gets evaluated first, because we know according to PEMDAS, multiplication should occur before addition. So that's the last thing we need to do to verify that this is actually a valid context, that this context-free grammar correctly encodes the string we have here. So we said we start with an E, and instead of doing these replacements inline, I'm going to show them being hierarchical. So we replaced E with E plus T. I know it's a little confusing. The T's and the pluses might look similar. And then the next thing we did was replace this leftmost E with a T. And then we replaced that leftmost T with an F. And then we replaced that leftmost F with a 3. Then we came over to that T. And you see, because of this leftmost derivation principle we applied earlier, we evaluate the full left-hand side before we move to any of the right-hand side. The plus sign requires no additional work because that's a terminal. But then we came to this T. We replaced the T with a T by F. So it became T, the literal terminal multiplication sign, followed by an F. We then replaced this T with an F, and then the F with the literal integer 4. And the very last thing we had to do was right here, right here, where we replaced that final factor with a 2. And so now you can see a few interesting things. We saw in our final input string we ended up with all terminals. We can also see in this tree that every item in the tree that has nothing below it, i.e. no children underneath it, is a terminal. This is a terminal, this is a terminal, this is a terminal, this is a terminal, and this is a terminal. This is synonymous to what we see earlier, but it's also just a slight observation where everything that has no children in the tree, i.e. there's nothing below a certain item in the tree, must be a terminal. So that's how we kind of, the same exact replacement we did on the left-hand side of this vertical bar is the same exact thing we did on the right-hand side. It just visualized a little bit differently. And so what I'll end up doing is actually we can collapse out all of the non-terminals and just leave this with terminals. So this ETF over here is just a 3. This E over here is actually just a plus sign. This T over here is, oops, I'm on eraser mode. This T over here is just a multiplication sign. This TF4 is just a 4. And this F2 is just a 2. And so by removing all the non-terminals out, we're left with just the terminals. And now we see this parse tree that we're very familiar with. And now if we go and evaluate it, you can already see without fully solving it out that the multiplication is correctly lower in the it's lower in the tree, meaning it has higher precedence than the addition above. And so this actually looks correct. And if we go through and evaluate this, we can see that if we evaluate the 4 by 2 first, we get 8. And then we're left with this, which is a simple addition of 3 and 8, which just evaluates to 11, and that is correct. 4 times 2 should be evaluated first to give 8 plus 3, which is 11. If we did this incorrectly, our parse tree would execute things left to right. So we do 4 plus 3, which is 7, times 2, which is 14. That's not what we get, and that's a good thing because 14 would be the wrong answer here. So this is really cool because we now have a context-free grammar, and that correctly encodes all of our mathematical expressions that we care about. And now you're able to see, given an input string, you know, based on what we just looked at, how to figure out if that string is valid according to the language, and then also how to get this parse tree such that all the operator precedence is encoded in the tree. And so the thing that's different about this tree versus the one we looked at when we were just handling addition and subtraction is that you see that we kind of have this precedence where we have E's mapping to T's mapping to F's. And we kind of put all the addition and subtraction up here with the E's, and the multiplication and division with the T's, and the F's are just the numbers. And so we generally see in our parse tree that the E's appear above the T's, which appear above the F's. And this works because we are putting things with, we want things with higher precedence to appear lower in our parse trees, and we are doing that by putting them lower in the context-free grammar. And I know that feels a little weird to like wrap your head around, so take some time and dwell on it. And I encourage you to, because it's a kind of an aha moment, and maybe it won't be a clear click moment, but it'll be a gradual realization that we are kind of baking precedence into the rules of the context-free grammar, which is pretty powerful. So the last thing that we do not have support for is consider the expression three times 8 plus 2. So the parentheses, according to PEMDAS, it's the first letter in PEMDAS, means that this 8 plus 2 should be evaluated first to get us 10, and then we should have 3. And so intuitively, the parse tree we know that we're looking for here is going to be a multiplication of 3 and then the result of an addition of 8 and 2. This is the correct parse tree. Because we don't have support for parentheses, there's no parentheses that appear as terminals in this. We actually would have to, we can't really parse this string. The closest we could parse is this right here, and if you walked through, you'd end up with the parse tree that looks like this. And this wouldn't quite work because this would evaluate to 24 plus 2, which is 26, when in reality we know what we're looking for is 10 times 3, which is 30. So two different outputs. So we know we can actually work through this part together. Let me just erase this. I don't know why it's being so slow. And I will erase all of this and all of this. We know that PEMDAS, whatever your intuition or whatever your schooling system taught you, shows that we saw that multiplication and division happened before addition and subtraction, but before multiplication and division, this parenthesis should be evaluated. So we want a rule, we have ET and F, we want a rule that happens below the T's, below the E's, because parentheses should be evaluated first. So what we can actually do is added one more rule here. There's a few different ways you could get this. The one I like, just because I think it's the simple, is we can literally add one more rule, which says an F can be a open parentheses followed by a whole new expression followed by a closed parentheses. And now this is interesting because this means that we can, in parentheses, go back to having addition again, addition and subtraction, which are traditionally lower precedence things, but because they're baked in this F so far down the parse tree, they actually have the highest precedence. So let's actually, I'm making the bold claim that this one simple addition, or seemingly simple addition, should let us handle all parentheses being the tightest precedence, or most urgent precedence. Let's see this is the case by running through an example. So let me go ahead and erase this. And let's try generate a parse for this expression right here. So 3 minus, well, we can do 2 plus 8 times 7. So intuitively, what we've seen so far is that multiplications should be executed before additions. But in this case right here, this 2 plus 8, whatever happens inside the parentheses, should be evaluated first because we need to multiply it with the 7. So it turns out, because there's an addition in here, we are going to evaluate a low precedence operator before we evaluate a high precedence operator. So in this rare case, not a rare case, in this case, because of the parentheses wrapping a whole nother expression, just because that expression has addition doesn't mean it's low precedence. It's actually a high precedence. So this addition will appear pretty low in the syntax tree, but this one will still be pretty high up. So I'm actually also going to parse this in syntax tree form rather than showing the line-by-line replacement, just so we can get the final tree easier. So we start off with our E. And this tree will be a little bit wider. Hopefully I don't run out of room. We know that we see a subtraction, so we're going to remap it to E minus T. And we know that very first E, we want to become a 3, because we have a minus sign already right here. And the only thing that appears left of the minus sign in our input string is a 3. So I'm going to replace the E to a T to an F. And that F becomes the literal 3. Nice. Now, the T part's where things get a little more interesting, because we have this open parentheses we want to match. So we have a T, and we know one way we can get the open parentheses is only by hitting this rule right here. So I'm actually just going to map I would naively want to map a T to an F directly, but we actually know there's a whole multiplication that happens after the close parentheses. So if we took this T, went straight to F, and then straight to open parentheses E, close parentheses, there's no way anything could ever appear right of that close parentheses in the parse tree. So that's a shortcoming. So that's why we would not want to do that route. And you actually hit a dead end if you do that route. Instead, we would replace it with T by F, because then we can make this a T. This would be the multiplication sign. This would be the F. And then we know that we could replace this T with whatever. We could eventually make this the 2 plus 8. And then we'd have the multiplication sign, and we know we can replace this F with a 7. Let's not get ahead of ourselves. I'm just giving a sneak preview there. But this T now is the leftmost non-terminal we haven't parsed. We're still using this rule of parsing the leftmost non-terminal first. And the T becomes an F. And the F, instead of mapping it to an integer, we actually need to try to see if we can derive this open parentheses, because that's the next terminal we need to match. So we map it to open parentheses followed by E followed by close parentheses. And so we can now see that we've matched the 3, and we fetched the minus sign. We already had that earlier. We've now also matched this open parentheses, which comes next. Now we need to make this E map to a 2 plus 8. And E takes us all the way back up to the very first rule, which was also our start symbol. So now we have unlocked addition again, because traditionally, before we had this new rule, once you walked down the grammar, you couldn't walk your way back up. But now with parentheses, you can walk your way back up. So this E, we're going to replace it with an E plus T. And we just need that to become a 2 plus 8. So I'm going to remap both the E to a T, and then both the T's to an F, and then both the F's to a 2 and an 8. So that looks like T to F, and that becomes a 2. And now we can see we've matched the 2. 2 right here. And then we've also now matched the plus, because that was already there. We just needed to get the 2 before we could say that. And then this T becomes an F and becomes the literal 8. And now we've matched 8. And we already have this close parentheses 2, so now we've matched that. So the last thing, and we already matched this multiplication sign. So the last thing is we just need this 7, this F over here to become a 7. And we know the second to last rule lets us map F to an integer. So we can do that. And now we've mapped our entire, meant to be highlighting. Now we've mapped our entire input string according to a parse tree. So this parse tree is a little bit deeper. But let's go ahead and clear out all the non-terminals, but I'm also going to take the liberty of clearing out the parentheses, because we only want the mathematical operations now. So this whole left subtree becomes just a 3. The topmost node is a minus sign. The right-hand side argument is a multiplication sign where the right-hand child is 7, and the left-hand child is the result of an addition of 2 plus 8. And so, let's go ahead and evaluate this tree. We know we have to walk this bottom up. So, I copy 2 plus 8 is 10. Then 10 times 7 is 70. And we know that's negative 67. Not to make a 6-7 reference. Does that look correct? Let's see. We know 8 plus 2 is 10 times 7 is 70. 3 minus 70 is negative 67. So that actually looks totally right. And so in previous examples, the thing to remark here is that we said things with higher precedence should appear lower in the tree. It appears that we have violated that assumption here because we have an addition that appears below a multiplication, but it turns out the parentheses are a special operator that has higher precedence than multiplication, and the addition happens to happen inside of those parentheses, which is why we see the addition happening below the multiplication in this tree, because it actually has higher precedence in this example and therefore needs to be evaluated first. This is pretty cool. So we actually now have a context-free grammar that represents all mathematical expressions that we're interested in. And we also have a way, intuitively we now have a way of, given an input string, being able to derive the parse tree that proves that that input string is valid according to this language. And we also know from earlier in the video how we can actually execute these things and evaluate the final tree to get a final result. So what we're going to do now is take this context-free grammar we have here, and what we're going to do is in code go ahead and write something that can take a mathematical expression, use this grammar to chop it up into these terminals and non-terminals, then we're going to create this tree. We're going to write a program in code that can generate this tree automatically for us. And then the next thing we're going to do is write separate code that can take the tree and walk over it, traverse the tree to get a valid final result by doing incremental operations on the tree. This is really neat. And this also requires us to look at a programming language, and I'm holding true to the assumption that we have no prior context with programming languages. So what I'm going to do now is swap over to my computer screen, and what we can do is I'll give an overview of the language that we're going to use. And the language I've picked is called Kotlin. I'm picking it for a reason that will become obvious later in the video, but it could have been used, we could have used any programming language we wanted to. But the very first thing we're going to want to do is take our input string. So we're going to write a program that takes an input string that should be just some mathematical expression, and then chop it up into the actual granular parts that we care about. In this case, without getting too far ahead of myself, we can look at this trivial example. The tokens we'd want to break this up into, I'm using token as the most atomic component of the input structure. The tokens would be a 3, followed by a minus sign, followed by an open parentheses, followed by a 2, followed by a plus sign, followed by an 8, followed by a closed parentheses, followed by a multiplication sign, followed by a 7. So that's the very first thing we're going to do. Once we do that, we chop up our input into these tokens. Then we can figure out how can we actually use the rules of the grammar and see if this ordering of input tokens is valid according to this context-free grammar. So let's go ahead. I don't want to ramble too far ahead. Let me switch to my computer and we'll go from there. Okay, so it actually turns out before we jump to the computer, there's a way to simplify this grammar that escaped my mind, and I meant to get to this earlier and then forgot, so I'm cutting back in here with a little retroactive recording. But it turns out, if we look at our definition of how we define the context-free grammar, when we talked about these rules, we weren't very thorough about what the syntax of the rules themselves were, like what could appear on the left-hand side and what could appear on the right-hand side. We kind of just invented it on the fly. And for example, some ambiguity can be seen right here, where I just say integer, but like, what really is that? And we kind of take that just to mean a number, but that's not necessarily the formal way of specifying things. And so it turns out when we're specifying these rules, there's actually one more symbol that we can use that has a special meaning. And if we allow ourselves to use that special symbol, we can rewrite this grammar in a much simpler way that I think does a better job of showing the precedence of operators. So what that term is an asterisk, means 0 or more repetitions of something. So in our grammar above, I was just saying that f could go to an integer. This is not the formal way of specifying this. If we wanted to be as correct as possible, what we'd actually say is f could map to either a 0 or a 1 or a 2 or a 3. Oh, this is also, I should have specified this. This means or. This vertical bar. So you could, if we want to be very correct, we could say an integer is equal to any one of these digits. An integer requires at least one digit. Then we could also say it could be followed by any number of more digits. So if I had something like 7, then this rule would pass because 7 matches this first part right here, and then any repetition, any 0 or more other digits. In our case, we have no other digits that we want to parse, so it would just be like empty. And if we wanted to parse a multi-digit string, we could say something like 355, then the 3 would map right here, and then the first 5 would map here, and since this star means 0 or more, we could say the second 5 also maps here. So if we permit ourselves to use this rule, then it becomes much easier to specify things correctly. So now what I actually want to do is go ahead and say, I'll spill out the answer here for the sake of time. The grammar we've derived up here works, but it's somewhat convoluted. If we allow ourselves to use this repeated expression, then things become much easier. So we could actually rewrite the grammar we have as E goes to a T followed by a plus or a minus followed by a term, and that can happen any number of times. We'll look at why this is equivalent in a second. Then we'll see T maps to F followed by any number of multiplication or division of a factor any number of times. And then a factor in F is either going to be a number, which we'll specify as an integer, so I don't have to rewrite this madness up here, but you know what that truly means. Or it is an open parentheses followed by another expression followed by a closed parentheses. And so there's a little bit of confusion going on, so I'm gonna actually expand on this to be a little more precise, because right here, this open parentheses means a literal terminal that is an open parentheses sign, versus here, these open parentheses are just used to group something that can appear several more times. So to make the distinction very clear, I'm going to make all of our terminals quoted, and all of our non-terminals will not be quoted. And so that should make things a little more apparent. Now, let's go ahead and take the same example that we were looking at earlier, which was this 3 minus, let me just copy it over, honestly. Just bring it down. Come right here, and let's try parse this through. And so we also have the same rule that the start symbol is still an E. And we're going to go straight into tree form just so we can see the precedence. It'll make things easier rather than needing to repeat this problem twice, because we're going to see that we get the same exact result. But this is, I prefer this grammar because it's fewer rules and it's actually easier to reason about. And we'll all see there's a third benefit when we actually come to program this in code. This structure we have right here has optimal structure that makes writing this in code very easy comparatively to this other method we had above. And we're actually going to add one other term to this expression because I'll get a little ahead of myself here. What we previously saw in all of our constructions was that at the end, when we looked at a parse tree, each node ended up having two children. Each operator had two operands, and those were the two children. We'll see here that the parse tree we get is actually a little bit different, and a particular node can have more than two children, and we'll need to do one more step to fold that back to our assumption that our working model where each node is an operator and the two operands are the children that we should use to evaluate the either addition, subtraction, multiplication, or division. We'll work through this and it'll make sense in a second what we're doing. But let's go ahead. We start with an E. And I'm gonna go straight into tree format again. And so I can see that like their structure is like any number of t plus t minus t plus t. So all this first rule does is let us group the high-level addition and subtractions. And we can kind of see that there's one right here and one right here. What happens in the parentheses matters, but it's going to come back later because we know that because it's in the parentheses, it's going to be eventually handled by this rule right here. So I can kind of see that I'm going to replace the E with an E minus, or sorry, I'm going to replace the E with a T minus a t plus another t. So this can be a t, this can be a t, and this can be a t, and we have a minus and a plus in between. So that'll be the first replacement I make. So I'm going to say that this e has a t followed by a minus sign followed by a t followed by a plus sign followed by another t. And let me just bring that up so it's a little cleaner. So we can see that like this E has not two children. Even if we factor out the plus and minus, which we get rid of, there's three children to it, which is a little weird. So we're going to come back to that after we finish deriving the parse tree. So on the left-hand side of the minus, I know it's just a 3. So I'm going to start by using this leftmost derivation and replacing that with an f, and replacing the f with an integer, which is just 3. So that's done. Now, the middle t, we know is going to have to, intuitively we know we're going to have to replace it to that. So this t, if I look, I kind of see a multiplication. I see an f followed by an f, and there's only one multiplication, so I don't, this asterisk right here says 0 or more. In our case, it's just going to be 1. So I'm going to replace the t with an f followed by a multiplication sign followed by another f. In this first f, we see this is an f, and we're going to have to make this 7 an f as well. So the first f is where we're going to try use these parentheses, because it's parentheses, and inside the parentheses is a whole other expression, which is 2 by 8. So this first f is going to expand to a open parentheses followed by an e followed by a closed parentheses. And that expression, that e, we know is just going to be a t plus a t, t plus a t, and it's easy for us to replace both of those t's with integers representing the operands, which is a 2 and an 8. Cool. On the right-hand side of this multiplication sign is just a 7, so we can just make the f directly a 7. And if I wanted to be fully correct here, I guess I'll do it. These t's wouldn't go straight to 8s, the 2's and the 8s. They'd go to f's, and then they could go to their respective integers. And then on the right-hand side, we just have this t, and we know that just becomes a 4. So we can replace it to an f to a 4. And so this is our new parse tree. But if I tried to drop some of the syntax, there's a little interesting thing here where this top-level expression term right here, we can't really just drop the syntax and get to the point where we have two children, because there's both a subtraction and an addition happening on this sign right here. So how do we deal with this? How do we take this parse tree and get back to what we're so familiar with, where each operand was a node in the tree with just two children that were the operators to that node? And so to answer that, I'm going to jump away from this example with yet another example. Let's say we just had a parse tree, which was all additions and subtractions. So let's say we had the phrase 1 plus 2 minus 5 plus 4. Then our parse tree would kind of look like this. It'd be a 1 followed by a plus, by a 2, followed by a minus, followed by a 5, followed by a plus, followed by 4. And I think I'm picking this separate example because we don't have to worry about what comes below. So we know that we want to eventually get this to a tree, and we can kind of figure out what that final tree looks like. But what we're actually going to look at is that this E item right here kind of has a list of children. It has a 1 under it, a plus sign under it, a 2 under it, a minus sign under it, a 5 under it, a plus sign, and then a 4. So there's 2, 4, 6, 7 children under this node. And so what we're going to do is we're going to do something called folding left. And that's actually going to let us convert this into a binary tree. A binary tree is what we've been familiar with. Binary means 2. And what that means in tree context, just when we talk about this in computer science, a binary tree is a tree where each item has at most 2 children. And the trees we've been looking at, a node either has 2 children, i.e. like this, or if it's a number itself, there's no children. So what we're going to do is you take, to fold left, this is called folding left, take the first sub-expression, so a 1 plus 2, build that into a binary node. We're familiar with this. And then you keep looking at the next expression and including that, just building upwards on top of it. So for our next part of that expression is a minus 5. So I then take this, what we have so far, becomes the left argument to a new node. That new node is going to be a subtraction, and the right child is 5. So we folded what we had as the left child of a new tree. This is our new bigger tree we have now. And then to include the 4, I'm going to fold left once again. So let me move this over here. This entire thing that we've been working with now becomes the left tree, the left operand. We folded it down left to a plus sign where the other child is a 4. And so this is how we've taken this process of folding left. It's pretty straightforward, but it actually bakes in the order of operations correctly. And so I don't want you to just take this folding left algorithm and be like, okay, it seems easy to apply, so we're good. You should actually take the time to think about why this works. And we can see that what we're pretty much encoding is that we know that if we have a bunch of operators of the same precedence, and that's true because if we look at the grammar, for this E to have a bunch of children, it's all terms being added and subtracted from each other. So all of the children of that E have the same precedence. Similarly, if we had a T node with a bunch of children, it'd all be a bunch of Fs multiplied and divided by other Fs. And so those all have the same precedence, because we know multiplication and division have the same precedence. So when things have the same precedence, you're intended to just evaluate them left to right. And so we kind of want to evaluate 1 plus 2 first, then take that result, subtract 5 from it, and then take that result and add 4 to it. And so we know that if we look at this final tree right here, to evaluate it, we need to evaluate the things that happen at the bottom part of the tree first and then work our way upwards. And so you see the very first thing we do to evaluate this tree is evaluate this 1 plus 2. And that's correct because if we're reading left to right, that's the first sub-expression that should be evaluated. And then after that, we subtract 5. And that would be the next expression that gets evaluated, because you would end up with the tree that looks like this. And so you need to evaluate this. And that would get you a tree that looks like 8 plus 4, this. And then the very last thing you're evaluating is a plus 4, which is represented by this tree, which gives you the 12. So you can kind of see this concept of folding left is pretty straightforward, but also pretty powerful, because it means, by virtue of the way we've constructed this grammar, all the children of any particular node have the same precedence, so the order of evaluation should just be from left to right, and that's a very powerful construct of this grammar. And you can also kind of see that we've baked in the precedence much easier. It's much easier to visualize how we've baked in operator precedence here. We have all of the additions and subtractions happening at the T level, and then all of the multiplication and divisions happening at the F level, and all of those are, because T's map to F's, that means in our parse tree, excluding parentheses because it's kind of an exceptional case, notice how all of these F's, oops, I just erased, all of these F's are happening below all of these T's, which means they're going to be evaluated first when we go to evaluate the tree to get our final mathematical result. So that's cool. So pretty much what that means here is if we wanted to fold our tree left, what we'd actually do, and this gets messy to draw out, especially with my terrible handwriting. Let me move this just out of the way so we don't lose it. It seems like a good enough spot. And what we're going to do, I'm just going to use numbering right now. We pretty much have an E followed by T1, followed by a minus, followed by T2, followed by a plus, followed by a T3. And so our folding left as we start, we build a node for this first sub-expression, which is minus T1 and T2. And then we fold this to be the left child of another expression, which is the plus, whose right child is T3. So that's how we pretty much fold this E out. And what we'd end up with is a plus of, on the right side, we know T3 is just a 4. On the left side, we know we have a minus. And then T1 just becomes a 3. And then this T2 is kind of the messier thing, where this whole subtree right here represents T2. And so for that, though, all the operators, if we look at the tree, every term left here already has only 2 children, so we don't need to fold anything out. But if there was, for example, one of the F's or one of the E's had more than 2 children, we need to apply the same folding process out to that subtree. But we look at each node in the tree, see that there's already only at most 2 children, so we don't actually need to do anything special here. So then we can literally just rewrite this tree as is, with only looking at the terminals, dropping out all of the non-terminals of the grammar. So we have a multiplication whose right argument is a 7. The left argument is an addition of 2 and 8. And so this is the final parse tree, and this gives us the correct precedence. We'd evaluate this 8 plus 2 first, and we see that's correct because the 8 plus 2 is in parentheses, and we know P is the first letter in PEMDAS, so that should be executed first. Then we'd evaluate the multiplication, and that makes sense because in PEMDAS, the next most prioritized operator is the multiplication. And then we'd finish out with the additions and subtractions, but we correctly note that we evaluate those left to right. So the 3 minus this subterm right here should happen before the addition with 4. And we can kind of see that. We have a minus 3 happening, and then we take that result and finally add 4 to it. So this grammar right here gives us interesting parse trees, where our parse trees can now have multiple children under any node. But we now know how to just fold left to get back to the original 2-child, aka binary tree that we were so comfortable evaluating. So this grammar is also what we call unambiguous. For every valid string, according to this grammar, there's only one valid parse tree. And I actually prefer this grammar because A, there's fewer rules. We have 3 rules versus this one up here had, 8 rules? And then I think it's easier to reason about the precedence. I don't think folding left is that complicated. And then when we actually go to code it, we're going to find that it has this property that makes specifying this in code very easy. And I can't prove that yet. We're just going to have to wait until we get to the part where the video where we start coding, which is not too long from now. So now what I'm going to do is cut the video back to the computer, and we'll build out what we've described. Okay, so I switched over to my computer, and I mentioned that we're going to be using the Kotlin Programming Language. I've been using this language a lot recently, and I think there's many things I enjoy about it, so I just made the choice to roll with it. It is, as I mentioned, a programming language, so it must have a context-free grammar available online. So I went ahead and made a search for one. And I guess I should, before I click on this link and take a peek at the grammar, I should specify that I chose Kotlin because I've been using it a lot recently and I like many of the language features it has. I chose it for this video specifically also because I think it is very readable for someone who hasn't maybe not programmed that much before. And I will also do my best to be explaining things as we go. But the truth is, you could have picked many different languages to use to write for this video, and they all are capable of building the language we're going to look at. And I know that might feel meta, like we're using a programming language to write a program that can translate a different programming language. Like, how is that possible? We're going to come revisit that at the end of the video. It may seem very weird, and to me it was very weird, but it's a pretty cool setup, and when we visualize it, I'll draw things out. It's pretty neat what we're capable of accomplishing here. But I get ahead of myself. Let's look at the context-free grammar for this programming language. And I mentioned that this is a very complicated programming language, so I can see there's a lot of rules. I see here's a rule that has here's a terminal, the literal word while, like the same open parentheses and close parentheses we just saw, and another non-terminal. It's cool, you can also click between these, and you can just see there's a lot of this programming language. The programming language we're about to build is not going to be nearly as complicated, but one thing I did think would be cool to look at was, I was trying to find multiplication here. And so I see this star, this asterisk in programming is how we denote multiplication. And I see it's chained from this rule called multiplicative operator. And if I come up here, it's used by this multiplication expression. And if I come and see where this tool is used, it's actually used by this tool called additive expression. And I think that's funny because if I look at additive operators, the additive operators are plus and minus. So you can see in our language we had our add minus being higher higher in the parsing chain than multiplication and division. And if we look at the context-free grammar for a real programming language, we see the same exact thing happening. And it's because we are baking in the way we bake in operator precedence into our language is pretty much how almost every other language out there does it as well. So the choices I'm making in this video are not purely random, though you'll see many of them are. That's cool to point out. But I made this video with the assumption, as I stated at the earliest part of this video, that you need not have any programming language experience. I'm going to go ahead and take the next few minutes to walk through the Kotlin programming language. If you already have significant programming experience, don't worry about it. I would actually advise skipping through the next few minutes. And the reason is because I'm also going to be explaining all the code I write. But if you don't have any programming language experience, then you might as well watch away. And the other thing that I'd like to mention is that for the last video I made, many people asked if I could share notes. Because I was drawing on my iPad, I didn't really have an easy way to export that file. For this video, since we're actually going to be writing a lot of code, I've made a repository on this website called GitHub. If you've never heard of it, you can pretty much think of it as a clone of Google Drive, but for programming code. And it has really cool ability to snapshot code at certain points. So after different milestones, you can go see what the state of the code was looking like. I'm going to link this in the description. It's going to be available, and I will keep it up forever. And you can see the programming language as we build it along. So, without further ado, let me swap over to my terminal, and what we're going to do is take a quick look at the Kotlin programming language. So, I'm using something called a REPL. It stands for read, evaluate, print, loop. And normal Kotlin programs are specified in files, and we're going to do that. We're going to build our compiler set of files. For the sake of me showing off specific features of the language and giving an overview, this REPL is really fast because what would happen if I wanted to show you one feature, I need to write the code for it, run the compiler, which would translate Kotlin code into the machine code that my computer understands, which is slow, and then run it. This is slow, versus an interpreter will, every time I feed in some amount of code, it'll just interpret that one line, evaluate it as if the Kotlin was running natively on my machine, and spit it back out to me. We're also going to talk a little bit more about this, because an interpreter versus the compiler that we're building is a slightly different thing, but there actually see there's a lot of overlap between the two. But there's interesting nuance and discussion about like why we have both, why certain programming languages are said to be compiled versus interpreted, but we'll get there further in the video. The other thing is that you're going to see I'm not using a pretty editor. I'm using something called the terminal. So before computers had this graphical interface where you had windows and folders and you can click around to see everything, all computers were operating in a terminal. I actually really like developing in the terminal. I think for the sake of this video, it's also going to be useful to like make sure I'm not getting distracted with like, if I use some sort of fancy text editor that had a button that did a lot and you didn't know what that button was doing, then you would be confused. Versus everything I do in the terminal will be pretty explainable because it requires me to type here. So let's take a look at the Kotlin Programming Language. The way we can print output is simply by using print, and then inside of these parentheses, we say what we want to print. So if I want to print the number 5, I would just call print 5, and it would spit out a 5. I'd actually like to use println, which prints a new line afterwards, which I think is easier to look at. Then, if I wanted to print a mathematical expression, I could do 7 plus 9, and we'd get printed out 16. Or, I could do something more complicated. I could do 1 times 2 times 3 times 5, 1 times 2 times 4 times 5, plus 53 minus 6, and it'll spit it out. And I should have used println, but I used print. And so print is the means by which we can speak output to our code. But that's something we'll use a lot of. And the core, a lot of what we'll also use is variables to track things. So you can define a variable as something named in Kotlin. So let me just define a variable called counter. And I'll do that. I'll say my counter is going to be a number variable. So I'm going to say var, which stands for variable, counter. I'm going to say counter has a type of integer. That's what that colon is. And I'm going to start off counter is 0. And so this defines, I get some complaint here. And I think that's because I forgot to end my line with a semicolon. Let's see. Expected type integer. Oops. Sorry, I should just say int. Cool. Another part of these videos is you get to watch me struggle live because, as you saw in the last video, if you watched the last video, I just kind of went for it. This will be the same thing here, except it's a lot easier to have my mistakes called out because I have to try and write code and the computer's going to yell at me if it can't understand it. Our compiler will do the same. If someone puts in a bad program, we'll have to make it yell at the person to say, hey, this is not a real program. So we define this variable called count0. If I print the value of count, then it's 0. Now I can assign count. I can say count equals 2 or 3, and if I println count now, it'll say 3. I could also have multiple variables. So I could do like a second variable called counter second. This could be an integer as well, and it could start off as 5. And I could print count plus counter second. Oops, that was a typo. And this should print 3 plus 5, which would give us 8. So that's cool. And so that's the concept of variables. Now there's something called a loop. And for this, it's going to look weird if I write it in this REPL, so I actually probably shouldn't have used the REPL at all. Let me hop out of the REPL, and let's make a file. So I'm going to go ahead and make a new file. KTS, usually our Kotlin files end in .kt. KTS is going to say it's a script file, and it'll let us run the code faster. So we just saw that you could have a variable. Variables have a name, and they also have a type. So in our case, we have an integer variable. But there's also other data types in Kotlin. So you could actually have a Boolean, which is a true or a false, or a string, or you could actually have a collection. So you could have a list of numbers. So let's actually try to work with that. So first, some like number collection, and we're actually going to say it has the type where it is a list, a mutable list, because we're going to want to add to it, of integers. And for now, we're just going to make it a mutable list of nothing. Again, don't worry about the syntax. I know some of this is foreign. So we're saying we have this variable called number collection, and it can hold a mutable list of numbers, and we've defined it to actually have nothing to start with. The reason we're saying mutable versus just list is mutable lets us add items to the list. If we just defined it as a list, once we define the values that were in that list, we can never change it again. And this might seem like a weird thing, like why is it actually desirable? Mutability is actually a big part of the Kotlin programming language. And we'll actually see down the line that mutability lets the compiler do certain things and lets it optimize certain things. So if you know you have a list of numbers or some list of items that is not going to change, and you specify that to the compiler in your code, the compilers that we work with that are out there are very complicated and can optimize many things and actually improve the performance of your program. Just for something as trivial as marking it as not mutable. So let's actually do something. Let's go ahead and add some numbers to our collection. So let's add 1. Then we can go ahead and add a 2 and a 3. And let's go ahead and print out number collection. And so I'm going to run this from the command line. It's going to be a little bit slower than the interpreter we just saw. And we can see we now have this list of the numbers 1, 2, and 3. So let's say I wanted to write the first 100 numbers into this list. How can I do this? We have the concept of a loop. So doing this like add 1, 2, 3 is kind of slow. We have the concept of a loop. So we could say, we could define a new variable, and we can call this next number to insert. And it's going to be an integer, and it can start at 0. And we can say, while this next number to insert is less than or equal to 100, what we could do is add that current number to the collection. So number collection, we can add the next number to insert, and then we can increase the next number to insert by 1. And so let me go ahead and delete what we had here. So now, we define this collection, we print it, it should be empty at first. Then we define this new variable called next number to insert, which starts at 0. And instead of having to 100 times print out this copy and paste, add 0, add 1, add 2, add 3, rather than needing to do that 100 times, we use the concept of a loop, which is iterative. And this lets us say, while this counter variable is less than or equal to 100, add whatever it is to the list, and then increase it by 1. This will start by adding number 1 to our list, then make the number 2, and then it'll add the number 2 to our list and make the number 3, and then add the number 3 to our list, so on and so on. So let's actually go ahead and run this. Oops. I have a typo on line 7, and that's because variable names are case sensitive, and so I forgot to capitalize my 2 there. Cool, so now we see when we first create the list and print it out, it is empty. That's why we get an empty list. Then we see that we have the numbers 0 through 100 here. Sweet, that looks pretty cool. The next thing we're going to take a look at is the concept of functions. So let's say I wanted to print out the first 10 numbers, and then later in my program I wanted to do that same thing again, but maybe the first 15 numbers. It'd be kind of weird to like build this out and then have to copy it and paste it somewhere later in the code. when like the logic is effectively repeated, we just go to, instead of 100, maybe 15. So we can define the concept of a function. And a function is a repeatable, callable amount of work. And a function can take some input and also return some value. So what we're going to define is a function, and let's say this function is get first k numbers, and it is going to take a limit, which is an integer, and it's going to return a mutable list of integers back. So what this is going to do, we are going to return a list that contains numbers 0 through limit in it back to the caller. So we can pretty much take the same logic we had before. We define some counter variable, which is an integer, and it starts off at 0. You're also going to see me, I end some of my lines in semicolons and some not. Generally speaking, Kotlin, every line of code should end in a semicolon, and some of them won't, because the Kotlin compiler can be smart enough to know when you don't need to, and it can automatically insert it for you. So sometimes you'll see me being sloppy about that. But then what I need to do is go ahead and make a list that we're going to return. So I'm going to make a return list, and that's going to be a mutable list of int, of numbers, and it's just going to be an empty list for now. And then what we're going to do is, while our counter is less than or equal to the limit, we will add our counter to the return list, and then we will increment our counter by 1. So counter equals counter plus 1. And once we break out of this loop, that means we've added the first limit items to the list. So we can use this return word called and that will exit out of this function we've defined right here and give control back to the caller. So now what I can do is I can print get first k numbers. If I wanted the first numbers 0 through 10, I could call this once. If I wanted the first 50 numbers, I could call it again. I apologize for the noise. That's what happens when you live in New York. And if I wanted the first 100 numbers, I could call it again. So now I'm able to repeat this work without actually having to re-enumerate the core part of this, like having to copy and paste this 3 times in my file. So let's go ahead and run out of this and compile it. And we can see that I get 3 different outputs. First, I get the numbers 0 through 10, then I get 0 through 50, and then I get 0 through 100. So that's pretty cool. So that's the concept of functions. Functions can take in an input, and they can spit out output. They don't have to. They could just do things silently. The function could have printed if we wanted it to. And so the last 2 things I want to explain. I've switched this to be prettier formatting now. Let's go ahead and delete it. The second and last thing I want to explain is the concept of classes. So a class is a grouping of both state and functions. So let's say I wanted to model a car. I could define a class, a car, and let's say a car has something about it. Let's say for now a car has a name and MPG, miles per gallon, and that can be an integer. Then we can say that to create a car, you could say val my car, or variable my car. The type of the variable is not an integer anymore, it's actually a type. So the car is the type of your variable, and it could be a Tesla, or Tesla doesn't really have miles per gallon, so it's a bad example. It could be an Acura, and we could say the miles per gallon is 55 miles per gallon. And so then maybe you want to print out some information about your car. So this is how we would actually specify the car class. We're saying that the car needs 2 things to be able to be created. It needs a name and a miles per gallon. And in the class, we're going to go ahead and store those. The reason I'm repeating these 2 lines is the name and MPG that get passed in here are only accessible when the instance of car is being created. So we actually want to store those as variables that belong to the class. And then let's say maybe you want to expose some function about the car. So maybe you want to say, maybe some function has good mileage. And this can return a Boolean. So we could say if the MPG is greater than or equal to 30, return true. Otherwise, it's not good mileage, we could say return false. And then I could print out here, does my car has good mileage? And so this is a function available to the car. So I'll invoke it using this parentheses. And now let's go see what happens if I compile this code. Oops. True. So then maybe another thing is I want a way to pretty print my car. So I can make a function called print car info. And this will actually return nothing, so I won't even give it a return type. And what this could do is it could print And so what this function does is it just does a simple println. But what's interesting is I actually reference the variables within this string. So this is a Kotlin specific thing. If I want to have a combination of text I write and also reference some expressions, I can use the $sign. So I'm referencing the variable name that belongs to this car and however many miles per gallon it has. And so now I can print my car. I could actually just say my car dot print car info. And so if I exit out and run the same compilation script or interpreter script, I should see that string. So the car accurate has 55 miles per gallon. That's cool. I know I'm going fast here. If you, I would encourage you, if you've not programmed before, maybe to pause the video, go look into some of this further. The very last thing that I'd like to explain is the concept of recursion, which is really difficult to wrap your head around sometimes, but it's also something that's very well explained out there, so there's a lot of resources. I will do my best to explain it here. We are going to use recursion a lot, and it's a tricky concept to wrap your head around because it might not seem like it makes sense. But what happens if I have a function, my function, that takes in some count or some number, and what would happen if I did something like printing the number and then calling the function again with some number minus 1. So this is weird. So if I call my function with the number 10, then what's going to happen is we call my function, it'll print out the number 10, and it's actually going to, this version of my function is going to call my function again with 10 minus 1, which is 9. And that version of my function is going to print out 9 and then call my function again with 8. And that version of my function is going to call 8, print out 8, and then call my function with the number 7. And so let's see what actually happens if we try to run this. So you can see there's a crash, some gibberish, and so scrolling back up, seems like we get to negative 34,240, 241, 242, 243. We keep counting down, so we keep printing lower and lower, and eventually the computer runs out of resources because it's printed too far down. Let's go ahead and try actually make sure this doesn't run forever. So maybe let's say if some number is less than 0, then we just return. And so what this means is if we call this with 10 It's going to print out 10 and then call it with 9. Print out 9, call it with 8, 7, 6, 5, 4, 3, 2, 1. We call it with 1, we're going to print out 1. It's going to recurse on itself, i.e. call itself, print out 0, or call itself, print out 0, and then it'll call itself with -1, and when it hits -1, it's going to get this check, and it's going to say, hey, some number -1 is actually less than 0, so we don't do anything, and then it ends, and then we should just see that we print out the numbers 10 down to 0. So let's go ahead and run that, and we see this as the outcome. Let's do one other very interesting thing though. I'm gonna right now we print and then recurse with 1 minus what we have. Let's print, do the recursion, then print the same number again, and let's see what would happen. So we see that we count from 10 down to 0, and then 0 back out to 10, and every number is printed twice. So if we look at the code, what ends up happening when we recurse, when we call this function with 10, we print out 10, it then recurses by calling the number by printing out 9. It lets that entire subtree of work finish, 9 to 8 to 7 to 6 to 5 to 4 to 3 to 1 to 0, and then it'll print out 10 again. So we see 10 being the start and the end. You see how 10 is the very first thing we print out, and then 10 is the very last thing we print out? The same can be said, the same is observed for 9. 9 is the second thing we print out, and it's also the second to last thing we print out. Because the function invoked at 10 will call function of 9. Function of 9 will call 8 through 0. Each of those will run, print out their numbers, and afterwards 9 will print itself again. So when we call this function and it calls itself, it's not replacing itself, it's actually creating a whole nother instance of it where there is multiple invocations of my function that are alive at any point in time. This is a very high-level explanation of programming and recursion, and I went really fast. So if that's confusing, I'd actually encourage you to pause the video and do some research on the side. My issue is I can't explain everything about programming languages in this video because I'd run out of time, and I think there's already great resources out there. I'd love to do that in a separate video to take an overlook at some of the most popular programming languages, deep dive into some of them, and I think that's actually interesting to see, like, why do we have so many programming languages, and what's similar about them, what's dissimilar, what was the evolution of programming languages. That's a cool video I would love to do, but for the sake of this video, I kind of need to be able to write code, but don't have the time to be able to explain every feature of a modern programming language. That being said, as I said earlier, I will do my best to explain everything as we progress along. So I'm going to go ahead and delete this file because we don't actually need it. That was strictly for example, and clear my screen. And now we can actually go ahead and start looking at building the first. What I'd like to do next is introduce the concept of a token. So we can effectively think of a token as a unique part of the terminal set of our context-free grammar. So every atomic piece of the input, we'd like to split out into a different token. So for example, if I said 3 plus 4, then the tokens we have here is a 3 followed by a plus followed by 4. Similarly, if I had something like 3 with a bunch of spaces and then followed by the plus or 4, this is technically a different input string, but things like white space or new lines don't really matter to us. The same set of tokens should be able to be extracted from this input sequence, which is a 3 followed by a plus followed by a 4. So pretty much what we're going to see here is the first step of building the compiler is taking our input string, and instead of working with this raw string, we'd like to convert it into a sequence of tokens so that the rest of the code doesn't need to deal with nuance of how the user presented the input. It can deal with just, here's what logically precedes the current item in the text. The other thing I'd like to call out is that I'm using the word token here to be consistent with what real compilers use. So for this video, I'm trying to use terminology that's consistent with real-world software. The reason is that I expect many people will run into complications while watching this video because it's a lot more complicated than the previous topic, and I think it's totally normal and expected that some amount of side research will have to happen. So if that is the case, whenever someone does get stumped, I'd like them to be able to have real-world terms for them to be able to search online as reference points rather than me trying to make up my own words for what I think things should be named. So a token is just this very atomic part of the language. So what I'm going to do is create a new class, a new file, where we're going to define all the tokens. And so before I even do that, what I'm going to do is copy over the context-free grammar that we just developed when I was drawing on my screen. And so I'm going to go ahead and do that. So we had E could go to E plus T. E could go to E minus T. We had E could go straight to T. Then we had T could go to T times F. T could go to T divided by F, or T could go straight to F itself. Then we had F could resolve as an integer, or F could be a nested parentheses followed by a whole nother E. So we're pretty much going to want a, oops, I got messed up there. We're pretty much going to want a token for each type of terminal that appears in this grammar. So I can see, just reading this, I can see should be a token for plus, a token for minus, a token for multiplication, a token for division, one for open parentheses, one for close parentheses, and one for numbers themselves, integers. Cool, so what we're gonna do is define an enum. An enum is just pretty much a collection of entities. We'll see why this matters in a second. So an enum class of the types of tokens we might expect in our input sequence. So we're going to expect, we just said number is one, we had plus for addition, minus for subtraction, star for multiplication, slash for division. Then we had open parentheses, a close parentheses, and that should be everything. Okay. Now, a token is going to have more than just the token type. A token is going to need to have a type, and then also what the actual value of the token is. For everything of these, it's trivial. The number is the interesting one. So if I have a number token, the actual value of the number matters. If it's 56, this is different than if the token's 10. For the rest of these, it's trivial. If it's a plus token, we already know that the character there is just going to be a plus sign. But we just have this for consistency. So we're going to define the actual token itself as a class, what we just learned about, where a token has a token type. And then it's also going to have the literal, which is going to be a string. And we're actually going to give it a default literal. We're going to say, we know for these token types, it doesn't really matter what the literal is. We're never going to look at it because we can derive the entire, we can infer the literal type by looking at the token type. For number, we cannot infer the literal value by looking at the type alone, so we will need to encode the literal in here. So that's fine. So that's actually how we're going to define, this is how we're going to represent our tokens. So the next thing we need to do is work on something called the Lexer. So I'm going to make a new file called the Lexer. And what the Lexer is going to do is it's going to take in the input of the program. For now, that's just a mathematical expression, but as we continue expanding this and adding more features, it'll actually just be considered a program. And what it's going to do is instead of, it'll take in a string, which represents the text, and it's going to spit out a list of tokens. And that way, every future part of this, we'll see like the output of this will feed into the next part, which will actually be used to generate the parse tree. And it'll be a lot easier for the logic of the parse tree if it doesn't have to worry about stuff like parsing through the actual input, if it can just see, hey, here's what the next token is. So we're going to make a class here. It's going to be called the Lexer. And we're going to make the Lexer accept the input as a string. And the Lexer is going to have a method we're going to make this top level function called scan tokens. And it's going to return a list of actual tokens. And so the class itself is going to need to know a few things. In order to come through, look at all the input, look at all the textual input, and parse it into tokens, it's going to need to know a few things. The first off, we're going to have it actually track all the tokens it's encountered so far in a variable, which will be a mutable list. I'll give it a correct type. Mutable list of token. And we will just make it an empty list of it'll be just an empty list for now. Then we're going to need to know where in the current input string we are. So a string is a series of text letters that can be numbers, spaces, or characters, and we're able to look at a specific position in that string by asking there's Kotlin methods available. So if our input string was ABC, then the character A is said to be at position 0, the character B is said to be at position 1, and the character C is said to be at position 2. So everything's 0 indexed in Kotlin, which is consistent with other programming languages. But let's say I've already processed A and B and put them into tokens for this other language. These wouldn't be valid tokens for this language. I need to know that I've already processed A, and B. So when I go to scan the next token, I should know that I'm looking at C. And so we can keep track of it by actually just saying, here's the position of the next token that you haven't yet come across. And to start with, we're not going to have looked at anything, so it's going to start at position 0. So current position, this is going to be a number, and we're just going to start it off at 0. Cool. Then we're going to want to have a few helper functions that we're going to see are going to be useful not too long from now. So I'm going to define a function. I'm going to make this function private, so only we can call it in this specific class. Externally, the Lexer should just expose this top-level scan tokens function that would return all the tokens in the input sequence. So we're going to define this to be private, and that's why I'm defining all these fields to be private, is so that no external caller can look into this class. It's not the end of the world since we're the one in charge of all the classes, but the more software you write, the more you'll see software architecture and design is an art of itself. And so it's generally a good idea to leave separation of concerns to be a real thing, and behavior that does not need to be exposed outside of any particular class should be kept private. So I'm going to define this function called advance, which will return the token at the current position and then advance the pointer that's looking at the current token that's next to be scanned. So it's going to return a character. A string is just a list of characters, where a character is just an individual letter, digit, or number, or space in the string. And what we're going to do is say we're going to get the return character. It's going to be a character, and it's going to be the input we're going to get this char at function, which will take a string and return a character to a specific position. The position we're going to be interested in is its current position. And then we're going to increment current position, so the next time you call advance, you're not getting the same character back. Okay, so this is one thing we'll do. Then the other thing is we're going to keep calling this advanced. Oops, I need to give this the correct syntax. We're going to keep calling this advanced method, but at some point we're going to hit the end of the string. And if you actually try to get a character that isn't a valid index, so in our example of A, B, C, we know 0, 1, and 2 are the valid indices, where index 2 points to the character C. If I called this char at function with any index that's not valid, so 3 or above, or any negative number, it's going to crash the program. So we actually need to know when we're approaching the end of our input sequence. So we can actually just make a function is at end. And it's going to return a Boolean. A Boolean is true or false. So it'll return true if we are at the end, false if we have more characters to process. So we can literally just check if current position is greater than or equal to the number of letters that are in our string, our input string. And we can use the dot length property to get that. Cool. And that's where we'll start for now. I'm going to save this just so we don't lose our progress. So what we're going to do for our scan tokens is we're going to check. We're going to use a while loop. While we aren't at the end, so while we have more tokens to process, we're going to figure out what the next token is and then add it to this token list that we have defined on what says line 13 up there, which is really just 13 lines above where my cursor is. So I'm going to say while we are not, this exclamation point means not, while we are not at the end, that means we have another token to process. So what we'll do is we'll have a function called scan next token. We'll make this in a second, and that'll actually go through and scan the next token. Then afterwards, by the time we break out of this loop, it means we have no more input left to parse. So we'll actually just be able to return all the tokens that we parsed, which is going to be stored in this variable right here, this list of tokens. So now we need to make this private function scan next token. And it's not going to return anything. What we're actually going to do is just have this function figure out what the next token is and write it into that tokens list. And so we're going to need to call this advanced function. So we need to get the next character that we're going to process. So current character is going to be the result of this advanced function. So this will pull the next character that we have not seen and then update the internal state so the next time we call this function, we get the next, we don't get the same character, we get the next one after it in the list. So we call this current character. I'm actually going to give it the correct variable typing, which is just a char. And now we need to actually go figure out what that char is. So if the current character is a open parentheses, then we know we actually have a token of type open parentheses. So what we can do is take our tokens field from up here, and we're going to say tokens equals tokens plus this new field. We're going to create a new token, and that's going to have a token type. And here's where I actually need to go back to our other file. Token type of open parentheses. And we said it doesn't really matter. Like the other field to put in was this literal. We gave it a default value, which means we actually don't need to specify it. And in our case, for the type of an open parentheses, it doesn't really matter. So we can actually just leave that alone. And I'm going to go ahead and copy the rest of these over, because we're just going to have to repeat the same logic for all the rest. So this works for the open parentheses. Now let's check else if. So if it's not an open parentheses, let's check if it's a closed parentheses. So if the current character is a closed parentheses, then we can do exactly what we did here, except instead of returning the type as open parentheses, we return the type as closed parentheses. We can cross these two off of our list. Now we'll check if the current character is an addition sign. If it is, we'll do the same thing with the token type being plus. Similarly, we'll check if it's a subtraction sign. That leaves star slash and number. The order doesn't matter here because it'll just fall through this if, else if, else if, else if until it finds the right one. And the last one is a slash. And so that leaves one other token left, and that's number. And number's a little tricky because every other token we just looked at actually only used a single character. However, a number could be multiple digits in our case. We could do 234 plus 3, and that 234 should not be parsed as tokens 2, 3, and 4. It should be one number token that's actually typed as having a width of 3. So what we need to do is figure out some logic that lets us figure out how many digits are in the token. So if the current character is a digit, that means we're working with a number. And I'm gonna break this logic out into a separate function, just called scan number. And so let's go ahead and define this. So private fun scan number. It's not going to return anything. It'll just update the state of the class internally. And what we'd like to do for this scan number is pretty much something akin to, while we have a next character and that next character is also a number, keep expanding and eventually get to a point where we know where this number starts and ends, and then we can clip a substring of the original input string between that range and figure out that's the actual number that we're looking at here. So in order for me to look at the next character without actually consuming it, I need to build a small peek function. The reason I need to do this, rather than just looking at the next character, like we know that current position is the current position. I can't just look at current position plus 1, because if my input program ends on a number, then I could be looking at the last digit in a number, and I could try read the next one, and it'd crash my program because we're actually reading beyond the length of the input string. So we need to have a function that can peek, but also handle cases where we are out of input to look at. So I'm going to make this private function peek. It's going to return a character as well. And what it's going to do is it's first going to check if we're at the end. So if we're at the end, i.e. we have nothing left to parse, then it can just return, we can just return, I guess, 0 for now. So 0 is not going to be in the range of any digit. We'll check, like, if we peek and the next digit is greater than the character representation of 0, and also less than the character representation of 9. 0 is neither of those. 0 means there's nothing left there. So we'll check that. Otherwise, we can just pretty much return source and get the character that's at the current position. Current position because we've already incremented it when we called this advanced method to get there. So now this scan method can do something pretty neat where we can get the starting position of the number. So val starting position of number, and that's going to equal the current position minus 1 because we advanced it. And now we'll do while peak is a digit, we can keep advancing. We can keep scanning this token, scanning this character, because we know it's all part of the same numeric token. Eventually we break out of this loop because we have nothing left to look at, and then we can add a token to our tokens. So tokens equals tokens plus, and we'll create a new token. That token type let's see what it's called in this other file, number, and the actual value we'll pass in will be a substring of our input sequence. Our input sequence is defined by this variable named input. And we will substring from the starting position of the number to wherever we are at now. And the reason why we can do to wherever we are at now is because the substring function has this oddity that it substrings from this starting position to not this ending position to one character before this ending position. So when we keep looking at numbers that happen consecutively, we're eventually going to get to the last one. We're going to scan one past it, which will be the next token or the end of the sequence. And if we get there, then that's the first character we actually don't want to include. And since this API that we're calling returns all the characters up to that point but not including it, it actually works out in our favor. So this should work. And that should actually scan our number. And there's actually one other thing. I'm realizing, I think basically, if we're at the end, we just want to return some character that's not a number. So I'm just going to return some random character. I think returning 0 might cause an issue. The last thing we need to check, so we've handled all of the terminals, but we also need to make sure that we just skip over white space. So I'm going to say if the current character is equal to just a space, or there's a few other ways we can represent white space in code. One is a new line. If the user decides to use a new line in the middle, that's valid. We don't want to consider it. Or if the user uses a tab, then we don't want to consider it. Or there's also /r for carriage return. These are all just various forms of white space. We do nothing. That's fine. Ignore white space. Else, if we made it here, it means we have some issue where the user has done something that is not allowed. They've put some sort of input in here that we do not recognize. So we're actually just going to crash the program if we make it here. And the way we can do that is, there's a few different ways. Oops. But ooh, that's weird. Oh, there we go. So if we make it here, it means the user's put in a token we don't recognize. So Kotlin has this system function called error that'll just crash the program. So what we can say is error unexpected token current character. Cool. So this should be a baseline implementation of a Lexer. What we're going to go ahead and do, I'm sure there's issues with this. So what we're going to do is try actually feed in some sample input, call it through this Lexer, spit out the tokens it gives it back to us, and try compile that program. And I'm sure there will be at least one compilation issue. So I'm going to go ahead and make a new file, main.kotlin. And here's where we can just pretty much try create a fictitious program and feed it into this Lexer and see what tokens it gives back to us. So when you actually compile Kotlin, it's looking for a function called main, and that's actually where it begins executing all of its code. So we've currently split our logic across several files, which is fine. But if you have several files with a bunch of different functions, Kotlin needs to know where you actually intend to start execution. So it's looking for this function called main. And this main can also take a set of arguments. We aren't going to use it yet, but we will use it very shortly from now. So I'll go ahead and specify it anyway. And let's just create some fake source program. So let's start simple with 6 plus 3. 6 plus 4, that works too. What I'm going to go ahead and do then is say that we know that our tokens can come from list of tokens can come from the Lexer. If we feed in the source and then ask it to scan tokens, and then what we can do is just print out the tokens. Cool. Let me go make sure I use the right name. So in Lexer, we call this function scan tokens. Scan tokens, that looks correct. Cool. So now what we can do is hop out of our editor and actually try compile this code. So since we have several different files, I'm going to put them all into one folder. Right now we have, oops, I should really remove this. I didn't realize I was creating files for our examples from earlier. That was a nuance of shell that I, kind of funny, don't worry about it. But we have 3 files. We have Lexer, main, and token. This .git file is just from the GitHub page I was showing you earlier. Don't need to worry about that either. I'm going to make a new directory. This is equivalent to creating a folder. I'm going to call it source, src, short for source. You'll see that in a lot of GitHub code if you end up looking into further stuff that's out there. And I'm going to go ahead and move the Lexer into source. I'm going to do the same for main. And I'm going to do the same for token. Now we see there's nothing in here but a file for source, and I can print out a tree. We can see all the 3 files are now under source. So to compile this, I have written a program in Kotlin, and my computer has a compiler, which is funny because we're now using Kotlin to build a compiler, but I'm going to have to compile that using a different compiler. And so that compiler is called Kotlin C. And I'm going to tell it to compile everything in this source folder. So anything in the source folder whose file ends in .kt. I'm going to throw in a few different flags to this compiler. Don't need to worry about what they are for now. We can come back to it later. But I'm pretty much telling the compiler, take all these files, bundle them together in one run file we can get, and it knows to look for the main function to figure out where it should actually start ordering the code. And I'm expecting to get some compilation errors. Yeah, plenty of errors. Okay, so I'm getting a lot of values cannot be reassigned. That is expected. So I think that's part of debugging here is looking at this. So let's go ahead and hop back into our Lexer. Seems like there's a repeated error that we are adding too much. There's a repeated error that where we have this field tokens, and so tokens is a mutable list, and we keep reassigning it pretty much right here. This isn't right. So instead of tokens equals tokens plus, we can actually use, I believe, shorthand syntax. And this will let us accomplish what we want, where we add one item without necessarily replacing the actual reference itself. So an alternative, and I think I'll just prefer this to be clear, is a mutable set has a function called add, which just adds to the end of it. So we'll go ahead and just use that everywhere. Okay, I saw another issue that char at was not a valid. So to get this is not a valid language construct in Kotlin. I'm mistaking that from another language. This should fix that. Let's go ahead and try recompile again. We're definitely gonna have other errors. Hopefully we just have fewer errors. Okay. We are missing a return statement on line 9 of the Lexer. Okay. We need to return the return character here. That makes sense. Then on line 26, we are referencing an unknown variable named source. And that's because our input variable name is named input, as you see up here on line 1. That's a good call. And 34 of Lexer. Oops, it looks like I missed a... yes. I need to use the same API here, this .add. And on the main file, we have a complaint on line 3 that token is not a known class name, and that's because tokens is not a known name, is not a real name. Token is the correct name. Let me try compile this again. Okay, not as many errors as I thought we'd have. So now that we've compiled it, if I tree our current directory, we now have this new .jar file. That's a compiled bundle that we can now feed in, and I'm going to take the Java virtual machine. So this Kotlin code is compiled to an intermediate language. We are going to invent our own intermediate language not too long from now, and that's what our compiler will compile to. The Kotlin compiler compiles to this intermediate language called JVM bytecode, and we'll talk a little bit more about this at the end. I think Java will be the interesting example study. But it's compiled to an intermediate language, and that's stored in a jar, and now I'm going to tell my computer to run a simulation of those instructions and execute them on my computer's actual hardware. So if I pull this out, I see that we have 3 token types. One's a number, one's a plus, and one's a number, and we see that the 6 and the 4 are handled correctly. This actually looks good. So let's go ahead and do one other thing. Rather than printing everything on one line, let's go ahead and print each thing out on a separate line. So the way we can do this is using a for each loop. So this is just a shorter way of saying tokens for each token. Look at the current token and just print that on its own line. And that way, if I run this, then we can see things are printed out on their own lines. So this looks correct. Let's go ahead and give it a expression that uses every syntax operator so we can make sure that that works fine. So let's say 4 times 2 divided by 6 divided by 5, sure, subtract 3, or 3, yes. 3, I just want to use unique numbers. Okay, let's look at that. Compile this. Run it. I see a 6 plus, I see the open parentheses, the number, the multiplication, the other operand, the close parentheses, the division by another number, and then subtracting 3. That looks fine. So now we can see that we've taken our input and we now spit out a list of tokens that actually correctly represents it. Let me do one thing to point out something. So we know if I did something like this, this is not a valid string according to the context-free grammar. It's just a bunch of pluses, but that's not the job of the Lexer. The Lexer should just be pulling out the tokens from the input stream. And so we see that even though we know that that's not a real input string, it does correctly pull out all the tokens from the input string. The other thing that I'd like to verify that I claimed earlier was that any amount of spacing shouldn't really matter here. So I'm going to comment this out. So 6 plus 4. I can even get rid of the space here. This should work totally fine. It should give us a 6, a plus, and a 4. And see, that works totally fine. So great. Now we've finished the first part here, where we've taken our input string and spit out a series of tokens that represents the structure of the input. The next thing, as we just saw, is that this doesn't actually tell us if the input is a legitimate input program according to the context-free grammar we developed. So the next step will actually be trying to figure out how can we now walk over all these tokens and figure out what the correct parser is that builds up the tree of items here. And before we move on to the parser, there's two other changes I want to make. The first is you can kind of see that to compile things, we run this long command. It's kind of slow. And right after we run it, I kind of want to, instead of having to keep going back up in my command history to find these commands, I'd rather just make a script that'll compile and run these at the same time. And so I can just execute that in one file. So this is not a thing you need to know, but it's called shell scripting, where you can just chain commands together, and that way we can easily refer to it. So I'm going to do that by copying and making some new shell script. Shell scripts end in .sh. So I'm just going to call it run. I'm going to paste in this first command, save the file, and then paste in the second command. Save the file again. And now I can just do dot slash. Dot slash refers to the current folder we're in, and just name this. Oops. So I get a permission denied. I can just change the modification. This is not something you need to know if you're not familiar with programming. But for context, what that's doing is it's pretty much we created a file, and files are by default read and write friendly, but they're not meant to be executed. So chmod stands for change mod, and I add the x modification, x permission, which allows you to execute the file. So instead of treating the file as just some text, you can actually treat it as a program. So now I've added that modification, so now I should be able to run, and you'll see that it does both steps for us. So that's convenient. The second thing I'm going to do is hop back into the text, and you'll see in our example, actually, if I jump out, that it takes a few seconds to compile, that there's not an easy way to tell when we've reached the end of our input sequence by the tokenizer. We see the number plus the number, and we can see intuitively there's nothing more, but when we actually go to build this thing that we're going to call the parser, it'll be very convenient if we have an explicit token that just says, hey, this is the end of the file, there's nothing that comes after this. And it may just seem trivial, like, hey, you could just check if you're at the end of the list of the tokens. But in generally compiler design, we see this token called the EOF, which stands for end of file. So we're going to go ahead and add that just to be consistent with other compilers, and it'll make our job in a few minutes easier. So to do that, going to go to our token types and add an end of file token. Then I'm going to save that. Let's hop to the Lexer class, and it's pretty straightforward. So this is the top level function. I'll add a comment. Top level function for taking the input and finding all of the tokens, handling byte space. And pretty much what we do, this is the function that's public and that gets called. Pretty much while we're not at the end of the input, we keep scanning tokens, and then we return the list of tokens in this class variable called tokens, defined on this line right here. All we need to do is right before we return, let's just create one more token that is the end of file token and add that to our return list. So what I can do is tokens.add, and I can make a token. The token type is end of file. And that's all we need to do. So now if I go ahead and run, we'd expect we get this arithmetic expression. So we see the number plus the number, and the very last thing we see is this end of file token. So that's nice. Token doesn't actually mean anything besides helping us understand that we reached the end of the file. And the other thing I need to go ahead and do, I'm seeing, is I need to update just the grammar. This is the old grammar that we were going with. We decided to go with the easier grammar to understand. So let's go ahead and update that actually. So we know that a E maps to a T followed by either a plus sign or a minus sign followed by another T, and that can happen any number of times. Then we know a T was the same thing, except it maps to factors, and a factor in F is usually a multiplication or a division followed by a factor, and that can happen any number of times. And then lastly, a factor was just either a integer or it was a literal open parentheses followed by a whole new expression followed by close parentheses. Sweet. So that was just something that I originally forgot to do earlier. I used the second last grammar, but the two grammars we looked at parse the same language, and that's the same language that we're looking at building here. They were structurally equivalent in terms of what strings would be valid expressions or not. So all the token types we represent here are also supported by this grammar, and they're the exact set of tokens we would need to encode this grammar. So that's just, I wanted the comment to be up to date. So let me go ahead and save that. And cool. I will also go ahead and make a commit here. So I talked about the GitHub repository earlier, and I said that we could freeze the code at certain points in times. We're at a good stopping point in terms of making the tokenizer, the Lexer. So what I'll go ahead and do is freeze the code at this point in time, now that we're at a good stopping point and a working set of code that we have. And you'll be able to then go ahead and, if you're curious, jump and see what the code looks like at this time if you are curious to see what everything looks like. Because as we build more and more features, we're going to add more and more files. So you might want to see like, hey, what was in that other file, even if it's not on my screen. Okay, and let me go ahead and I'll also add in our script in case you want to run this yourself. Then we can make a commit. A commit is called is the formal term for a snapshot of code at a specific point in time. And that can be called Lexer fully complete. Sweet. Okay, so if we want to think about how we're going to represent our tree in a data structure, we saw that for each item in the tree, an item in the tree, as we said earlier, is called a node. A node was either a operator, i.e. an addition, a subtraction, a multiplication, or a division. And if it was an operator, it had two children, which themselves are nodes. Or if it wasn't an operator, it was just a literal number, straight up like a 5 or a 50 or a 45. And so we know there's two types of nodes in the tree. A number node just holds a value and does not have any children under it. And then a binary node is what we'll call an operator. And that node has an operator, so it needs to represent what mathematical operations performing, whether that's addition, subtraction, multiplication, or division. And then if it does have a operator, if it is this type of node, then it must have two children, and those two children are expressions. It does not matter, or it matters, but the children expressions themselves could either be number literals or binaries. It doesn't really matter. That's how we get this tree-like structure, is when the children of a binary node are also binary nodes. So To represent this in our modeling, how we're going to model this in data, one of the foundational parts of software engineering is figuring out how you actually want to represent data. We're going to define how we actually want to represent the items in this tree. So what I'm going to go ahead and do, before we actually start building the parser, we need to define the structure of what we're going to parse the tokens into. How are we going to represent this tree in using classes that we talked about earlier? So let's go ahead and make a new file. Exper. It's just going to be short for expression. We're going to have to type this a lot, so I like the shorthand notation. And this is going to be how we're going to represent our expressions. And so ignore the syntax of the Kotlin language here. But I'm just going to say we have a class called expression. And something I did not call out earlier, but is important to know, is that classes there's an inheritance relationship between classes that's possible in the Kotlin programming language. So we talked about I think I used car as an example class earlier. The car class could be a child class of vehicle. And so maybe there's a parent class called vehicle, and there's children classes for car and boat and motorcycle or bicycle. And the parent class, the relationship means that each one of those is an instance of the parent. So a car is a vehicle, a boat is a vehicle, a bicycle is a vehicle, and that's how we're going to model things. So we're actually going to define this expression, which is just a node in the tree, and there's actually two types of expressions, a number literal or a binary expression. So the easier is the number literal, and all that this class is going to hold is the value. We're working with whole numbers, integers, so it's just going to hold an integer. And this class is a type of expression. So number literal is a type of expression. And now the other thing that's a type of expression is a binary operation. I'm just going to call it a binary. And so a binary has more than just the value. It's going to have an operator and then two children. And so we know what we've been seeing when I was drawing this out on my iPad, we had a left child and a right child. So it's kind of the items in this binary node is going to be one, a left child. The type of that left child will be an expression. Then it'll be an operator. For now, we'll just let that be one of the tokens. And then a right child, which itself is another expression. And then binary itself, this binary node, is an instance of an expression. And so it turns out this, what do we have, 8 lines of code, fully represents all of how we are going to represent our parse trees. Because you will start with an expression. That expression, if there's no mathematical expression, if the user just inputs a 5, it'll just be a number literal. In the majority of cases, there will be some sort of chaining of arithmetic expressions. So we're going to start with a binary node. It's going to have some operator, and the children themselves, it's going to have 2 children, and those can be expressions. And those can arbitrarily either be number literals or binary expressions themselves. So we're going to have this tree, and at the end, everything at the bottom of the tree is just going to be number literals. So this is how we're going to choose to represent things. So now that we have our choice of how we're going to represent things, we could actually start looking at how we're going to build the next step of this, which is called the parser. So let's go ahead, save this file, and I'm going to make a new file called parser. The parser itself will be a class. It's going to take in tokens now. And this is a little bit different. So we're actually one level of abstraction up now. The previous class we built was the Lexer, and that just took a raw string as the input and spit out tokens. Now we're not looking at the input directly, we're looking at the tokens that represent the structure of the input, the semantic ordering of items in the input. So in our parser class, we need not be concerned with issues such as white space, because that's all handled in the Lexer, which gives us the tokens. So we kind of have, like, at the lowest level, we have text input, then we have the Lexer, which gives us tokens, and now we're going to have the parser, which gives us the actual the expression, tree-like representation. So this is also a pretty popular or common topic of discourse in the art of software engineering is layers of abstraction and separation of concerns. And we can kind of see that we're getting to it, and we're going to keep expanding on this with more and more layers. So let's go ahead. Our parser now that we have a list of tokens, we're going to be walking over that list to try to build out instances of these expressions and build this full-on tree. And so we need to keep track of where we are in that list of tokens. So I'm going to make a variable that's private to this class. So only we can access it in the class, but like in the main class where we create it, where we will eventually create an instance of the parser, it won't be accessible there. And all this is going to track is the current position. And this itself is an integer. There's a number, so it starts off as 0 because the same way that strings, the first character in a string is the 0th position, that's true for lists as well as it's true for lists in the Kotlin programming language. And it's true in most programming languages. You'll see that the very first item is position 0. It's kind of counterintuitive because in English, or just in the real world, when we're counting things, we usually start at the number 1. There's a very real reason why computers actually start at position 0 that's not obvious in these high-level programming languages. If we take a look at a different lower-level programming language, which I'd like to do in a future video, there's actually a very cool reason, and one that'll make things make a lot more sense as to why we start at 0 instead of 1, but that's out of the scope for this video. And so, similar in the way we did the Lexer, I started by defining some helper functions before we actually started getting into the meat. I'm going to do the same thing here. So the first thing we're going to want to be able to do is have this peek function, which will look at our current position and just tell us the token that's at that position. So this one's pretty straightforward. It's a private function, and we're going to call it peek, and it's going to return a token to us. And all it's going to return is the tokens. It's going to take that list of tokens and figure out whatever the token is at the current position. Start off with 0. Okay. And then a natural question off of that is we're going to start walking through these tokens, calling this peek method, until we're at the end of our input. So the next thing we should do is define a function that tells us if we're at the end. This will return a Boolean. It's true if we are at the end, false otherwise. And what this will do is it'll call the peek function, it'll get the current token that corresponds to the position in the variable current position, and it'll literally just check the type of that token. Remember, each token has a property on it called type, which is a token type from that enumeration, and we'll check if the token type is equal to end of file. So that's kind of convenient. Now, we have our current position that starts at 0. We're going to want to be able to comb through the input, so we need a function that'll actually bump that pointer up. So we're going to then define a function called advance. What this will do is it'll return the next token that we haven't yet looked at in the sequence. So what we're going to do is, what we like to do is something like return the token at the current position. This is what we'd like to do. But the issue is, let's say we are already at the last item. Let's say we're at the end of file item. Oh, sorry. What we'd like to do is increment current position. So current position equals current position plus 1, and then return the next token. Let's say, though, the issue is that we're already at the last token in this file, and we accidentally call this function. We wouldn't want to advance any further. If we're looking at the end of file token, there's nothing after it. So it would be an issue if we had 5 items in the list, and we tried to then get the 6th item, it would crash our program because there's no 6 items. There's only 5 items in the list. So we'd actually need to defensively check if we're at the end before we increment this counter. So if we are not at the end, and we can check if we're at the end by calling this function we just built, then we can increment the counter by 1. Otherwise, if you're at the end and you try to advance, we should just throw you the token you were already looking at. And then we need to return the previous token. So the deal with advance is it'll return, you call advance to get a reference to the current token. Our logic right here will then bump up the counter. So if we're looking, the very first time you call this, the current position variable is 0. So we bump current position to 1, but we'd actually like to return the item at position 0 because the very first time you've called this, we haven't returned item at position 0 before. So we'd like to call tokens at current position -1. Oops. So the very first time you call this, current position will be 0. We increment it to 1, and then you return the index of this list at 1 minus 1, which gives you 0, which is the first item. Then the second time you call this, current position goes from 1 to 2, and then we return the token at index 1, which is the second item in the list, and so on and so on. And it turns out this idea of returning one beyond, the item previous to the one we just looked at is going to be so frequently used later on in the parser that I'm just actually going to pull this out into its own separate function. This function called previous, and this will return the last token that we looked at. And so it's equal to this line we have right here. So this is just the same as me returning this previous. So that's useful. Let me go ahead and save this file. There's a few more helpful functions we're going to want to get to. The next one is checking. So, oops, my focus is all messed up. So let me go ahead and copy over our grammar up here again. And I can actually do that just by hopping over to, I believe we defined this in token. Cool. Just for our reference. So when we go to parse an expression, we're first going to check to see, we're going to try parse a term, and then we're going to try, after we parse the term, we're going to try consume either a plus sign or a minus sign token, a token with type plus or a token with type minus. And if we have one of those, that means we should have another expression afterwards. So we're going to want a function that actually lets us check what the next type of the token is. So we're going to make a function called check, and it's going to check if the next token in our list has some type that's equal to the parameter passed in. So we'd be able to check, is the next token a plus or is the next token a minus in the example that I just contrived above. And if it's not clear why we're defining so many functions before we use them, you'll see in a few minutes. It'll be nice. A lot of the logic we have is repeated, and it'll be nice separation of concerns if we already have these helper functions that abstract some of the trivial checking of where we are in the list. So check will say, there's two things. We'll call this peek function, which will let us look at the token of the current position. So we'll call this, we would like to return, call this peek. Let's peek at the next item that we haven't yet looked at. Look at the type of it, and see if it's equal to the type that the caller passed into the function. So if the very first item in the user's input was the number 6, then we'd call peek, current position 0, so peek would return the first item in the list, which is just a 6. The type of it would be number, and so then it would return true if we were checking for a type of number and false for any other token types. The one tricky thing, though, if you read through this code, is if we call advanced enough times where we hit the end of our input, then our current position is actually going to be equal to 1 past the highest index that we could check in the list. And what we'll need to do to handle that is check if we're already at the end. If we're already at the end, then we should just check if the user is seeing if we're at the end of file token. If you don't understand why this check right here is necessary and why we couldn't just do this, go ahead and look at all the functions we made and give yourself the example of just the phrase 6 plus 3, and you'll see that by the time we get to the end, if you tried to call peek, you'd crash the program. I'll leave that as an exercise to the viewer, but this is a necessary check. Then we're also going to want a function where we expect something to happen. So for example, in our grammar up here, if I get to the point where I'm parsing an f and I don't see an integer, then I would expect there to be an open parentheses, And if there's not, that means we can't parse the current factor term. So there's an illegitimate input, and we should actually just crash the program and tell the user, like, hey, this program's actually not parsable. So we're going to define a function that helps us do that, and it's going to be called consume. So consume will take a token type, and then it's also going to take a message, which is a string, and it'll return a token back to the caller. And so what this function will do is it's going to assert that the next token is of a particular type, the type that is specified by the first parameter of this function. If it is, all we will do is return that token and advance our counter. If it's not, we'll just crash the program with the error message specified in the second parameter message. So now we actually have functions that we've built that makes this really easy to do, so we can just call what we already have. We know from the function we just built, check, that we can use this to check if the next token is of a certain type. So what we'll do is we'll call this check method with the type. If check returns true, it means that the next token in the sequence was the type we expected. So we can just return that token in advance. We return the next token in the sequence because check works by peeking ahead of the next item. So we're saying, hey, check will tell you the next item is of this type. So if the next item is of the type you expect, we can go ahead and advance our cursor to consume that token and return that to the caller. Otherwise, if we don't make it to that return statement, that means that check returned false. So the next item in the list is not of the type that we want it to be and we need it to be. Therefore, the user input must be invalid. So we'll crash the program using this built-in Kotlin standard library function that comes available to all. It's predefined for all Kotlin builds, and we will just error out with the message. And so this is the first way. We'll see when we actually call this. This is how we're actually going to start being able to defensively filter out text that is specified by a call of our program, i.e. the call of the compiler, that isn't actually a valid mathematical expression. The very last thing we'll do is make a function that'll help us perform multiple checks at the same time. What I mean by that, it'll be helpful for us when we get to right here, when we're looking, let's say we started with our start symbol E, we've parsed the T, and we see an open parentheses. So that means we should expect either a plus or a minus sign. It'd be nice if we could call a function and say, I expect either a plus or a minus sign, rather than needing to call two separate functions. One that says, hey, is the next item a plus sign? And if not, hey, let's check is the next item a minus sign. If not, we know we have an invalid input. It'd be nice if we could just say, hey, I'd expect the next token in our input sequence to be either a plus or a minus. Otherwise, something's wrong. So we're going to define a function that just lets us check multiple types at the same time. It's going to be called match. And it's going to type in a var arg stands for a variable number of arguments. So you could pass in either a plus or a minus or a plus minus multiplication. Any number of items to this function works. And it's going to return out a Boolean. So what this will do is it'll look at the next item, it'll check the next item in our input sequence, look at the type of it, and see if it matches any of the types specified by the caller of this method. If it is, then it matches our expectation that the next token is what we'd expect it to be, so we'll return true. Otherwise, we'll just return false. It doesn't need to crash the program, we can just say, there's nothing else to do here. So I will iterate for every type in this types parameter. So in our example we just looked at, it'd be like a plus or a minus. For each of them we'll check. Let's just check if that's the next item type. So we'll call the check function we just built out, which does exactly this. And if we do check and it is the correct thing, we'll go ahead and advance it. We'll consume that token, return true. Otherwise, we'll move on to the next thing. Let's say we make it outside of this loop. That means we've checked all the types and the next token doesn't match any of them. We're not going to crash, we'll just go ahead and return false. Cool, so let me go ahead and save this. And this is now all the helper functions we need to go ahead and start building out the true meats of the parser. Okay, so we now have these baseline functions. Let's go ahead and look at their grammar for a second. And so I previously said when I was drawing on my iPad that the way this grammar, this final grammar we looked at, is structured in a very interesting way that makes parsing through it actually very easy. And so this is going to be a little tricky, so we're going to start small, and we're going to learn by example, because it's not too many lines of code we actually have to write to finish this, but it's tricky to wrap your head around at first because it says you use recursion, the concept we saw earlier where functions can call themselves. So the way we actually build this, what we're building is a recursive descent parser. So recursive means recursion. We saw that earlier. It's when a function has the potential to call itself. And then a descent implies that we're traversing down a tree, i.e. we're traversing down some ordered structured grammar that has precedence baked in. And then it's a parser. We're ultimately, at the end of the day, taking a stream of tokens and parsing it into some final output. So the way we build a recursive descent parser is we're going to start with exposing a top-level function. This will be public, and this is what the main class can call. But inside of that, we're actually going to build functions for parsing each of these. We'll build a parse expression, build a parse term function, and then also a parse factor method. So the top-level function will look something like this. Notice I'm not marking it private. And it's going to return an expression, the type we defined earlier. And to do that, it's going to need to know, we know that to start, the start symbol is an E, an expression here. So we're going to have to have some method called parse expression that knows how to handle from the input this right-hand side here. So I'll go ahead and make a parse expression. And this will also return a type of an expression type that we defined earlier. This parse expression is going to come across a T. The very first thing that parse expression does is it should look for a term factor. So it's going to need to be able to call this function parse term. It doesn't need to have all the logic for parsing the term. It should just know, hey, the first thing I expect is a term, so I'll parse it. After it calls a parse term, it can check if there's an open parenthesis, or sorry, it can check if there's a plus or a minus. If it is, that means that there's the star in this example is representing not 0, it's not representing no repetitions, it's representing at least one repetition. So if it finds a plus or a minus after it parses the term, then it needs to consume that token and then parse a term again. And the logic for parsing this T in this T is the same because of what we saw, the context-free part of the context-free grammar. So we have repeated logic, so it actually makes sense to separate this out into a function because it's a repeated body of work we'd like to do. Lastly, we'll have a parse factor function. This is also going to return an expression. And this one is easier because we either have an integer or we see that we're going to see an open parentheses followed by an expression. So let's go ahead. I'm going to go ahead and comment this out. And actually, no, we'll keep it. Let's start with the parse factor because this is the easiest. So if we are calling a parse factor, it means that we are expecting an F term. And we know an F term is either a number or it's an open parentheses followed by an expression followed by a closed parentheses. So let's just go ahead. Case 1, integer. So we can use the functions that we built now to make this a lot easier to implement. So the first thing we're going to check is if we match a number. So match, remember, it looks at the next unseen item in our list of tokens, and it'll check, is the token type equal to the argument? In our case, we're passing in a number type. So it'll check, hey, is the next token that we have yet to look at a number? If it is, then we know that the factor term is the left-hand side of this equation. So what we'd actually just return is a number literal instance of the expression we saw earlier. If I hop back to what we defined this expression at, there's two types of expressions we can create, either a binary one or a number literal. In this case, we're going to want to return a number literal where the value is equal to the value of the token associated with that number, because recall that a token has a literal field, which is a string. Let's go back to our parser. This one's easy enough. So we'll go ahead and we'll make it an instance of this number literal expression. And the value we put in has to be the value that's stored in the token. So there's a little bit of an issue where we could get the last token. So recall that match, if I jump to this. Match says, because of this line, if the next token actually matches the type, we'll go ahead and advance. So we skipped past the token. We'd actually need to go look at the previous token to figure out what the value was inside of it. If we call match in this case, we have a number type token. We're skipping past it. So we actually need to go one back. And that's exactly what this previous method does. It lets us look at the previous token we called out. So we'll go ahead and look at the previous token because we skipped past the number by virtue of making it inside of this if statement. And then the tricky part is that we can pull out the literal because we know that each token has that literal field that we just saw. Oops. But that is a string and we need to convert it to a number. The field in the constructor, when we define this number literal, expects an integer as we saw in the definition. Luckily, Kotlin has a super simple built-in function that'll just take a string and it'll convert it to an integer. If it's not a valid integer, then we have an issue, but we know that our tokenizer is correct. Our Lexer is correct. We already looked at some examples previously to verify that it's behaving as expected. Sweet. So that looks good. The case 2 is that we have a open parentheses followed by an expression followed by a closed parentheses. So we can check this. So let's try match, the same way we try match the next token for a number, let's try match the next token for an open parentheses. Eventually we know that since we've matched an open parentheses, we should parse an expression and then we'll end out by consuming a closed parentheses. So you know at some point we should call this consume function because we're not checking, we demand that in order for this program to be valid, there has to be a closed parentheses. And the error message real fast is failed to parse a factor. We can just say it so it's easy. Expected following an open parentheses. My face is probably cutting that out, so let me scroll down a little bit. That looks fine. Okay, but before that, we actually need to parse an expression. We haven't built the function yet out, but we actually know that there already is a way to do this. And so that's by calling this parse expression. And so parse expression, recall, returns an expression type. So we'd actually want to capture this. So the type expression. So we'll call parse expression. It'll give us an instance of expression. That could be a number literal, or it could be a binary expression that has any amount of depth to it. It just depends how much the input happens to have inside of the parentheses, as determined by the user program. Darn, just spilled coffee on my shirt. That's unfortunate. I'm going to go ahead and throw it in the wash. But let's get through this first. We parse an expression. Then we consume the closed parentheses, make sure it's valid. And then our parse factor actually needs to return an expression. So the last thing it needs to do is return this expression. Okay. So this is all the logic we actually have for parse factor. Parse factor is the easiest, but the tricky part is this parse expression. We're calling a parse expression, but we actually haven't defined what parse expression looks like. So let's go ahead and do that. Parse expression, we know, it should look for a term to start with. So the very first thing that parse expression should do, is parse out a term. And we're going to capture that in a variable because that's the parse term, which we have not yet defined, have we? We've not yet defined a parse term. Let's go ahead and define that. It's also just going to return an expression, and we haven't done the implementation yet. So we're going to get the working expression, and that's just going to equal parse term. It's going to be of a type, of an expression type. So we parse out this initial term. And now, after that, we have this part of the grammar right here. I'll paste it down here. Oops. And so what this says is, to parse an expression, we know we for sure start by parsing a term. After we parse the term, there is a possibility for any number, 0 or more, of something to happen. And what that something is it's either a plus or a minus sign followed by another term. So we could actually check, we could see after we parse the expression, we could check once. So we could say, if we match either a plus or a minus, and this is where this function we defined earlier that could take in any number of inputs and tell you if the next token matches any of them. This is the reason I made that separate function explicitly, because for this rule, it's convenient to be able to just say, hey, we're curious on either matching a plus or a minus. It doesn't matter which one. So we could say, if we match a plus or a minus, then we know there's another term that comes afterwards. But if we match, recall our match function moves the cursor forward one, we need to figure out if it was a plus or a minus. So what we can actually do is capture the operator, which itself is a token, by calling this previous function again. And this will get us the item that we just give pi, which by virtue of us entering this if statement is either a plus or a minus. So then after we parse a plus or a minus, we know another term follows. So we can say parse term, and this is an expression, and we call this parse term again. So we're calling parse term again. And afterwards, we need to return the overall expression. So we'd want to say return a binary expression where the left-hand side is this working expression, the very first thing we parsed out. The right-hand side, the operator would just be the operator token. That'll tell us if it's a plus or minus. And the right-hand side is the second term that we parsed out. So this would let us check. This function right here would work if we had t followed by a plus another t, or a t minus another t. But it's actually possible that the star says we could have two. We could have another plus or minus t afterwards, but our function here doesn't really capture that because we're only checking for one future thing. So the star, remember, the star means this could happen any number of times. So rather than using an if statement, we're actually going to use a while statement. There's two things we need to change. So let's say while we have, so after we parse the initial term, we'll keep checking. While there's a plus or minus afterwards, it means there's another term that we need to parse out. So we'll consume that operator and then parse another term, and then we actually need to form that into a binary expression. The interesting part is that we saw in the example I did on my iPad that if we have 6 plus 5 plus 4, then we'd start by parsing the 6 and 5 into a plus a 6 and 5. I'm using these parentheses to capture precedence. And afterwards, when we see the 4, we'd make this 6 plus 5 be the left child of a new binary tree. So every time we actually encounter a new plus sign, we should make whatever our working expression is up until that point the left child of a new tree, and then save that new tree in case we need to have another thing we need to parse out. So what I'll actually do is this working expression, instead of returning right here, I will replace working expression with a new expression where whatever expression we had before becomes the left child of the tree, and then whatever we just parsed out becomes the right child of the tree. And this is just that left unfolding we saw happen earlier. Okay. And eventually we'll break out of this loop. So if we had no plus or minuses, we just had the term, we wouldn't even enter this while loop, so we could just return working expression. If we enter this loop a variable number of times, by the time we make it out, we've parsed all the pluses or minuses, and we have already left folded them into a binary tree. Recall that a binary tree means there's exactly 2 children for every node, or 0 if it's a numerical node. And so we can just return this working expression again. And so it's still weird though, because we have these calls to parse terms. We have not defined parse term yet. But it turns out, if we look at the grammar, parse expression and parse term are very similar. Just a few thing changes. Instead of plus or minus, we try match for multiplication and division. And instead of parsing terms as the children, we end up parsing factors as the children. So what I'll go ahead and do is I'll write the parse term body, but it's going to look very similar to what we just wrote earlier. So to parse a term, we know the very first thing is a factor. So I'll go ahead and make our working expression variable equal the parse factor we call. Then I need to check, we could have any number of multiplication or division signs follow, like any number of multiplications or divisions happening. So I would check while the next token in our input is either a multiplication or division. Then I would need to do the same thing where I capture the operator, which is a token, by calling the previous, because the match function skips past the token if it is a valid match. Then I would need to parse out a factor, because look at the grammar. For matching t, once you parse out the first factor, if you parse a multiplication or division sign, there has to be another factor that follows. And that itself is an expression. And the same way we left fold, we're going to have to fold left again. So each time we parse a new term, we make a new tree where the left-hand child is everything we've evaluated thus far. The root of the tree is a new multiplication or division node, and the right-hand side is whatever factor we just parsed out. Okay, so what I'll do then is we'll say the working expression is equal to a binary expression where the left child is the expression we built so far. The operation type, i.e. multiplication or division in this case, is stored in the operator token. And then the right-hand side is whatever factor we just parsed out. And once we make it out of this while loop, it means we have no more multiplication or division signs. So we've fully parsed out this term, and we can return whatever working expression we fully built up. And if I've done this correctly, which is a big assumption, then each of these parse expressions, parse terms, and parse factor methods works. What's interesting though, is they actually call each other. So let's go ahead and figure out the top level parse function, and we'll run through some examples to see what's happening. So the parse function that we expose, and I should actually make each of these inner parse term functions private. Because only we want to be able to call them. The only behavior we expose to the public is this overall parse method. And if we've done this correctly, all our top level parse method needs to do is take the starting term, which is a expression. Expression is our starting symbol, E, which it can get from calling parse expression. And then we built in this end of file token, so we should make sure at the very end of the file that there's no trailing, like not a stray 6 or something. After we've parsed an expression fully out, there should be nothing afterwards. It should just be the end of the file. And this is exactly why I added in this end of file type token. And so we can use the consume method to assert that there is just an end of file token. And once we do that, if we consume that correctly, that means we have a valid program, so we can just return the expression. Okay, so this is a lot. It's not that much code, as I mentioned. What, like 50 lines, possibly less? But there's a lot of complication happen because we have these functions calling each other, and then the functions also call themselves, which is really weird. So let's go ahead and first, let's see if this compiles. I'm sure I have a ton of compilation errors, so let's go ahead and see what they are. Okay, not as many as I thought. Very first one, line 41, prev, P-R-E-V, is not a valid function name. That's because it should be previous. So let's go ahead and fix this. Okay, that's good. Second issue is there's no such thing as open parentheses. Do I have a typo? Let's go ahead and check. Line 48. Open parentheses. Let me go ahead and check our token type. Open parent. Am I blind? It looks fine. Let me just copy over the word. And then paste it. Interesting. Oh, the issue is not that I spelled it wrong. The issue is that I need to say it's a token type dot open parentheses. It's part of that enumeration. Okay, the third thing was we're missing a return statement on line 51 of parser. Oh, that's very much true. Oh. And the reason is, if we make it here, okay, so this is a good example of something I missed. For parse factor, we know we either match an integer or an open parentheses followed by an expression followed by closed parentheses. If we can't match either of those things, then we are unable to parse a factor, which means the program input must be invalid, so we should just crash. Unable to parse a factor, expected a number or open parentheses. Cool. And now let's go ahead. Oh, one more issue. On line 48. Return parsed expression. Cool. Let's go ahead and run this. Okay, sweet. So this compiled and it ran our original program that just spits out the tokens. What we'd like to do now is actually have it parse the tokens and then spit out the expression. So let's go ahead, go to our main file. We print out all the tokens. We can still do that if we want. Let me go ahead and give a line separation. What we can now then do is then get the expression by creating instance of our parser, feeding it in the tokens, calling the top level parse method that we decided will be the public API that we let the caller call, and then we can actually print this expression term. And so we have 6 plus 4. So if this is correct, what I'd expect to get returned is a binary node whose left child is a number node and the value is a 6, an operator which is a token type of the plus sign, and a right child which is a numeric expression with a value of 4. Okay, so let's see what we get. We get a binary where the left is a number literal with a value 6. That looks correct. You see the operator is correctly a token with token type plus. That's correct. And the right side is a number literal where the value is 4. So that looks good. Let's go ahead and make it a little more complicated. Let's do multiplication in there. Times 8. So 6 times 4 plus 8. So we can think about this. We know that multiplication has higher precedence than addition. So we'd expect the top level to be a addition, because that would force multiplication further down the chain. We'd expect it to be an addition node, where the left child is a number literal of 6. The right child is itself a binary expression. The binary expression operator's multiplication. The left child is a number literal 4. The right child is a number literal 8. Okay, so this is a little bit messier to read. Let's go ahead. Oops. What we can do is just copy this into a file. Oh, that's awesome. All right, I'm not sure why it's giving me a hard time. What I can do is just run the program again, force the output to this file called temp, and let's go look at temp. Okay, this works. Okay, so now what we have is a binary operator. The left child's a literal number of 6. The operator is correctly parsed out as a plus. The right side is interesting because it's yet itself another binary expression now. So I'll fork that onto a new line. Or what we can do is like this, where the left child's number literal 4. The operator is a token type of star, meaning it's multiplication. The right child is a number literal of 8. And we can see that we correctly parsed in the recursive structure, and we can see that the multiplication is higher precedence, and that's being forced to lower into this tree. So that's pretty cool. So this apparently appears to be working, but I have not done any good job at convincing you how this is fully working. And it would be a fault of mine if I just said go read the code and figure it out for yourself. So what we can actually do is add some logging to our code to figure out what's happening. So what I'm going to do is I'm going to go back to our parser file, and I'm just going to make a variable called, we're going to add logging so we can trace behavior. And I want it to be able to something we can turn on and off. So I don't just want to add a bunch of print statements in case, many steps down the line, we're probably not going to care. Once we understand how the parser works, it doesn't really matter if we need to see the internal steps it takes to create this parse tree. So I will just gate that under a variable. Enable tracing. And we can just call it true for now. And so then I'll also make this function called log, and it'll take in a string. It'll take in a statement, which is a string. I'll name it statement, and it'll pretty much just only print it if we're enabling tracing. So if we enable tracing, then you can print the statement. Cool. So now what we can do is start adding some logging. So top level public parse function called, and then at the end, I guess we can also add the function name in. done parsing expression, verifying end of file exists. Okay, that looks good. Add some spacing here. Okay, now let's go ahead and add some logging. So we can say parse expression called. The first thing this is going to do is checking for, we'll start by parsing term. Okay, so parse expression. Afterwards, we'll say, okay, done parsing term, now checking for plus minus of a term. And so then if it enters here, we say found a previous, will parse term again. And then it's folds left. So then parse term, we can do the same thing. Parse term called. Let's figure out the exact. We'll start by calling parse factor, and then we can use the same exact wording we used over here. So I have to make this a parse term, and now you're checking for multiplication and division. Update the function in here for consistency. And sweet, the last thing we need to do is add logging for parse factor. Parse factor called log parse factor matched a previous will return literal. Case 2 is, oops, let me add the parentheses here just for consistency, is parse factor matched and open parentheses will parse expression now. It'll call parse expression, and then parse factor done. Oops, what did I just do there? Parse factor done parsing expression, checking for close parenthesis. Okay. Now we added a lot of logging statements. We have the logging on. Let's go ahead and run the same example we just looked at. Oops. I need some issue with my logging. Fun. Yes, I do need a... So I need to make the function call. So I need to use slightly different syntax here. Sorry about that. Call the function, and there's one other place where we do it. Okay, let's try run it now. Okay, we see a lot of logs being called now. What I'm gonna do is I'm gonna write this to a file so we can come through the file specifically. Okay, So let me also just, actually, yeah, we can just, let me also just get the expression that we used. 6 plus 4 times 8. Let me delete the tokens because we don't really care about those. Okay, oops. So our expression was 6 plus 4 times 8. Not sure why I spaced it like that. Let me not do that. Okay, so we can trace exactly what's happening now. So you could do this on your own, but walk through an example to make sure it's clear. I'll actually walk through 2 examples to make sure it's clear, because there's 2 different things we need to check. This checks our recursion. So, and it checks that we're doing order of operations correctly with precedence being baked in. So, what we're seeing is we start with this top level parse function called, and if I actually jump back, that top level parse function, she makes 2 logs. One at the very start when we first call it, and the other is after we're done parsing the expression. So, if I look here, I see this is the very first thing we get called. And if I look down here, I notice that it's actually the very last thing that gets printed as well. So that's interesting. Then we have this parse expression gets called, and that's what parse just calls parse expression. Parse expression says I'm going to start by parsing a term. Parsing term is going to say I'm going to start by parsing a factor. Parse a factor will then check, am I looking at a number or an open parentheses? We can see it matches the literal 6, so it returns a literal. And now we can see that bubbles back up to parsing term. So if I jump over here to our parser, parse term got this, it got that first numeric literal, and now it's going to check if there's multiplication or division that happens afterwards. Okay, it doesn't find anything. So then it finishes, and so we come back up. Parse term does not find a multiplication or division sign, so it just returns this working expression. The caller of that was right up here. And so now this is the working expression, it's just that number literal. And so then it's going to check for a plus or a minus. Recall, we just parsed out this 6. It should now match this plus sign. So we get here, checking for a plus or a minus. Then, of course, it's going to correctly find the plus sign. And so it knows that whatever follows a plus sign, according to context-free grammar, should be a term. So it's going to call parse term. And we see that's exactly what happened. And parse term gets called. It knows that the first thing that's in a term is going to be a factor. So it calls parse factor. And we expect, because we have 4 times 8, it should parse out the literal 4. That's exactly what happens. That returns out. So then parse term now has its term, or it has parsed out the factor. And now it's checking for multiplication or division. It should find a multiplication because we know we're looking at a 4 times 8. And so we see that's exactly what happens. It finds a star. And so on the right-hand side, it's going to parse a term because that's what we parse according to the grammar. If we have a multiplication, it's optional that we have a multiplication or division, but if we do, we have to have a term that follows it. And so then the term just calls parse factor to start. We've already seen this. That's going to parse out the number 8. There's no open parentheses. So then it's done. It returns the literal. And so then at that point, if I go back to our parse expression, we now have working expression. We get a working expression, and we fold it left up, and so now we have this working expression, which is actually just our entire expression. And so this parse expression returns to when it was called up here. The recursion's over now, and we then have we consume the end of file, and then we return to the main function. That's exactly what happens. Parsing's done. It verifies that the end of file token's there, and then it's done, and we end up getting our full output. This is cool. So this seems to make sense. Let's go ahead and change this to be an invalid token. So let's just say I had 6 plus nothing. Let's go ahead and see what happens. Oops. See, so we actually get an exception. So we can see there's an issue. Something's gone wrong here. It says unable to parse factor, expected a number or open parentheses. Let me just run this out here. Okay, so we can see that we start with parse. Where's my cursor? Parse always just starts by calling parse expression. Parse term will always start by just trying to parse out a factor. We know the factor is just going to be a 6 here because it matches the number literal. That's cool. So parse term's done. It's going to check then for multiplication or division. It's not going to find one, but that's fine because it's optional. Remember, there's an asterisk in the grammar, which means 0 or more. So there's just 0 multiplications or divisions in this case. So then you'll see that parse term is done and it returns. So then parse expression will now check for a plus or a minus. It's optional. It sees a plus or a minus. So it says it found the plus correctly. And now it knows what follows the plus sign must be another term. Parse term gets called, and it's going to start by trying to parse a factor. We know that a factor will check if the next token is either a number or an open parentheses. In our case, the next token is an end of file. There's no number or open parentheses that immediately follows. And so we get a exception in our code, and that comes from line 73 of the parser. If I hop to line 73, you can see that this happens in our parse factor function because it first checks if the next token is a number right here. It's not going to find that. Next token's end of file. Then it'll check if the next token's an open parentheses. It also won't find that because the next token is an end of file. And so it's not going to hit either of these if statements, and so we'll get to right here and we'll crash out. So we can see that's where things go wrong. Now, the third example I want to look at is left folding. So we saw that was something different. We saw that we might have multiple children of a node, and we used a while loop to keep left folding in our code. Let's go ahead and make sure that works. So if I do 1 plus 2 plus 3 plus 4. So before I even open this file, I had one plus 2 plus 3 plus 4. And that means all of these are the same precedence, which means we should execute from left to right. We know things that are deeper in the tree should get executed first. So 1 plus 2 should be the deepest thing in the tree. The result of that should then be added to 3. And the result of that whole thing should be added to 4. So the parse tree we're expecting, we should be able to see that plus 4, like 4, is the right child of the topmost node. And the topmost node must be a binary node of addition. Let's go ahead and take a look at debug to see that. This file that we wrote this into. Shoot. I accidentally appended. I'm going to get rid of debug because it has the stuff from the last example in there. Let me rerun this, delete the file so we're not appending to what we already had in that file. Okay, see a lot of logging, but let's go ahead and first spot check that things look right here. So we have a binary. The left argument is this whole other thing. We'll come back to that. The operator is a plus, and as I said, the right child should just be a number literal 4. Okay, but now let's look at this left child. We have the left child. Its left child is yet another binary operation. Let's go ahead and expand that out, and I'll just keep expanding this out. Something's wrong here. Oh, no, it's not. This matches this parenthesis right here. Okay, so we see in the top level expression, it's a binary. The operator is a plus. The right child's a 4. So we see that plus 4 is the very last thing that must happen because it's at the top of the tree. If we take look at the left side of the tree, we see that there's another binary expression, but the result of that is then plus with 3. That makes sense because that means the second to last operation that would happen would be the plus 3. And that's the second to last thing that appeared in our expression. And then if I look at the left child, it's itself a binary expression. Both the operands are number literals, and they're 1 and the 2. So the 1 plus 2. So this tree has parsed out correct structure. So nothing about that looks concerning to me. Let's go see what the code looks like. It's tracing. So we start with our parse. We call parse expression. Nothing surprising there. We know that every expression starts with a term. In our case, we know that there's no multiplication and division. So every term is just going to map to a factor, and that factor is just going to be a number. So the very first thing we parse out is we can see this number 1 gets parsed out. We return the literal. And then parse term is going to do this optional check for multiplication and division. It's not going to find anything. So the left-hand side is just a 1. So then now we bubble back up to our top-level parse expression. If I just need to trace what just happened in code, then what we just did was, to get the first number, we called parse term. And then now what we're going to do is we're going to keep checking for pluses or minuses. And we're going to see that this loops 3 times because we have 3 additions. So this log right here should appear 3 times. And I can see that by checking for will parse term again, because that's the string. We can see that it gets called 3 times, but let's go ahead and see what happens the first time. So it parses this 6, or this parses this 1, sorry. Then it's going to find that there's a plus sign, and so it's going to say, okay, we need to parse a term. That term's just going to parse to a factor, which is going to parse out the number 2, so that makes sense. Parse term has no multiplication division, so that just empty states. So then parse expression is going to hit that while loop again. And it's going to check, okay, we parsed another term. Let's check if there's a plus or minus again. And in our case, there is. And so it's going to say, okay, well, I found another plus or minus, so what must follow it is a term. That term's going to parse to a factor, and the factor is just going to parse to the number 3, which is what happens here. Then it's going to loop back again in that while loop. And one more time, it's going to check, hey, is there a plus or a minus? It finds a plus again. So then it's going to call parse term again, because we know a term must follow the plus or minus if there is a plus or minus. It's going to call the term to factor. The factor is just going to map to 4. And it's going to finish up. The recursion's over. Calls back to this top-level parse method, and we're done. And so the reason we get this correct structure where things are actually done is because of this very smart logic we have right here, where every time we get a plus or a minus and we parse the new term, we take whatever we already had thus far and make that the left child of a binary expression. And so that means that every time we encounter another plus term, that becomes the top level root of our node. And we read left to right of our input with our token parsing. Our lexer happened left to right. So as we find more and more additions and subtractions to the right, those will keep getting pushed to the top of the tree, and everything that already existed keeps getting pushed down via the left child. And that means that the very first things we ended up seeing and encountering end up very low on the parse tree on the left side, and the things that we find later on appear in the top right of the parse tree, which means those will be executed later when we actually go to evaluate the parse tree. Sweet. So there's one other thing we can do here to make our printing prettier. I'm going to turn off I'm going to turn off tracing for now. I'm going to remove this debug file. And if I run, the issue I'm seeing is like the binary expression that it prints out is like this mess, but it doesn't show the structure hierarchy. Versus when I was drawing on my iPad, it was really easy to follow things because they were very prettily drawn. What we can do, and you don't have to follow this part, this is not that actually that relevant, it's a good test of recursion. What we're going to do is just make a function that pretty prints this with indentation, so show the hierarchy. And so you might need to pause the video right here, honestly, because what we just covered is we just built out a full recursive descent parser, and I know recursion can be a tricky topic, so I would actually encourage you to go clone the repository, play around with some of the files, add more things, add more print statements, and make sure you understand the exact control flow. Because what we were kind of doing on my iPad is pretty identical to what we were doing here and what we're teaching the computer to do. Not really teaching it, we're forcing it to do. Just in a very well-specified way where we use no intuition, just straight rules and principles that the Kotlin language interpreter understands. So let me go back to this main file. Let's find a way to pretty print this tree. So what I'm going to do is let's make a function called pretty print. It's going to print some expression. So it needs to accept that expression as an input. And we're not going to draw like the left and right forking as a tree. We're just going to use new lines for every node, and the amount of indentation, kind of the way I did it when I was modifying the output directly, where more indentation means it's further along in the tree. So our indent will also be a parameter, and that will work. It'll start off as 0. So we'll pretty much need to, for each node, print the node out with the right amount of indentation, and then print out the children with even more indentation. So for indentation, I'll make a variable called padding, which is a string. We'll just use like we'll use 4 actually, screw it. We'll use 4 spaces as the indentation amount. And we'll repeat that by the number of times we should indent. So if we should indent once, it'll be 4 spaces. If we should indent twice, it'll be 8 spaces. And then we need to check what the expression type is. So if the expression, and this is Kotlin syntax, the expression is in a number literal, then to print it out, all we do is print out the padding, and then it's a number expression, so we can just print out the value. And then if the expression is binary, we have to print out a little bit more. We would print in, add our padding in, our indentation. We print out that we have a binary node. We print out that the operator oops, I had it right. I apologize. Sorry, my keyboard's just being weird. Expr.operator.type. And I need to close that quote. Okay. And then for binaries, we print out the operator type, and now we need to print out the children, but the children should be even more indented. So here's where we're going to use recursion again. This is another place where you can learn recursion. I'm literally going to call the same pretty print with the expression's left child. And I'm going to, instead of using the same indent, I'm going to add a level of indentation, which by this line right here will add 4 more spaces when we print out the child. And I'll do the same thing where I print out the right. And so now, rather than print out expression, I can just call pretty print with this expression. And our indentation starts off at 0. And now let's see what happens. I'll let you trace through things to see yourself, but Oops, there's an issue. Unresolved, line 10. Oh yeah, I used the wrong variable name. Should just be expression. Sweet. So now we can see that we have the tree-like structure. Instead of being vertically growing, it's horizontally growing. So we can kind of see that this is the top level operator is a binary, and the two children is a number 4, and then another binary operator. This binary operator has two children. One is a number 3, and another binary operator, which is a plus. This binary operator has two children, which are both numbers. So this looks correct. Let's go ahead and do one more complicated example just to make sure this fully works. And I like this one right here, so let's go ahead and roll with it. And then for debugging purposes, I'll also just print out the original string. Let me clear this. Cool. So I should expect that the deepest thing that happens first is this 4 times 2 is evaluated. If I look at the most indented thing, I can see that multiplication of 4 and 2 is done first. The next thing that happens should be this division of 5, and we see if I take a step out, that's exactly what happens to the result of this. And then we see the result of that is then added to 6. And this makes sense. We'd want the addition of 6 to happen before the subtraction of 3, because the plus and the minus are on the same precedence level, which means we should read left to right. So we still want to put things that appear first deeper in the tree. That's exactly what's happening with this plus being here and the minus being the top level. So this looks totally fine. So if you've made it this far in the video, you should be very accomplished because we've effectively covered the bulk of the complexity. And this is really impressive. I think that's the hardest part. Understanding the recursive descent parser is very tricky, and it might require you to pause this, maybe build this on your own, in your own programming language of choice if you've written code before to understand what's happening, or it might require you to do some research online to follow along. But if you've made it here, we are about like 90% of the complexity through the way of this video. So this is the most difficult part in my opinion. So kudos. And the next thing we need to do though is we've done 2 of the 3 steps. We have an input. The first thing we've done is chunked it up into tokens. The second thing we've done is generate this parse tree that has precedence baked in. The last thing we need to do is actually spit out code, because that's what a compiler does. Compiler takes an input, which is code expressed in one language, and it should compile it to code that's legitimate in another language. What we haven't specified is for what type of machine we're trying to write a compiler for. And so we're actually going to invent our own instruction set of a machine. So what I'm going to do is I'm going to swap back to my iPad, and we're going to invent our own virtual machine. It's going to be called a virtual machine. You could think of it, if you watched the last video, we saw that we built a physical hardware that implemented some very small instruction set. We're going to build our own instruction set for this compiler. We could make our compiler compile to the instruction set we built in the last video. We could make our compiler compile to the instruction sets that are used by my Mac, for example, and we could literally run the code directly. Turns out code generation can be very tricky depending on what language you are trying to use as your target language, i.e. what the output language of your compiler will be. So the language I'm going to invent is not fictitious, but it is going to have some very convenient aspects of it that will make code generation very easy. So let's go ahead and swap back to my iPad. Okay, so unfortunately, there's something wrong with my iPad and the stylus won't work. I'm hoping it's a temporary issue, but I let it charge for 20 minutes. I thought maybe just out of battery, but it still doesn't work at all. So I'm hoping that if I just leave it for a few hours or days, it'll magically start working again. The good news is that I could totally type everything I was going to draw. It'd just be easier to draw it. So we're totally fine to type here. So I'm just going to make a new directory. And let's talk about the machine. So at the start of the video, I previously said that this video that I'm working on right here is a direct continuation to the last video I made. Up until now, everything we've looked at has been pretty much independent of that video. we actually need to take a step back and discuss some of the things we looked at in the previous video. And what I also said at the start of the video is that if you hadn't watched the last video, that's totally fine. There's going to be no assumption that you watched that video all the way through because it's 12 hours. So what we're going to do is I'm going to explain, just at a high level, the computer we built up in the last video. And it's going to explain, it's going to matter because we need to eventually, the next step in what we're building out here is we need to take our abstract tree, our syntax tree that has mathematical operations encoded in it, and we want to spit out a series of instructions for some computer's actual instruction architecture, so that if we were to physically run this on that computer, it would get us the same result. It would get us the intended result of the mathematical expression, no matter how complex it is. So we saw in the computer we built in my previous video, there is RAM, memory, aka RAM, and there was also these things called registers. And so RAM held both instructions and data, and registers just held data. So pretty much what we built in that last video was, if you wanted to write a program, you would actually encode all of the different instructions in different positions in RAM. And so when you booted on the computer and started running it, the computer would take whatever value was at the first position in RAM, address 0, and it would treat it as an instruction based on some way of encoding the actual instruction into a number. And it would then know what to do by executing that instruction. That's the hardware we built. So we had different instructions that were supported by this computer. We had instructions for loading a value from RAM into a register. We had instructions for storing from register back into RAM. We had addition and subtraction instructions. And the last one that was interesting is we also had this out instruction that let us write a value to a display. So like we could actually interface with the real world and show, some value to a human who is just staring at the computer physically, or a physical implementation of that computer, which I showed that I had built. And so pretty much we had memory that stored instructions, and it could also store data, because we just saw that we could read and write to RAM. But then all of the actual data itself, when we want to do addition and subtraction, lived in these things called registers, which was independent of RAM, but they were very easy to access. We saw that if you wanted to look up something in RAM, you kind of had to take an address, go traverse RAM until you find the right address, and then spit that out, versus registers just exist, and there's instructions for working directly with those registers, and they're very fast to work with, as we saw in the implementation. You don't need to know that if you didn't watch the last video, but we pretty much grouped things into RAM and registers. And so if we wanted to add a number, what we need to do, if we wanted to say like A plus B, we'd have to put the values of A and B somewhere in RAM when we were programming the computer, and then we'd use instructions to load those values from RAM into registers, and then the actual add and subtract instructions operate on registers, not RAM. And so what we had in that computer over there, this is called a register-based computer. At least that's what I'll call it. Where everything was reading or writing to RAM, and then all arithmetic was happening in registers, but it ultimately get pushed back into RAM if you needed to save the result for anything. So pretty much RAM had both instructions and data, which was totally fine. We could totally have our compiler compile our instruction, our mathematical expressions, in the code that we're going to end up expanding that to include and support, to an instruction set like this. Turns out that's a little tricky to do for reasons that aren't apparent right now. It might sound like a mystery box. Like, how do you even take the tree we just have there and generate like adds and loads and stores that encode the same mathematical expression that we would have in an input? That sounds like a tricky problem. It is, but it turns out we're pretty close, and it's going to be like, this is like an aha moment for me when I learned this. I'm hoping that I'm doing a good enough job of explaining things such that you all can also have that aha moment. I think everything we've covered so far has been kind of we're all independent aha moments for me. Like, being able to take a mathy expression and build this tree is really cool to me. Using like this concept of recursion that we just were introduced to a few hours ago. So this is a register-based computer. This is not what we're going to compile our code to. For our project, we're going to be using what's called a stack-based computer. And so a stack you pretty much know what a stack is just by English. If you've programmed before, I'm sure you're already familiar with stacks, but I'm making no assumption that you had prior programming knowledge to this. And so a stack is quite literally just a pile of things on top of each other. So if you have a deck of cards, that's an example of a stack. Or if you're stacking books, that's an example of a stack. And so if we think about in the real world, if you have a large stack of something, the easiest things to do are adding something to the top of the stack. You just take something and put it on top. Or if you want to pull something off the stack, you can easily pull the top thing off the stack. And if our stack's really long, it's hard to pull out things that aren't at the very top. And it turns out in computing, a stack shares these same properties where you can very easily look at whatever's at the top of the stack, very easily add something to the top of the stack, and very easily remove something from the top of the stack. But we actually have no interest or support for doing things that are outside of that scope. So in our stack that we're going to work with here for this computer, you can't add something into the middle of the stack. If you have 10 items, you can push an 11th item on the top, or you can pop the 10th item. But you couldn't put something at the 4th position. Similarly, you couldn't remove something at position 5 if there's 50 things. So pretty much, we're always just going to have a list of things. In the real world, it could be a list of cards, or a stack of cards, or a stack of books, or just anything. Here, we're actually going to store, to start with, just a stack of numbers. And so the two operations we kind of have for working with the stack it's called pushing and popping. So push will put a new value on the top of the stack. Popping, if the stack is non-empty, it will take the top item off the stack. And so our hypothetical computer, there's no physical version of this computer. We'll come back to that later, but we're going to translate to this language. So we're inventing a programming language, and I'm also inventing a language for us to compile to that's at a lower level. It's more granular and less readable instructions, because it'll show how you take a high-level program that feels like English and translate it into something that's computer speak. And that was my ultimate goal for the video. So it's much easier to do this for a stack-based computer, and you'll see why not too long from now. Things will just feel like, oh, this kind of makes more sense. So let's talk about the instructions that are going to be available for our stack-based computer. So let me go ahead and clear out the stuff from the last video. That's all we're going to talk about from the last video. We showed that's what we built in the last video effectively, and we were focused more on the hardware side of the implementation. So the very first thing we're going to have support for is a instruction called pushInt, and it'll let you push. It has one argument. Instructions can have arguments. Same way like in high-level programming language, we saw that when you're calling a function, you can pass in parameters, arguments. Same is true for low-level instructions with the computer. PushInt pushes the arguments to the top of the stack, where the argument or the parameter is an integer literal. So let's say, in our hypothetical computer, instructions will all still live in RAM as well. So let's say that I had a program that was pushInt 5 and pushInt 3. So our stack will originally look like this. It'll be empty. And so after the first instruction in our code says pushInt 5. So it's going to put 5 to the top of the stack. There's one item on the stack. Our second instruction, pushInt 3, will push a 3 on top of that. So now we have 2 items on the stack. So that's the very first operation. Now let's say we want to add those. Well, that's what our next instruction is going to be. Add will pop the top 2 items from the stack, add them, and then push result back onto the stack. So add does not take any arguments, no parameters. So if I updated our program and it had push int 5, push int 3, and add, we know what happens after you push 5 and push 3. They just push them onto the stack. What this add instruction does, it's going to pop both of them off, the 3 and the 5, add them, the result is 8, and it's going to push that 8 back onto the stack. Okay. And then there's also going to be analogous versions for subtract, multiplication, and division. So I'm just going to copy this and paste it 3 more times. Sub will be for subtraction. We can say mul will be multiplication, and div can be for division. And I'll just update here. Okay, so now if I had a program that looked like this, first off, this would crash. Because we start with a 5 on the stack, then we push a 3 on the stack, then we pop both those off and put an 8 on the stack. And then when we get to this add instruction, it needs to have 2 items on the stack at least. There could be any number of items beyond 2, but it just needs at least 2. This right here would fail because there's only 1 item. So this would actually crash our computer. So this is invalid. So in our compiler, we're spitting, as we take a mathematical expression, these are the operations we're going to have to spit out. And we need to spit them out in such a way that the computer itself can evaluate them and not crash. So our compiler will need to be very correct in how we structure things. But let's say I want to do something more interesting, like let's say I wanted to do 3 plus 5 minus 4. So I could start with the 3 plus 5, which I already have. I add them. Then I could push in a 4 and call subtract. So if we trace through this program, what it looks like is we'd start with the 3 on the stack. Then we start with we push a 5 onto the stack. Then we push a 3 onto the stack. Then we'd add them, which becomes an 8 on the stack as the 1 item. And we would push a 4. And so the issue, if I subtract this, is it's going to pop the top 2 items, a 4 and an 8. 4 minus 8 is negative 4. And so it'd push a negative 4 onto the stack. But we know this is actually not the right outcome. We wanted to do 3 plus 5, which is 8 minus 4, but we've done 4. The way this program evaluates 4 minus 3 plus 5. So we correctly evaluated the 3 plus 5 first. There was no issue with that. But the issue is when you call the subtraction instruction, it's going to pop off the first 2 things. And if you have an A on the top of the stack and then a B after it, below it on the stack, it's going to do A minus B. The issue is by us pushing the 4 on the stack after we have the 8, that means we're going to end up doing 4 minus 8 because 4 is at the top of the stack. So in reality, this might look correct, but what we actually wanted to have done is have the 4 be on the stack before the 8 even got there. And that way, when we had done the 3 plus 5 and pushed the 8, the result of that, which is an 8, back onto the top of the stack, then the 4 would have just been below it, so we could have called subtract. So it turns out this is the right program because I said, well, let's walk through and see what happens actually. So we push a 4 onto the stack, then we push a 5 onto the stack, then we push a 3 onto the stack, then we call add, which is going to pop the 3 and the 5. The result of that's an 8, and so it's going to add an 8 to the top of the stack. Then we get to the subtract instruction. That's going to pop the two last things off the stack, the 8 and the 4. And then it's going to push the result of that, which is a 4, to the top of the stack. And so what's interesting here is that we push the 4 onto the stack very first, and then the 5 and the 3. And it turns out this is the only way to get the correct program. So even though we did the 5 plus 3 first, and we called the add before the subtract correctly, we actually had to have dealt with the 4 first before we could have known that was valid. Because the only way that we could have guaranteed that the result of 5 plus 3 ends up on the left-hand side is if it's on the top of the stack. So that's interesting. But I'd actually say that's a little confusing. And so it would be nice if we could have had the actual program we had before, where we pushed the 4, pushed the 5, then did the add, then pushed the 3, and did a subtraction. Or sorry, I have the numbers backwards, but let me undo that. It'd be nice if we could have done something closer to this. And so the good news is we totally can, because we can design this instruction set however we'd like. So there's a nuance here where for all of these instructions, if we pop the two things off, if the two things at the top of the stack, so if the stack has A and B, then stack base. So the A is on the top of the stack, B is the second thing on the stack. For addition and multiplication, if we pop these two things, it doesn't matter what order we treat them in, because both those instructions are commutative, i.e. A plus B is equal to B plus A. Similarly, A times B is equal to B times A. So it wouldn't really matter how we treat them. For subtraction and division, however, we saw this earlier with that when we were dealing with the precedence and parse trees, the ordering absolutely matters. So we wouldn't want to just assume anything. So we need to be very formal with how we specify things. And what we'll actually say is the first instruction that gets parsed, the first value on the stack that gets popped is the second operand. And the second value that gets popped is actually the first operand. So if we popped and did A minus B, then it'd actually be the second to top item minus the top item is what we end up pushing back onto the stack. So I'll make that clarification that this is A minus B. And then similarly, this is A divided by B. For these two, it's A plus B, which is just equal to if we had done B plus A. God, I love the car horns. Not sure if that captured on audio. Okay, so now, for this right here, this is actually the correct program. Because now we'd push a 5 and then push a 3. Those would be the two items on the stack. We'd pop them. We then replace that by pushing an 8 onto the stack. Then we push a 4 onto the stack. And since this item is effectively B, and this item is effectively A, then when we pop the two items, we do A minus B, which means 8 minus 4, and that gives us 4. And so we'd end up popping these, pushing the 4 onto the stack, and we're done. So that looks good. Now let's generalize what we just discussed. So we kind of see if we have a trivial 1 plus 2, then what we end up doing is we push the left operator. Or actually, let's start with subtraction because we saw that the order matters here. To evaluate this, we push the left operand, which is a 1. Then we push the right operand, which is a 2, and then we'd actually do the instruction sub. And so this would push 1 on the stack, then push a 2 on top of that, and then do the second to top item, which is the 1 because we pushed that first, minus the top item, which is the 2 because we pushed that second. So we kind of see that to do this, we're pushing. So I'm going to remark that we push the left operand to the stack, then push the right operand, then evaluate using one of the add, subtract, multiplication, or division instructions. So that's easy. We saw how this looks for a 3 plus 5 minus 4, but let's actually go ahead and take the parse tree and figure out how we kind of looked at that and eyeballed it, right? Let's look at what the parse tree would look like for this. So we know that the parse tree, this is going to be trickier to type, fine. Let's do it though. So the parse tree for this, we know that because of how we did the left folding earlier, we would end up with a minus sign on the top of the stack. Oh God, bear with me. Okay. the first child would be a plus sign because we do the 3 and the 5. The right child would be a 4. Okay, then the 2 operands to that are a 3 and a 5. Okay, so this is what the parse tree would look like. And so let's think about how we'd actually walk over this parse tree and spit out the correct instructions. So we kind of saw for this example right here that we pushed the left operand, then we pushed the right operand, then we pushed the actual operator instruction. We want to try to do that same approach here, but the issue becomes apparent pretty quickly. When we want to push the left operand, our left operand is not actually a number. It's actually in a result itself. And so it's a result, it's an expression itself. So we know that we actually want to push the value of this, we'd actually need to solve this subtree first, this smaller problem. So we'd actually evaluate that first, and then we could follow the same instructions. So we're going to start by trying to push this entire left tree on. So the left child is actually a tree itself. So to push the value, we could actually put out the instructions that would evaluate that entire left tree, because by the time we then walk through and the computer executes all those instructions, just the actual result of the arithmetic, which will be an 8, will be on the stack. So to push down the instructions for this, we know that for that left tree, we'd push out the 3. Then we push a 5. And then we do the add operation. And so this 3 instructions right here, after we evaluate them, we know we're going to have an 8 on the stack, but that means we've actually pushed effectively on the top of the stack, we have pushed the left argument of the overall minus sign. So then I've pushed the left operand. Now I need to push the right operand of that minus sign. The right operand is a 4. And then I need to push the operator, which we started with, which was the minus, which corresponds to the subtract instruction here. So what we're kind of seeing, and this is the exact same program we had earlier, what we pretty much see is that you want to evaluate get the right set of instructions, and to evaluate any operator, you have to get the value of the left child onto the stack, then get the value of the right child onto the stack, and then you actually perform the operation itself using one of the 4 instructions, whether that's add, subtract, multiplication, or division. And so if the operands are just numbers, then it's straightforward to just use the push in instruction to actually push the number itself directly onto the stack. If it's not a number, if it's actually a compound instruction, we can just focus on that sub-instruction, that subtree itself, and figure out what instructions we need to push to evaluate the left tree. So instead of saying that we push the left operand and then the right operand onto the stack, this is synonymous with saying we could omit the set of instructions that would get the evaluated left argument onto the stack, and then put out the set of instructions that would get the evaluated right argument onto the stack. For either of those arguments, if the value of what we're trying to get onto the stack is just a number, then we could just use the push in instruction. Otherwise, we have to spit out some instructions whose result, when evaluated, is whatever the evaluation of that smaller tree is. So what I'm saying here is, our claim is we'd omit the instructions, typo, that would evaluate the left operator, the left operand, the left-hand side of the tree, then omit the instructions that would evaluate the right-hand side of the tree, then omit the instruction associated with the operator itself, which is either an add, subtract, multiplication, or division. So that's the claim I'm making. We've seen it work in 2 examples. let's go ahead and look at one more complicated example. Rather than me typing the parse tree out, what we should do is let's just go, we have code that does this now. So if I jump back to our main file, sure, we can work with this complicated instruction right here, this 6 plus 4 times 2 divided by 5 minus 3. Let's go ahead and look at the tree it spits out here. Okay, so this is the parse tree. I'm just going to copy that over. Okay, so we start off with this top level minus. I'm saying that we need to start by omitting the instructions that would evaluate the left-hand side of the tree. This is the left side of the tree. So to figure out the instructions that would evaluate this tree, we do that same thing again. We'd figure out what instructions we need to spit out to evaluate the left-hand side of this subtree. The left-hand side of this subtree is just a 6, so that's straightforward. So I just push 6. Then the right-hand side of the tree is yet another tree, and so we jump another layer down and say, well, what's the instructions that would evaluate the left-hand side of this tree? The left side of the tree is yet itself more instructions. So this is the final subtree, which is the left-hand side of the parent tree. And so to evaluate this one, we need to look at its left operand. Finally, we see the left operand is just a number, which is number 4. So we can push that onto the stack. Then, for this tree, we need to evaluate the right-hand side, which is just a 2. So we push a 2 onto the stack. Then, we'd omit the instruction that is associated with the operator, which is the star, so it's a multiplication. So I'd hit a mole here. And so now these instructions, the 4, 2, and the mole, evaluate this. But this, recall, was just the left operator for this parent item. And so now, for that parent item, we've evaluated the left side. We've omitted the instructions that would evaluate the left side. We'll have to do the same thing for the right side now. So we visited the left side. Now we'll visit the right side. The right side argument is just the number 5. So that's easy to go ahead and push a 5 onto the stack. And so now we've put onto the stack the operations that would spit out the values for the left argument and the right argument. So the last thing we need to do is put out the operation for the instruction itself, which is a slash. So that's a division. And so now we've put out the instructions that would get us this. Now, that was visiting the right-hand side of this parent node. So for this binary plus, we visited the left side, which was pushing the 6 on the stack. That's the very first thing we did. Now we visited the right-hand side. Now we need to go ahead and do the plus. We need to visit the operator itself, which is just an addition sign. So we'd spit out an add. And so now we spit out the instructions that would do this and evaluate this entire subtree. And so recall that this entire thing that I have highlighted was the left argument to the topmost item in our tree, which was the original minus sign. So we visited now the entire left-hand tree, and now we're going to visit the right-hand side of the tree, which is just the number 3. We see that right here. And so to visit that, all I have to do is push a 3 onto the stack. And then the very last thing I need to do, now that I've pushed the arguments that would emit both the left value and the right value, i.e. both the operands values would be, after we execute all these instructions, we have 2 items on the stack, which would be the left number and the right number. So the very last thing we need to do is visit the operator itself and spit out this minus sign. And so my claim is that these operations right here is the correct instructions we would need to spit out to evaluate that mathematical expression that we saw in the main file.
What we can kind of do to verify this, there's one route. We could just simulate execution here. I'm already confident that this will get us the right answer, so I'm not going to do that. But what we can kind of see is we know that for each of the multiplications, divisions, additions, subtractions, they operate on the last two things that were put onto the stack before them. So if I start skipping through these pushes, I get to the first operation that would happen, which is a multiplication. And so I would then see, I can easily see that the two things that would be multiplying are the top two things, the last two things that were pushed onto the stack. So this would end up evaluating to the 4 times 2 first. And so we actually see that the very first thing that happens is that multiplication. And that's actually consistent with our expectations, because according to the precedence baked into the syntax tree, this is the deepest part of the tree. This is the most indented part here, which means this has the most urgent precedence, and it has been pushed to the bottom of the tree. And so we can correctly see that the code we spit out here is respecting the order of operations by doing that multiplication very first. We can kind of see after that, the next thing it does is division, and that's also kind of consistent with what we see, because that's the next deepest thing, is this division right here. And that's consistent with us we're seeing that we're evaluating the multiplication and the division before the addition and subtraction. So yeah, you could actually walk through this and simulate execution. I know I said I wouldn't, but I should just do it for being thorough here to make sure the idea is in your head. So let's read through and figure out how we'd evaluate this program. So if we were the computer, here's what the computer would do. It'd see the push 6 instruction, so it'd push a 6 onto the stack. It'd see the push 4, so it'd push a 4 onto the stack. It'd see a push int 2, so it'd push a 2 onto the stack. Then it'd see a multiplication, so it'd pop the 2 and the 4 and multiply them to get 8. And then it would push the resulting 8 back onto the stack. Then it would see a division sign, it'd push a 5. I skipped the push 5 instruction. Then we'd see a division sign. And so then we pop the two top things off the stack, the 8 and the 5. We divide them. Let's just say 8 divided by 5. What does it return? 8 divided by 5 is 1.6. 1.6, I should use whole numbers to make this easier, but it pushed the 1.6 to the top of the stack. Then it would add the 2 items on the top of the stack. So it'd pop 6 and 1.6 to get, and then push the result 7.6 onto the stack. Then it would push a 3 onto the stack, and the very last thing it'd do is it'd subtract. So it'd pop these 2 items off the stack, and so we'd have 7.6 minus 3, which would get you a 4.6, and it'd push the 4.6 to the top of the stack. And that is the correct result here. So it seems like I will leave this as an exercise to you to verify this. You can keep doing more examples, but my claim here is actually the correct approach we're going to take. To spit out the code, you would start with the top item in the tree, in the parse tree that we are now familiar with and built out. You would spit out all the instructions needed, such that when all those instructions are evaluated, you are left with the left operand on the stack. Then you would do the same for the right tree, the right operand, and then you would push the instruction itself. And so we kind of see very consistently that the top thing that we have on the stack, or the last thing we actually end up doing on this in this evaluation of this mathematical expression should be a -3, because that is at the top of the parse tree, meaning it has the least urgency, because recall we evaluate these trees bottom up. So that's the very last thing we do. And that kind of is consistent with the fact that the last instructions we do is pushing a 3 on the stack and then doing the subtraction. So we kind of see that the very last thing we're doing by peeking at the final source code that we emit is a -3. Similarly, we saw that the very first thing we did was the multiplication, the 4 times 2. That's consistent with the fact that it's the deepest thing down here. So if it's a little fuzzy to wrap your head around this, that makes total sense. We're really exploding this idea of recursion. Like, we had this recursive property where, like, to evaluate something, we might need to evaluate a whole nother tree. So, like, to evaluate the left child, it might not just be a number. with complicated expressions, it's not going to be a number. It could actually be a whole other tree itself. So it's weird to think about visiting a child tree and then having to come back up and visit the other side of the tree. But I would encourage you to play around with a few examples. And so what we can do now, I'll let you pause it if you need some clarification. What we're actually going to do now is, now that we've taken our input, chopped up into tokens, and then derived the tree out of these tokens, what we'd like to do is go ahead and traverse that tree and spit out all the instructions that would be needed to generate the machine code for this language that we're compiling to. This is the stack-based language that our compiler will translate our high-level language code to. So let's go ahead and actually do that. I'm going to save this. The other thing I'm going to do is, let's make a commit of everything we have here. Made some modifications. We can add our notes in, and then we can add all the changes we made in the source file. Oops. Don't want to compile. I don't want to include the final compiled program. So I could Cool. So now we've frozen our code at this point in time. So if you want to use that as your reference point to play around with some more examples or anything we just discussed, now's the time to do that. Now let's go ahead and clear this, and let's start thinking about how we'd actually approach this. So, like we did before, we're going to have to define a new data representation for actually the instructions that we're going to spit out. And so it'll be straightforward. And I think you'll actually find that, similar to the parser, there's actually not that much code to write here. We use recursion. We're going to use recursion to visit and walk over the tree, the same way we use recursion to take the input tokens and build the tree. So I know if you're hating me for recursion, this is the last of the recursion, and if you can understand this, then there's everything else we're adding for the most part is more recursion or expanding upon the recursion, but not in any fundamentally new way. So what we're going to go ahead and do is need to define the instructions that our compiler will spit out. So now our compiler is going to take in a program, which is just code, text. For now, it's just a mathematical expression. And it's now going to spit out final instructions for our stack-based computer that we invented. And we'll also then have a way shortly after to actually evaluate the code it spits out, so we can make sure everything works correctly. So I'm going to define this new class. Instruction, and this will represent the instructions that are supported by our computer our hypothetical computer. It's called a virtual machine. Our hypothetical computer that we're compiling code to. So instruction, we saw that the very first type of instruction, each of the instruction types will just be a class, that is subclass's instruction, was this push int, and this one has an operand, has a parameter, an argument, and the value in that parameter is what value we're pushing onto the stack. And so this itself is a type of instruction. Then we had addition, subtraction, multiplication, division, and that's all. Those don't have any operands. The instructions themselves encode all the behavior that is needed to know what to do, because recall, the add is not saying, hey, you should add these two numbers that are specified by arguments. It's saying, hey, go look at the stack, see what the top two things are, and add those. So we have an add instruction, a subtract, which we'll just call sub, a multiplication instruction, which we'll just call mul, and then we had our division instruction called div. Cool. So this represents, our compiler will create a bunch of instances of these, and in a list, we'll spit out instances of instructions. So I actually need to go ahead and make the compiler now. So I'm going to make a new class called compiler. And so our class compiler is going to expose one public method called compile, because that's what a compiler does at the end of the day. It takes code and compiles it. Or to compile something means to translate it from one language, a source language, to a target language. It's going to take in an expression, and it's going to return a list of these instructions, i.e. this new class type we just defined in the previous file. And also recall, we just take one instance of an expression, and because an expression has children, that one expression actually encodes the entire tree of operations we need to do. So we just, when we call this function, we'll hand it the top level node, i.e. the highest point of the tree, which is just the entire tree, and so then it'll walk down the tree to figure out what to do. And so if we're going to return a list of instructions, we need to start by creating that list. So we'll create a value instructions, which will be a mutable list, because we're going to have to keep adding instructions to it as we walk over the tree. And it's just going to be an empty list for now. So we can just use this Kotlin function mutable list of. Then what we're going to do is we need to start walking over the tree. So I'm going to make this new function called emit. It's going to be private. We only want it to be called from here. That will visit the current node and then figure out what instructions it needs to emit to the what instructions it needs to add to this instructions variable. So it's going to take in an expression, and it's going to take in this instructions parameter, this mutable list of instruction, because this is where it's going to have to add the instructions to it. So pretty much our expression, as we saw in the, and I can actually just jump to the file. Our expressions are one of two types. They're either number literals or they're binaries. So we just need to handle the two cases. There are two different cases. We need to treat them differently. So when our expression is a number literal, then it's actually super straightforward. We know that all we need to do to visit that item is just push its value onto the stack. So I'll just add to our list of instructions an instance of this push int instruction that we just defined in the other class. The value will just be in the field of the expression node itself. The trickier case is if we have a binary expression. And so when we have a binary expression, we know that we need to emit the instructions for the left tree first, its left child, then emit the instructions for the right child, and then push on the operator. So here's where we're going to use recursion. And so to visit the left tree, we're just going to call this emit function again. So we're going to emit, not for the same expression, we're going to emit the instructions that would generate the left argument to this binary expression. And we're going to pass in the same instructions parameter so it can add to this global list we're keeping track of. Then it'll need to visit the right argument. And so it'll call this emit function on the right tree. And so this is where it's going to use recursion under the hood. And the last thing it needs to do is actually add whatever the instruction is. Like if we haven't, if the binary expression is an addition, we need to omit the addition instruction. So the last thing we'll do is we can create a, and this is a little bit of a trickier thing. So I'll actually pull this out into a separate function. Why don't we do that? We'll make a private function called instruction for operator. It'll take in the operator, which is a token stored in the expression field, and it'll return just the correct instruction for that operator. So it'll look at the operator's type. If the type of the token is a plus, then we should return an add instruction. If the token type was a minus, then we should return a subtract instruction. And we'll do the same thing for multiplication and division. So star was the token that corresponds to multiplication. And slash returns this div. And so if we have any other type of token type, it's not valid. So we'll just say else. We can just crash the program. Invalid operator. And we can just print out whatever the operator, or whatever we expected the operator to be but got instead. Cool. So now we visit the left tree, we visit the right tree, and then we need to spit out the instruction for the operator. So I'll literally just call instructions.add, and we'll just get whatever the instruction for the operator was. And we can get that token by just looking at the expression itself, because it's encoded in the binary expression. Okay, so this is it. So now in our top level compile function, all we need to do is just emit the instructions for the top of the tree. It'll call this emit function, and the emit function will keep calling itself recursively. So we'll just pass in these two things: the top level instruction, the top level expression, sorry, and then the instructions variable that'll track things in, and then we'll return just the instructions when all is said and done. Okay, so we're gonna come back and add some logging, but let's go ahead and update our main file so that we actually call this compiler once we have our syntax tree. Okay, let's jump back to an easier 1 + 2 + 3 + 4. So first thing we do is we take the lexer of the input and get a list of tokens. We print out the tokens. I'll go ahead and comment that out because it might be noisy. Move this around. Then we take the tokens, create an instance of the parser, feed it the tokens, figure out what the tree is, and we'll print that out. We can keep that. Now we'll actually compile it. So now we'll walk over this tree and emit the instructions that, when evaluated, would give us the final result of this mathematical expression. So I would get a set of instructions, which would be a list of instructions. And we get this by creating an instance of the compiler, and then telling it to compile the expression that we got from right above. And so once we do that, we get a list of all the instructions. We can just go ahead and print them out. So instructions, for each instruction, just go ahead and take the instruction, which is a type of instruction, and print it out. One per line. Alrighty, let's go ahead and see if this compiles. I bet we have some issues somewhere. Wow, I'm very surprised. Okay, I thought we'd totally have some compilation issue. None at all. So we see that we get expressions. This is not we get some instructions coming out, but this is not the instructions for 1 + 2 + 3 + 4. So clearly something's off. There is a compilation error. I see. So basically what happened is my script for run will compile the code and then execute the file. In this case, the compile failed, but it had the same file from the last time I did successfully compile the code, so it ran that. So there is a compiler issue. On line 28, there is no such thing as an instruction div. And, oh, that's because of capitalization. That's on line 28 of the compiler. So not capital div, but lowercase div. Cool. Now let's try run this again. Okay. Much less chaotic to look at. Okay. So now we can see that our compiler is spitting out these instructions. So it's saying push 1 onto the stack, then push 2 onto the stack, add them. We know that the result of that is 3, and that's correct because the first thing we would want to do is add 1 and 2. Then it pushes the value of 3 on the stack and adds again. That also looks correct, so we know plus 3 is the next operation that should happen. And then it takes the result of that, pushes 4 onto the stack, and then adds those 2 things together. And so that actually looks like it's the correct program. So what I'd like to do, because I introduced a lot of complex recursion, and I know it's hard to explain, and it like kind of requires you to like trace through code a few times to be able to make sense of things. Let's go ahead and add some comments to our compiler file so we can kind of see when this emit thing calls itself. So I'll make a new parameter this class should log, and we'll default it to true. And so then I'll have the same exact setup that we had from the parser, where we have this log function. So I'll literally just copy that over, and it's just gonna check if we should log, then print it out. Otherwise, do nothing with it. Okay, so let's just add some log statements here. Top level compile function called. Okay, so then emit. Emit called with number literal or we could say emit called with binary expression, and we can try just print out that expression. And so then we could say recursing on the left side, and then we could say recursing on the right side. Okay, and then we can do one more statement for when we put out the operator. Now adding binary operator, we can just call the same function again. It doesn't really matter. We're gonna waste the result for just, or we're just gonna call it again, but it's not. There's no damage in calling it multiple times for logging. Cool. So let's go ahead, jump back to main. I want to add some. Let me turn off the debugging from the parser. So let me actually make that a parameter to the parser. So I'm gonna say the parser can, in the class, can have its parameter should log, and we're just gonna call it false. So if I come back to the parser, private val should log, that'll be a boolean, we'll require it there. So I can get rid of this enable tracing. Cool. So that should turn off the noise from our parser, because we know how that works now. And we can still print the expression, or the syntax tree. Let's just add, oops, what did I do wrong? Oh, let's just add one more line to split it out. Separate the tree itself from the instructions that we emit from the compiler. Cool. Let's run this. And ooh, many compilation errors. What did I do here? I must have broken something. Only expressions are allowed here. Okay, something's wrong on line 20. Alright, I actually cut the video, but I just wanted to take a look at the bugs on the... There are so many compilation errors, I just wanted to take a look at them independently. But it turns out there's only one issue, which is val should have been value, so I had a typo in the field name. And if I do that, it fixes all the other issues. Alrighty, so we see we're looking at 1 plus 2 plus 3 plus 4. That's the correct parse tree, because we see the 1 and the 2 are the deepest, so they just get evaluated first, then the 3, then the 4. We see that we get some instructions. These are the correct instructions. You can see that we're doing the pushing the 1 and the 2 and adding those first, which makes sense. It's consistent with the fact that this is deepest in the tree. So let's trace through some of the logs we have. So we see this top level compile function getting called. Then we're seeing that this top level function just calls emit with the binary expression, and it's not pretty printed, but you can kind of see that this is the entire expression. So we see that it's doing a 1 and a 2, and it's got a 3 and a 4 in there. So that's our entire expression. So the first thing is to do is evaluate the left side of the tree. And so we can see emit gets called again, and this has the entire left side of the tree. So this has the 1 plus 2 plus 3. Up here, that corresponds to this. And notice how that entire thing is the left argument of the topmost operator, the topmost addition operator. And so this got the 1 plus 2 plus 3 in it. It has to evaluate its left side. So we can see that it calls emit again. And this time, the left child is just a binary plus of 1 plus 2. And so this is yet another compound expression, so it has to look at the left child. So it's going to call emit again on the left side. And we see that eventually the left side of this expression is just the number 1. So it's saying it's going to emit called with the number literal 1. So it's just going to emit the push int for 1. Then it's going to recurse on the right side. So this call to emit has just done it's recursed on the left side. Now this call is going to recurse on the right side. The right side we know is just the number literal 2. And so we see that it's getting number literal 2. So then this instance of the emit call has now visited the left child and the right child. So it has to print the operator. The operator is a plus. And so we see it's saying it's now adding a binary operator of add. Cool. So then the next thing we see is we see recursing on the right side. But to which instance of the emit does that belong? If you trace it out, you'll see it belongs to this one right here. So the right side of this one is just a number literal 2. Oopsies. And so we see that it just prints out a number literal 2. And then the operator, now that it's visited both sides, it needs to spit out the operator add. Let me just make sure I'm speaking that correctly. 1, we just spit out a 3. Yeah, so we visit the right child. And we need to do, oh yes, the operator for this is an add. So then after we spit out the 3, so we visit the right child, we spit out the operator itself. And then finally we see that there's now a recursing on the right side happening. And that corresponds to this emit up here, where the right side is just a number literal 4. So we emit a number literal 4. We see that correctly gets called. And then we lastly, visiting this top level emit, need to spit out the operator, which is a plus. And we see the instruction add happening. So we see the function calling itself, so it gets a little interesting. One thing that was a little unclear in my explanation though was when we see this like emits being called, or like now we see it recursing on the right side, recursing on the left side. It's unclear from which parent call of emit this comes from. So I'm gonna add one more thing where every time we call emit, we'll have some unique number and we'll include that with our log. So that way when you see recursing on the right side, it'll spit out some ID as well. And you can see from which parent call of emit had the same ID. So that's just for helping making debugging, making the understanding of part of this go better for you if you want to pull this on the side. So every time we call emit, I'm going to make a new private variable saying next unique number. We can start this off at 1. Doesn't really matter where we start it. It's a type of an int. So every time we call this emit function, let's get that number for this instance of the function call. So we'll say unique ID, or we'll just say log ID. And that's an int is 1, or is equal to next unique number, sorry. Not 1. And then we'll need to increment next unique number. And so now every time we log here, we can say emit call with literal, and I'll preface with the log ID. Okay, cool. So now I'm going to go ahead and compile that, and hopefully it makes the debugging a little bit easier for you to understand. So now we can see, wow, we have 7 different calls to this emit function. And so this one right here starts by recursing on the left side. Recall the left side is this entire complicated subtree right here. So the next time we emit from the instance of that emit function is going to be at the very end. So all of this right here is us evaluating the left side of the tree, visiting the left side of the tree. And we have 6 more recursive calls to emit that happen as part of that. And once all of that's done, we get back to the very first invocation of the emit function. And now it's going to say this number 1 is now going to look at the right side. And it's going to call emit one more time. And that right side is just a number 4. And so then it's now visited both the right side and the left side. So the number 1 is going to spell out the binary operator for addition. And I can pick one more just for example, where this number 2 right here, corresponds to another unique emit call. It's going to look at its left side, and its left side is this binary +1 +2. And so its left side, it's going to call emit again. So yeah, this is visiting. Oops, sorry, that is not corresponding. This is the number 3 is what corresponds to the +1 +2, and so you can see the number 3 recurse on its left side. It's easy recursion because it's just number 1. Then number 3 recurses on its right side. It's also easy recursion just because it's number 2, and then number 3 spits out its operator. So hopefully this is useful enough for you to debug. For now, I'm going to turn this logging off, just because I think it's kind of noisy. And the compiler file should log. I'm just going to, or I guess we'll keep it true. It can default to true, but in our main function, we'll just specify that we don't want it to log. Should log equals false. Okay. Let's run this one more time. Okay, so this is really cool what we just got to. We now have the ability to take an input and spit out all the instructions for a program such that if we ran these set of instructions on our computer that has this instruction set architecture, it should evaluate the right result. And so what I'm saying here is if I evaluate all these operations, I should see 4 + 3 + 2 is +1 is 10. I should see just a 10 on the stack afterwards. And this is really, really cool. So we have officially built a compiler. We are, like 5 hours into this? we now actually have a program that takes in something from one language, a high-level language, which is the one that we're familiar with. That's how we evaluate, this is how we specify mathematical operations. And it now spits out the equivalent set of instructions that would make evaluating those instructions get you the final result. And we know that computers, if we had a computer that existed that physically implemented the instruction set we just defined, where we have a push in, add, subtract, multiplication, and divide, it would be able to do it really quickly. And so you can actually think of what we just built as a glorified calculator. But I'm claiming that these instructions are the right instructions. What we'd actually like to do is build a program that can simulate instructions, simulate execution of these instructions, so that we can actually verify that we do get the right result if we evaluate these instructions. Because right now it's like we see a lot of instructions, we can't really tell if it's correct. But I think before we do that, let's just look at one more complicated example. Like, I think what's not remarkable about 1 plus 2 plus 3 plus 4 is that you could have easily just reasoned through these being the instructions that you need to specify for the machine. If we give it a really complicated expression, something like this, you cannot easily, you can, it just takes you like a few minutes probably, figure out what instructions you need to omit in a program to evaluate this mathematical expression so that it'd be equivalent. But if I just compile it, look how much faster it can do it. So this is where you see we just have computers becoming significantly faster than humans when we specify things in a deterministic, consistent way. So what I'm going to do is I'm going to pause the video now, and I'm actually going to go build something that'll execute all these instructions and make sure and spit out the final result. So let me go ahead and do that. And we're not going to concern ourselves about it. This is just going to be an interpreter for this language we've invented that we're compiling to. I'm actually not going to show the implementation because I don't want you to get confused as to why we're doing this or like how any of that works. You should just know that like these are the instructions. If we had some computer that physically existed, we looked at in my last video a physical computer and punched these instructions into the computer's RAM, then we could just actually run the program and see what the final result is. We don't have a physical computer that implements this instruction set, nor would I want to go through the hassle for every single program to take these instructions and punch it into RAM on my computer. So instead, I'm just going to write another program that simulates what that computer looks like. And I know that also probably sounds a little meta, like we used one language to build a compiler into another language that's not it's a language we invented, and now we're building a program in a different programming language that evaluates the instructions for this fictitious language we made and compiled our program to. Yeah, there's a lot of confusion. We'll actually come later in the video, once we finished our programming language, talk about some of these things that are fuzzy in the brain, like why do we do it like this? So let me go ahead and pause the video and take care of that. Ooh, and before I pause the video, let's actually commit what we have right here. Cool. So now, we have a few different commits here. Or if I clear it and git log, we have a few different commits. We have a commit from when we started the Lexer, then we finished the Lexer, then when we finished the parser, and now we have code generation. So we actually have a full compiler now. This is really cool. You should be very accomplished if you made it this far in the video. I'm not sure if anyone will make it this far in the video, but if you did make it here, you should be proud of yourself if you understand the bulk of the theory behind what we're doing here. Because this is actually how real compilers work. Okay, so what I've done, if I show the current directory structure, I've added this new file called machine.
And so the issue right now is that we have our compiler and it spits out all these instructions for this new computer we designed. The issue is I don't have a physical computer that implements that instruction set at the physical level. It's out of the scope for this video. So because I don't have a computer that actually implements this instruction set, we just use this file, which is software, to simulate it. So this file will pretend as if it's a computer. It'll look at all of the instructions and tell you what the result would be if a real computer that abided by our instruction set architecture were to execute that program. And so I'm intentionally not going to show the source of it because I don't want to get lost in that specifics. But what I have done, is committed that file with the changes. So if you want to pull this at this point and play around locally, feel free to do that, and you can use that to verify your program's work. So if I run what I have, then we'll now see we get the syntax tree. We can see all the instructions that it spits out. Oh, I also made a small change. You might have noticed earlier that the add, subtracts, multiplications, and divides in this list of instructions had some gibberish after them. That was actually because by default, the Kotlin Programming Language will print the address of where those objects live in my computer's memory. We don't really care about that. We don't care where it lives. We just care that it's an add. So I changed some of the formatting there so it prints prettier and just shows the actual name of the class. But back to my point, after that, we now see what the final stack would look like after we evaluate things. So right now, our language doesn't have any way of printing or anything. We just have a way to evaluate an expression on the stack. So I chose to make this machine just print out whatever the stack is after the program's done running. And if we've done everything correctly, we should expect one value on the stack because we're only pushing and popping things to perform the arithmetic expression that's passed in. And that one thing should just be the final result. So I can see for this example of 1, 2, 3, 4, we know that should sum to 10, and our final stack says that sums to 10. So that looks cool. Let's try, I also, have a more complicated expression. So something like this uses parentheses, multiplication, division, and subtraction, longer expression. Something that if you wanted to execute this if you wanted to evaluate this by hand, take a little bit. If you wanted to try write the machine code for that our compiler spits out, that'd take a lot longer. But our compiler, we'll see, does it very fast. And that looks correct. So I guess at a high level, if I were to evaluate this, I'd say 10 divided by 2 is 5, plus 4 is 9, times 2 is 18. I hold the 18, 6 times 3 is 18, so I have 18 minus 18 on the right tail, which is 0. So I have a 0 plus 8 working from right to left. So I see 8 as my final result. That looks good. So you can see this is much faster than we could do it. And it's cool that we actually have a interpreter that spits things out. And I know I just said it a minute ago, but I don't think I could overstate how impressive what we've accomplished so far is. We have taken advantage of some of the more complicated aspects of a high-level programming language like Kotlin, i.e. recursion, and some of the class structuring, and leverage that to write in several hundred lines of code a true compiler. We are able to take something that is English to us and translate it into a set of instructions that are so low level that we can build computers that can execute those instructions by moving electricity around. And that's what you would learn if you watched my previous video. So you kind of see, like, even in our compiler, we've had layers of abstraction where we have the input token, the input text, and then token sitting on top of that, then a parse tree on top of that, and then code generation on top of that. Below all of that, there's still a computer that has to execute the code. And so that's what the previous video was. And you can kind of see, like, these layers of abstraction just keep stacking on each other. And if I get around to making more videos, which I would obviously love to do, we'll just see the abstraction layers get higher and higher. But the higher up you go, the more interesting things you can effectively make a computer do. But at the end of the day, no matter how high up you go, everything a computer goes through has to get compiled and ends up as these very atomic and granular computer understandable instructions. So this is really cool. You should be proud of it. I am proud that I made it 5.5 hours in so far. And let's talk about what we'd like to do next. So I said at the start of this video we're going to invent a programming language, and we kind of haven't really done that.
all we can do right now is evaluate mathematical expressions. Technically, that's a language in itself. But what I'd like to do now is add some features to our language that makes it feel like some of the more modern programming languages you may have worked with, or if you've not coded before, to show you some of the conveniences that modern programming languages have. So I'd like to take our math equation solver into something that can actually run programs and implement algorithms in the real world. So the very first thing I did when I gave you an overview of the Kotlin programming language was to show you, I showed you printing, which we'll get there, but I showed you the ability to store variables and use variables. So we saw that you could say like a variable named x is equal to the result of some mathematical expression, and then you could have another expression after that which uses the result, or uses that referenced variable that we just defined above. So what we're gonna do is add support for that to our programming language. Turns out we actually don't really have to make, maybe we make one new file, trivially so, but we don't really have to make anything new. We're just gonna update each of the stages of what we just built: the lexer, the parser, and the code generation, the compiler part. So we know that our language that we worked with started with the context-free grammar. Let's jump back to that and see where the context-free grammar would take us. Like, what would we need to change, add to our context-free grammar to add support for what we want to do here? So I had the syntax tree somewhere. Okay, yeah. This is our abstract syntax tree. So what we'd like to be able to do right now, you can just right now our program just takes in, like, our compiler just takes in a single expression. We'd actually have to change that. So we'd like to add support for two new things. The first would be defining a variable. So right now, if you type in an expression, we evaluate it, throw it away, or I guess we print it out and the program's done. We're now going to be able to do multiple things in a program. So we would like people to be able to define variables. So how that might look like in code is we could say, like, let some variable, I'll call it x, equal 1 plus 2 plus 3, something like that. And we know how to evaluate that right-hand side. That's just an expression. Conversely, in the expressions we already know how to evaluate, we might want to do 1 plus 2 times x. So we'd like to be able to reference variables as well. So now our programming language is going to go from not just a single mathematical expression, but a list of statements, where a statement can either just be an expression itself, or it can be a variable declaration statement. And then we also need to change it such that within an expression, i.e. the grammar we have right above this, you can reference variables. Right now, at the most granular level, the only non-terminals, or the only terminals aside from the operators themselves in parentheses, are integers. We'd also like variable names to be part of that. So let's see how we can update our grammar. We're going to say that the syntax for defining a variable is the word let followed by some name of the variable. And we'll just say, for the sake of our compiler, the variable name is just all letters. Like, we're not going to deal with other characters like underscores or dashes, which if you've worked with other programming languages, those have support for. Ours is just going to be like whatever the word is, whatever the word following the word let is. We're going to treat that as the variable name. There will be no special characters or numbers allowed in it. Then there will be an equal sign. And then after the equal sign, there's just an expression. And that's the expression we already have defined up here. We just want some mathematical expression. So we could say something like a statement is equal to the literal word let followed by some identifier. We'll find the rule for identifier in a second. Followed by a literal equal sign. Followed by an expression. And while I have this, we've been saying ET and F up here. We can just go ahead and rename these as what they are. Okay, and so then I also said, what is an identifier? We said an identifier is just going to be, we said it was all going to be text. So no special characters, just letters in the alphabet, A through Z, and any at least one of those. A variable name has to be at least one letter long, but we'll say it can be as long as the user wants it to be, whoever's programming this. So we're gonna say A through Z, so just any character, and then followed by any variable amount of letters. So you have to have at least one, because remember the star matches 0 or more, so we wouldn't want an empty variable name. That's not really possible. That's just white space. So instead, we'll say you have to have at least one letter, and then you can have as many letters afterwards as you want following it. The other thing that's going to change is, right now, I said earlier, like a minute ago, we're going to go from our language being able to just evaluate a single expression to our language being able to evaluate a number of statements, where a statement is either a variable declaration or a mathematical expression. Mathematical expression being the expression you're familiar with by having looked at this grammar previously. So we're going to have multiple multiple statements in our program. So we need a way to delineate between different statements in our program. What you'll see most programming languages do, or not most, but a lot of programming languages will require you at the end of each line to have a semicolon. So whenever you finish a statement, you have a semicolon. And the reason that that's happening is because the parser and the compiler need to know when one statement ends and the next one starts. And so it just turns out it's an easy solution when it comes to implementing the compiler is just to require, as part of the context-free grammar of the language specification, that we just have some delineator, some letter, some token, something that is reserved. You can't use it elsewhere in the language, but it can be used to separate statements. And that way, when we're combing through the tokens, it's really easy just to group by every time we find out this semicolon, for example, if you're using the C programming language or Java programming language. In our case, we can go ahead and run with that. We can use semicolon. I like it. And you might be wondering, well, not every programming language has this. For example, Python doesn't have this. Python actually uses spacing for determining how it should split up statements and expressions. In our Lexer that we built previously, we actually explicitly made the choice to filter out white space to not overcomplicate things. If we want to do something similar to what Python does, we'd actually have to revamp our Lexer accordingly, because now white space actually has semantic meaning, where previously we agreed that white space was trivial and we wanted to ignore it. So this is the rule for a statement declaration. Now, the other thing we need to change is we said a program is now a list of statements. So we're going to introduce a new rule, program, and it's going to be a list of statements, and that's the end of the thing. And now in our grammar, the start symbol is not statement, it is now program. So start symbol is statement. And this looks good, except this supports the statement that is a variable declaration. We want the other one where we're just evaluating an expression. So we'll say that a statement can either be this variable declaration, or it can just be a mathematical expression. So it would look like an expression followed by this semicolon that we're using to delineate all statements. Cool. So you might say this looks correct. We're actually missing one other thing, because we said this has made 2 of the 3 changes. We're saying that a program is no longer a single expression. It is now a list of statements, where a statement is either a variable declaration or an expression evaluation. The third thing that needs to be able to happen is that we need to be able to say in pre-existing expressions, when we are just evaluating an expression, whether that's the right-hand side of a variable declaration, right here, or just a standalone expression as a statement, that we also need to be able to reference variables that were defined previously in the program. So right now, our factor term only lets you, the only way you can escape it to a terminal is if you map to an integer, or you have another expression wrapped in parentheses. A third option is an identifier. So if I have, on this line, I have let x equals 1 plus 2 times 4. Right here now, when I'm parsing that next line, x is a valid thing to use in that expression. So I need to make sure I have support for that in my grammar. Now, this is an interesting thing to call out, because let's look at this example right here. So this right here, I'm defining a variable x, And then in the next statement of the program, I have a expression statement, and that expression references an identifier named y. But y has not actually been defined, so it's invalid, and this is not a legitimate program, and our compiler should yell at whoever puts in this program. This might make sense intuitively, but what I said earlier was that the context-free grammar that we designed earlier represents the set of programs that is valid according to our language. Now what we're seeing is that the context-free grammar, it's possible to parse things that are valid syntax of our programming language, but aren't actually valid programs. So the context-free grammar is very useful for determining syntax correctness, but there's more to it than there's more to a valid program than just matching syntax. There's also idiomatic structure and semantics. So semantics here, one of the semantic rules we have is that a variable that's used in an expression must be defined prior to usage. And so that's something that we're actually have to update in our compiler where, hey, when we're spitting out code, if we're referencing this identifier, we've never seen it before, then something must be wrong, so we should also crash the program accordingly. Similarly, another example of things that would break is, let's say I have a variable declaration, x, and I reference x as part of the variable declaration. Well, x isn't yet defined, so this should crash as well. So there's things like that that we need to be careful of. But this is our updated working grammar. And so the very first thing we need to do is update our Lexer, because we now have some new types. We now have an identifier term. Like we want a token for identifiers. We'd want a token for this let keyword. We'd want a token for the equal sign. And we'd want a token for the semicolon. So what I'm going to do is hop over to the Lexer. Or actually, we need to hop over to our token definition first. And I'm going to delete the grammar up here because this is no longer valid. We'll just use the grammar in Parser. I can actually copy over what I had in Parser just for cross-reference. And so we see that we need to add support for some new things. So we're going to have a let the let keyword is a reserved keyword. Oh, another example of something that would be invalid is if I tried to, something eventually that like a lot of programming languages will complain about and not let you do is using reserved keywords as a identifier. So I could not say let equals 5 plus 3. The compiler would, for most modern programming languages, would complain about this because you're using a reserved keyword. Let is reserved. It is a terminal in our programming language that has semantic meaning. So we don't want people to use that and be confused on our parser side. How do we know if the let keyword in our Lexer is an identifier versus the let token, sorry. So there are some rules, and we'll find that the more we add to our programming languages, the more rules we'll have to deal with. I think for the sake of this video, I'm going to ignore some of the rules because we're not trying to build the most robust compiler. I'm just trying to show the high-level concepts of what programming languages support and how that's implemented at the compiler level. So we have let. We also have identifiers now. So this is another interesting one because except for number, until now, every token has been fully identifiable just by the token type. And number was the unique one, where for a number token type, we also needed to include the literal because that holds the actual value associated with the number. That's something we want to keep while we're parsing through the input. So the same is true for identifiers. The literal will actually be the name of the identifier, and that matters because we need a way to distinguish between different identifiers in the same program. And then we also have the equal sign now, and we also have semicolon. These would be our new token types. So that looks good. Let me go ahead and clear this out so we don't have this duplicated across multiple files. Save this. And now what we'll do, we need to update our Lexer. That's the very first thing we deal with. We have to have it comb through all of the input and correctly identify tokens. So I won't rehash everything we do here, but for 3 of the new tokens we added, equals and semicolon are easy because we already have a list of if-else statements that checks for single character matches. So we can literally just add 2 more. Doesn't matter where we put them. For matching the equal sign and the semicolon. So if the current character is equal to the equal sign, or if the current character is equal to the semicolon. In that case, we just simply return, we add to our list of tokens a new token with the correct type. The new types we literally just added in the other file. So that would be a equal for this guy and a semicolon right here. And then I'm also going to make this into a if-else statement, because once we match one of these, we don't want to keep going. Cool. Save that. That looks fine. The trickier two are going to be the let sign, because that's 3 letters versus all of these are just 1, and then also identifiers, which can be any number of letters. But it turns out the logic's kind of the same. Like if we see a letter, we should just figure out what the entire word is, and then it's trivial to then see if it's let, return a token of type let, and if it's not let, then it necessarily is an identifier. So what we can do is at the bottom here, just add one more statement. And that would look something like if the current letter is a character. So if current character, and there's a function built into the Kotlin programming language that lets us get this for free, is a letter. So in that case, what we want to do is, we know the first letter we're looking at right now is a letter, and we skip past it, so we actually need to go back one. Keep expanding the window until we find the first non-letter, and that must be the entirety of some word. And then from there we can figure out if the word is an identifier or if it's a let keyword. So I'm just going to split that logic out into a separate function called scan identifier. And we can define a private function scan identifier. Oops. So what we know is that the starting position, the index in the string that has the first letter, is wherever we are -1. Because the scanx token starts by consuming the current character we're looking at. So our current position is 1 past the first letter of the word that we just looked at to get here. And so we're just going to keep peeking. So we're going to use a while loop. While we peek, and it's a letter, then we are still looking at the same identifier. So we'll just keep advancing. While it is a... Oops, sorry, I got moved around. That was weird. While we have a letter, just keep calling the advance function. Keep expanding. And then, once we exit this loop, we know we have looked at all the letters. And so we have our word. We know the start and end position of the word. So we can just get that string by taking a substring of the original input. So Kotlin also has a built-in function for this that we used previously. We go from the starting position all the way out to current position. And recall that the substring method goes from the left argument index inclusive, but it goes up to 1 before the current position. And so when we exit that loop, current position is actually looking at the next character after our word. So we point to that because then it will go up to that letter, but not inclusive, which is the full word. And so now we can check. If the literal is the word let, then we know we have a let keyword. And so if that's the case, we would just add to our tokens list a new token whose type is this let. And the literal doesn't matter, so we can just leave it around the field literal. Otherwise, we must have an identifier. Token type of identifier. And now we actually feed in the literal. Cool. So if we did this right, that should be all we need to have our lexer correct. So, yeah, I really do want to write. Okay, so what we can do is test main by actually just aborting after we print out all the tokens. That's because we haven't done any of the rest of this stuff that we want to do yet. Interesting. Did I cut off too early? Oh, I never forgot to do the tokens. Okay. Okay, so we see this is fine, but this is the expression we already knew worked. We just verified that we haven't broken anything. Let's actually write a program that's a little more interesting. So maybe we say let x equals 5 times 2, and then evaluate x plus 3. So I'm seeing the let keyword being parsed correctly. I'm seeing identifier that correctly has x. I'm seeing the equal sign getting parsed correctly. The expression looks fine. The semicolon's correct. Then we see an identifier reference, a plus, a 3, a semicolon, end of file. That all looks totally fine to me. Okay, so now let's hop over. The next thing we need to do is update the parser. So let me go ahead and listen to the parser. And recall what we did earlier to build what we called this is the recursive descent parser. Is we had a separate method for parsing each of these rules, and then each of these rules could call each other. So there's a few more. It's called mutual recursion, where if I'm parsing a factor, it could call if I'm in parse factor, it could actually call back up the parse expression. And so if you trace the recursion stack of all these method calls, it's kind of how you end up with a tree of recursion calls, and then you end up with a tree that represents the syntax of the program. So we're going to need a few changes here. The first is we're going to need functions for some of the things we have here. So we're going to need a function for parsing a statement. Ooh, and before I can even do that, actually, we need to update some of our data modeling. So let me actually hop out of this. What we need to do, first, let's go look how we so our parser needs to end up returning expressions. And previously we just had it return one expression. Now it needs to return statements. And statements can be an expression or it could be a variable declaration. So first, let's go ahead and make a new class. STMT, just short for statement. Ooh. And we have two types of statements that we saw in the grammar. We saw a variable declaration statement, and we saw a expression statement, where you just are evaluating an expression that may or may not use variables, but it's not defining one. So those are the two things we need to define. So a variable declaration, var declaration. This has a few things of interest that we need to encode. One is the name of the variable, and then 2 is the expression that is used to define its initial value. The other one was an expression statement. And this is just an expression. And it wraps the expression variable we already had. But we also need to go, and I'll save this, and update our expression class. Because now an expression is not just a number or a binary expression, but an expression could also just be a variable reference. If I just say x plus 5, then you have a binary root where the right child is a number literal 5, and the left child is not, it's neither a number literal nor a binary node. It is a variable reference. So we can just make a third class here, which is a variable, and the only thing we need to encode about that variable is the name. and that itself is an expression. Cool. So that should update our data classes. Now we can hop back to the parser. And so we'll need a few new functions. So if I jump back to the grammar, we're going to need a function for parsing a statement. We're going to need a function for parsing a variable declaration. And we're going to need a function for, or I guess for statements, we now have two types of statements. One's an expression statement and one's a variable declaration statement. So we'll have this parse statement that calls either parse variable declaration or parse expression statement. And the parse expression statement is just going to be able to call the parse expression function we already have, and it'll just need to assert that there's a semicolon afterwards. That's the only difference. So at the top level, our top level parse function no longer returns an expression, it returns a list of statements. And so what we need to do is make a variable that tracks all the statements we've parsed. So it's a mutable list of statements, starts off empty because we have yet to parse anything. And then instead of parsing an expression and returning that, we're going to check while we're not at the end of the input, we should keep expecting there to be more statements. So we'll add to our list of statements a call, whatever the next statement that we parse out is. And we'll define this parse statement function in momentarily. And then now, we still assert there's an end of file afterwards. We don't return an expression, we return the list of statements. Cool. So now we need this parse statement function. And it's going to return an instance of this new statement class we just declared. And so there's two things a statement can be. Statement is either a variable declaration or an expression. We differentiate by seeing if the first token is a let token or if it's not. If it's let token, it must be a variable declaration. Otherwise, we'll treat it as a variable, as an expression statement. So if we can match a token type of let, it must be a variable declaration. So we'll make this function return a call to a parse variable declaration, which we have yet to implement. We'll do that after. Otherwise, it must be an expression statement. So we'll just call this parse expression statement, and this is something we'll also define right now. Cool. So that means we have two new functions we needed to implement. One is a parse variable declaration, and this will return a statement. The other is parse expression statement, and this will also return a statement. Cool. Okay, so our parse variable declaration, we know that it should expect to start, we should expect a let keyword, but we've already matched that 7 lines above where I'm at, so we've already skipped past the let by virtue of making it to this function. So first, the next thing that comes after the let keyword is the variable name. So we need to get the name from the next token. So val name, it's going to be a string, and we're going to call the consume function. We expect the token type of identifier. Not crash. And if one doesn't follow, we would crash. So we would expect a name for a variable declaration. If we do get something, what we'd like to do is pull out the literal. Because recall, a token has a literal. And that literal, for the case of a variable declaration, is the name of the variable. Okay, so we'll get the name for the variable. Then we expect an equal sign to follow if we look at the grammar. So I'd consume a token type of equal. And if we error out, we should say expected equal sign after variable name. Then I'll go ahead and parse the expression out that equals the initial value for that variable. So the initializer, i.e. the expression that determines what the variable will be set to, we can just call from parsing an expression, and we already have that one built out. And then afterwards we expect a semicolon to end the variable declaration statement. And so if we get here, then we can just return an instance of the statement where we feed in the name and the initializing expression. So that's our parse var declaration. And now we have to update our parse expression statement to first get the expression. And it can do that by calling this parse expression function that we already had, so nothing's new there. And the difference is that it needs to assert that there's a semicolon after. And so if it does that, then we have a valid expression statement, and we can return the statement which wraps this. Not a var declaration, an expression statement. Cool. So those were only the new functions we need. And then the other change to our grammar, recall, was that a factor term can also reference an identifier. So we need to update parse factor. So originally parse factor either matched an integer or an open parentheses. Now it could also match, in case 3, an identifier. So if we match a token type of identifier, then we can just return an instance of the variable expression that we defined, that was the first change we made to the original file. And we're going to look at the previous item, because if we match identifier, then we skip past to the next item. But we actually want to go back, look past to the item we skipped by, because that's the variable, the identifier token, and that token encodes the name of the variable we're referencing. So we want to capture that. And we should actually pull out the literal. Cool. So that should be everything we need to update the parser. What we'll do is save this. Let's hop back over to our main file. And instead of returning after we print out the tokens, let's stop printing out the tokens because we know that works. Let's have it print out our expression. Our pretty print needs to be updated though, because it does not handle the variable literals. So if we have a exper.variable, then I will just print out the variable name. But then also, our parser no longer returns one expression. It's going to return a list of statements. So we actually need to print out each statement. So our program is now, we can print out each of the statements in the program. And so we actually could just make our pretty print accept the program. And now our compiler will compile a program, but we'll have to get there and fix that. So I will actually comment the rest of this out for now. But our pretty print does not take an expression, it's going to take a statement. And so when the statement is actually, so we're gonna pull this out into two separate functions, because we still want this logic for printing out the actual expressions, but we want a new one for also printing out statements. So I'm gonna make a new function, which is pretty print, but it prints out a statement. And so then for each of our statements in the program, I'm going to pretty print those. So program.for_each. And so for each statement, for the current statement, which is a type of statement, we will pretty print that current statement. Cool. This looks good to me. We'll see what the compiler says in a few minutes. So now this pretty print statement, it'll do the same padding trick. But we need to check if the statement is either a variable declaration or an expression statement. And if it's an expression statement, we'll then pretty print the expression itself, which we already had below. And we'll add some indent. And if it's a variable declaration, we'll print out the variable name and the assigning expression. Add the padding, a variable declaration, named, and then we will pretty print the statement's initializer. And we will also add some indent. Okay. This should be sufficient to pretty print. Let's go ahead and run it. I'm super confident we're going to have a compiler issue. Okay, a few compiler issues. Let's see. When must be exhaustive on 21 of the compiler. Ooh, okay, we're not there yet. This is actually the compiler. So we can actually just else this out for now. To do. We haven't gotten to the compiler yet, that's fine. Actual type is statement, but expression was expected. Let me hop back into that. That's 21 of main. And that's because I forgot to pass in an indent. Start at 0. Two more issues, not bad. Unresolved reference padding. Oh, that's just a typo. On line 36. Cool. And unresolved reference statement. Oh, it should be STMT. Okay. No, that's not what I wanted to do. Now let's run this. Perfect. Okay. So I see now my program is not one node that expands out. It's just a list of things. So there's two different things that are at the top level because there's two different statements in this program. We have a variable declaration named x, whose value is a binary operation of 5 and 2. Sweet. And an expression statement, which is a plus of a variable named x and number 3. Sweet. So see how much faster that is? Like, we've updated the Lexer and the parser so much faster than when we first had to write it. So the next thing we actually need to do is have our compiler go ahead and spit out the actual instructions for this. But to do that, we actually need to introduce two new instructions to our virtual machine. So let's hop into our definition of instruction. And these are all the instructions that our computer that we're compiling to can execute. So we're going to add 2 more instructions here that I skipped earlier because we weren't even focused on variables. And we're going to keep adding more instructions to this machine. But pretty much the only way we can implement variables is if we have a way of storing stuff. So if I have some expression and I want to define a variable, like let's say I know how to evaluate that expression on the stack, but I need to then write that somewhere. So our virtual machine is going to expose two new instructions, 2 low-level instructions. So our machine's going to have, in addition to this area where all these instruction lives and the stack lives, it's got the concept of a local, which is just a place to store something. And so you can have as many locals as you want, and each one's assigned a unique number. So every time we define a new variable, we're just going to map it. Our compiler is going to give it a new local slot, and we'll keep track of that. And then whenever we see that variable referenced in code, we can just emit out the instruction that loads from that local slot onto the stack. So we have 2 instructions. One is going to be storing a local, and one's going to be loading a local. Both of these take on a slot number as an argument. So if I call store local with a slot number, I'll originally start off with 0 because I have not written anything in. Then it'll pop whatever's on the top of the stack and write it into that slot, which is these slots are independent of the stack. It's something else, somewhere else in the computer. We don't need to worry about how the computer implements it. That's out of the scope and not something we're interested in. We just want to be able to translate to the computer's language that it speaks in. And so you can store a local, which will pop from the stack and write it into one of these numbered slots, or you can read from one of these numbered slots and it'll push the value in that local onto the stack. It won't get rid of it from the local, it'll just take whatever the value is and push it on. So we can define 2 new instructions for this. A data class for loading a local, and it's going to take in a slot number. This itself is an instruction. And then there's going to be one for storing a local. It's going to have to write to a slot, so it needs to know which slot to write to. Cool. So pretty much, let's say if we can walk through this. Let's say that someone had a program where it was x equals 1 plus 2, y equals 4 minus 5, and then we print out x plus x times y. So what happens is we'd evaluate the 1 plus 2, and the compiler would say, okay, new variable is x. I'm going to say x can live in the local slot 5. So it'll evaluate 1 plus 2 and call this store local at slot 5. Then let's say it sees a variable declaration for y. It evaluates 4 minus 5 to -1, and it say, hey, I'm going to let y live in slot 6. So it'll call store local to write the evaluated result of this expression to the 6th slot. And then when we actually reference these variables, the compiler knows, hey, I've seen variable x before, and I remember I assigned it to the slot 5. So to reference that variable and get that value back on the stack, all I do is call to load local with that slot number. And similarly for y, I just want to get the value of y onto the stack, because recall, to evaluate this multiplication sign, we evaluate the left subtree and the right subtree. These are no longer binary expressions or number literals, they're variable references. So when we reference a variable, all we need to do is get it on the stack. That's how we evaluate a tree. To evaluate the left and right, remember we have to do whatever it takes to get some number value and then push that number value on the stack. In our case, all we have to do is look up a variable. So we're just going to admit load locals. So a load local 5 to get x onto the top of the stack, then a load local 6 will get y on top of that on the stack, and then we'll spit out an add instruction, and that'll actually do the evaluation. So I'll save this. And now we can go to the compiler. And so a few things need to change. We said that there can be any number of local slots. So we need to do 2 things. First, we need to keep a mapping of variable names to what slot we've assigned them to. So we'll keep a map, which is a mutable map, and it's going to be a map of, you feed it in a string, which is the name of a variable, the name of an identifier, and it gives you the integer, which is what slot number we're reserving for that variable. And it'll be an empty map for now. And it's going to be mutable because as we process more variable declaration statements, we'll find it. And so what's also interesting is if we get to the point where we're referencing a variable and it's not existent, that means it has not been defined, so we'll have to crash the program, as we talked about earlier. We talked about the difference between semantic correctness, or syntactical correctness versus semantic correctness. And then we also need to keep track of, we said we have any number of these locals. We're just going to start off using local position 0. We'll just keep incrementing. Every time we find a new variable declaration, we'll start off, the first variable we see that's defined, we'll give it to the 0 slot. The next variable we see get defined, we'll give it to the first slot, and so on and so on. So we just need to keep a track of the next local slot number that we can use that hasn't already been used. It starts off at 0. Okay, so now our top-level compile function, this needs to change. It's no longer taking an expression. It is now taking in statements, which is going to be a list of statement. And it's still going to spit out a list of instructions, because that's what the compiler ends up spitting out. It translates from one language to another. And so what I need to do is just for every statement, just emit whatever instructions are needed to generate that statement. So what this looks like is we could do, taking a list of statement, we could pretty much say, get rid of this right here. For every statement we have, so statements for each statement is a type of statement. This gives us the current statement we're looking at. What we're going to do is just call this emit statement. We're calling emit with the current statement, and then also our list of instructions that we will add to. And I'll just keep it on one line. Okay, so our emit does not take an expression anymore. Emit takes a statement. So we'll need to make a new function for that. So a statement is one of two types. If it's an expression statement, we already know how to deal with that because we have this emit function right below that correctly emits the instructions needed for an expression statement. So we'll just call that. The more interesting case is now if it's a variable declaration statement. And so if that's the case, we need to check. For defining a variable, the first thing we need to check is have we already defined this variable? If so, we have a choice here. We can either choose to crash the program, or we could let the variable be redefined. Well, for now, we'll just choose to crash the program. Many programming languages will not let you define duplicative instances of the same variable, because right now we are mapping from the variable name to what local slot it has. So if we have two variables that are supposed to be different with the same name, we can't map them to two different slots because the identifier is identical. We can't distinguish between the two different variables that you're discussing. So if our local map, if our mapping that we created above has a variable already with this name, then we should just crash. And I can print out the statement name. Otherwise, I'm going to go ahead and emit the instructions that would give us the initializer of the statement. I.e. the right-hand side is the equation, or the expression, and we need to evaluate that first before we can write it to a local. Next thing we can do, we have, so after this, it submits all the instructions that would get the starting value of that variable onto the stack. So we'll need to reserve a slot for the variable. And that's just going to be in the next local slot, which we already defined above. And then we need to increment that variable. So the next time that we get next time we encounter a variable declaration statement, we can just use the new slot and make sure we don't end up assigning it to the same slot. And so now we can update our mapping, where we map from the variable name to this slot that we just reserved. And then the last thing we need to do is write an instruction for storing the value, which is going to be on the top of the stack after we evaluate whatever this call right here puts onto the stack, to the local. Cool. And this should be all we need to evaluate things. But there's one other thing. We have to update our emit expression, because if we're emitting, and this is what our compiler complained about earlier, we correctly handle if we're emitting a number literal expression or a binary expression. We need to handle the expression statement, or sorry, the variable expressions. So that's when we need to load from a local. So we first need to check the mapping. What slot does this variable name belong to? And it's an optional int because it might not exist. We might reference a variable that doesn't exist. So if the slot is null, if there's nothing in the map for that, then we should actually error out. Referencing undefined variable expr.name. Otherwise, we can just emit a instruction for loading the local. And we already know the slot it belongs to by looking it up from the map. So that's as easy as it is. So now, let's compile this. Oh, fun. Okay, we have a few issues, all in this instruction class. There's something wrong with instruction. Starting on line 9, object. Oh. I accidentally got rid of a semicolon there. Not sure how that happened. Compiler 33. Compiler 33 says unresolved reference to local. Locals. That should be pluralized. Then we had one other one, machine. Ooh, okay, I'm gonna pause this. We haven't gotten to the machine yet. That's the class I said I was not gonna let you look at. Okay, figured that out. Okay, so now we need to update our main, because we need to tell it to start printing out the instructions again. And our machine is not yet updated to run, but let's go ahead. Cool. So this is the expression we looked at earlier, where we define a variable and then reference it. So we can see that we push out the statements of the right-hand side. Let me move my mouse down here. So to define x, the first thing we did was emit all the statements that would be needed to evaluate the starting value, which is a 5 times 2. We can already know that these are the 3 instructions that we'd expect to be emitted. And then we see that we're assigning x to slot 0, and we store into that slot. The next thing we encounter is this expression right here, and we know that we should expect to see the instructions for resolving the left child then the right child, then an add. So we see the right child, the 3, and the add. For the left child, we see that's just a variable expression, and so we're loading from that local slot. So this looks totally correct. Now we talked about a few problematic cases. Let's go make sure that I can't define a variable twice. So if I tried to find an x again after this, then the program should crash. Quick, I'm seeing a duplicate definition of variable x. My face is probably cutting that off. That looks great. The other thing I claimed that we would need to defend against earlier was if we reference a variable that doesn't exist. So let me define a variable y and have it be equal to some variable u, which doesn't exist. Sweet, we get a illegal state exception referencing an undefined variable. That's great. The other thing I'm kind of curious about is what happens if we let y reference itself? This shouldn't be valid either, because we're saying let y equals y, but there's no value for y. The right-hand side of the expression should be what's evaluated to figure out what y should be. So you can't reference y, or else you kind of have a conflicting source of truth. And we do correctly error out there. So that looks good. Let's do one more where we have two variables. Let y equal 1. And then we'll just do evaluate x plus y. Okay, so I can see that we are evaluating the value of x. We store it into local slot 0. That looks good. Then we're pushing 1, because that's all we want y to be. And then we store that into slot 1. Sweet. Then to do x plus y, we load their respective slots and add them. That looks totally fine. So it looks like as we have more variable declarations, we're correctly mapping them to new local slots. This is pretty cool. Now let me go ahead, and this is powerful. Let's go ahead, before I can convince you that this works, by updating the machine. I'll pause my video because I said I'm not going to show changes to the machine. Let's update it so it can actually, I'll need to update it because we just added these new instructions that it doesn't have support for. So I'll go and add support for that, and then we can run entire programs and make sure things work correctly. Okay, so I've gone ahead and updated the machine code. So now if I show the main file again, then we should see we let x equal 5 times 2. That should be evaluated to 10. Then y is evaluated to 1. And x plus y should be 10 plus 1. So we should see 11 being the last value on the stack. So let me go ahead and run this. And I can see that that appears to be the case. So our final stack is 11. So that seems good. Let's go ahead and just feed in one more. So maybe let me just multiply by x first, and then let's add 2. So now we should evaluate y times x first, which is kind of trivially just, I guess we can make this a little more interesting, so it's on multiplication by 1 to make sure it's working properly. Usually good tentative testing is you would use very different numbers to make sure that the correct output could only have been derived if the correct operations were performed, not if a multiplication by 1 could have omitted the actual multiplication and gotten you the same answer. So that's not very good testing, but I'm not very good at writing tests either here. As you can see, I don't have a single test file. I'm just picking up examples as I go along and assuming that each change I add isn't breaking other functionality. If we were making this a little more robust, that would be a different assumption, but for the sake of time, we're not doing that. Anyways, we should evaluate 10 times 2 to get 20 first, and then we can add, the additions are trivial in terms of, with respect to the ordering in which we execute them. So we get 22 plus 10, which would be 32. So let's go ahead and run that. Perfect. So this looks good, and this is really cool, because now we're not just a mathematical expression operator, we can actually have variables. And there's not a lot we can do with variables, but it's cool that we can define them, and we can define compound expressions based off of sub-expressions without having to have some nested parentheses mess. We just say, hey, this sub-expression, just call that x, call this other sub-expression y, and then it's much higher level for us to operate with x and y. So that's cool. One thing that is interesting though is I can't reassign a variable a value once it's been set. So variable implies by virtue of its name that the value that it's referencing can vary. Here we have the ability to define a variable, but there's actually no way to change its value once it's been defined. You can only reference it. And if you try read, if we saw what happens, or if you try assign a variable that's already been declared, it'll crash the program. So we need to actually add another instruction. What we have right now is something called in programming languages, it's generally called a constant. It is a named entity with an identifier that points to some evaluatable value, but the value of that reference never changes. We'd like to make our references be able to change the actual backing value. So, like if we had a counter or something, we could say, like, let counter equal 0, and then you could keep adding 1 to counter every time some accountable event happens. We can't really support that right now. So what we're going to do is add just a new type of statement to our programming language that actually lets you update the value of a variable. So let's go ahead and jump into the parser, or let's start, the parser, because that's where we have our context-free grammar at the very top. So right now a statement is either a variable declaration or an expression that may or may not involve variables. We'd like to just add a new type here, a new type of statement, which lets you update the value of a variable that already exists. Because we can't piggyback off of this expression, because it'd be somewhat ambiguous. We could update the semantic interpretation of our language to say, if you use this let expression with an identifier that already exists, we'll just update the value of that variable. That would be fine. I think you might lead yourself to confusion. Imagine if people started using your programming language where they think they're defining a variable that's new, but it turns out they've already used it somewhere, and so they have they have what they think are two different variables, but they're actually just writing over each other. So I'd like to make the distinction very apparent in our tiny language. So let's add a new expression type to this grammar, and it can be, we'll say maybe right now to define a variable we're using let identifier equal expression. Maybe we'll say update identifier to expression. And let me go ahead and pull these onto separate lines because it's getting a little bit long. So these are our 3 different types of statements that our programming language supports. I can pull these out to the hidden level, and I guess I should use double quotes here to be consistent with what we have above, even though the above is not already consistent to begin with. Okay, and the last thing is that this is a statement, and we said all statements need to end with semicolons, so we just have to add that to the statement right here. So now, we have to go update our Lexer, our parser, and our compiler. We saw the exact same 3 sets of things we needed to update to add support for variables. It's the same thing we're going to add. We're going to have to do the same exact process for supporting this new syntax that we're introducing to our context-free grammar. So I'm guessing you could actually probably know how to do this on your own if you put your thought to it. But we'll walk through it, obviously, because I'm not here to make this a exercise to the viewer for everything. So I'm going to save this. The first thing we need to do is deal with now parsing the input, because we introduced 2 new keywords to our language. There's 2 new token types. The word update and the word to now have literal meaning, so those can't be used as variable names. They are parts of terminals of the language itself. And so if we encounter the word update, we should not parse it as an identifier token whose backing value is the string update. It should just be a new type of token, which is update. So let's go ahead and update our token definitions. We have 2 more now. We have a update token and a to token. And that's all we need to do here. Also, one other thing I actually forgot, not to jump back, but I actually added one more commit after. So we talked about this commit that's second from the top where we add support for variables, but the machine itself didn't work that. It's like we could print out the set of instructions the compiler would spit out, and we'd parse the tree correctly, but we didn't have the simulator for our machine that would actually interpret those instructions and tell you what the correct or the final result of the program would be. I added one more commit up there where it's titled correctly, add simulator support to variable usage. So if you want to pull this code locally at this point, pull from there, and then you can play around and actually write complex programs and see what they evaluate to. That's just a digression that I wanted to make sure I didn't forget. back to what we were doing now. So we've added support for a new token type. We've updated our grammar. The next thing we need to do is go to our Lexer and make sure that whenever we see the words update in 2, we don't return a identifier type. We return these new types we just defined. So I'm going to go to the Lexer, and we already had right here scan identifier, which as soon as we see a letter, we just keep expanding outwards until we find a full word. We keep expanding while we have letters, and that start to end must be either an identifier or a token in our grammar that represents a reserved keyword. As we see for the example, let is the only reserved keyword we have so far. So now we're just going to add in 2 more cases. If the literal is equal to the word update, then we should return an update token. So I'll just copy the same logic here. Update, and then if we see the literal, oops, that should be an else if. If we see the literal two, we should also update. Formatting here. Okay, so now if we ran through our program, it'd correctly lex out update in 2 not as identifier tokens, but as actual 2 tokens or update tokens. So that's nice. So then the next thing we need to do is we've updated our Lexer now. Now we need to update the parser. So if we see this new type of statement, which is a variable update statement, we want to parse it out correctly. But before we can do that, we need to define what that type of statement would look like in terms of representation. So where we define all of our statements, right now we only had a variable declaration statement or an expression statement. Now we need to add support in for a variable update expression. And so to update a variable, the 2 things we need to encode are the variable we're updating, which is just the identifier, which we can call a string. And then the expression value the expression that when evaluated will tell us what the new value for that variable should be. And then this, of course, is a type of statement. Okay, so now we have our data modeling. So now we actually can go to our parser and actually parse out and conditionally return one of these variable update statements when we see that appear in the source program. So what's interesting, what you'll see in many other programming languages, you could just say, like if we had let x equals 5, you could just say x equals 5. We could have added support for this. So the thing is, when you are reading this x, it requires a little more logic if we had it like this, because you don't know if this x is referencing an expression type of statement, or if it would be representing a variable update statement. So by using the update keyword, we make that unambiguous and it's very easy to parse accordingly. So that's why I did that. And if you don't understand me, then let me tell you, when we are parsing a statement, right now, if we see the word let, we know it has to be a variable declaration. If we just had this other syntax I just discussed, we wouldn't know if we're parsing an expression statement or a variable updated statement without expanding further outwards and seeing if there's an equal sign after the expression or an identifier or a semicolon. So it makes it really easier if we just have a reserved token, which is the token for update, and say, okay, if the next token is an update, then it has to be a variable update statement. And so we can do the same way where we just make a new function called parse variable update, and then we'll just define that function right below. And what this will need to do, first we have to consume the identifier. So we need to figure out the name of the variable we're updating. So the name of the variable we're updating. And we'll get that by consuming a token type of identifier. That's the next thing that should happen. So the error in this case would be that we
if you don't have an identifier after the update sign, then it's an invalid statement, and the issue is, must specify variable name to update. If we do get this, then we just need to pull out the literal value, and that tells us the name of the variable we're updating. The next thing after we have the update keyword followed by the identifier is we expect the keyword to, so we can just consume that literal off of the input stream. So we can consume a token type of 2, and we'd say, expected literal 2. Cool. After we see the literal 2, we then expect the expression that we are updating the variable's value to. So we can get that just by parsing the expression. So the value is an expression type, and we just get that by parsing the expression. So this is that same idea of mutual recursion, where we already have the logic for parsing expression. So we know that the next thing in our input stream should be an expression. So we'll just call this parse expression, and that will either correctly parse the expression, or it'll error out if what follows is not syntactically correct according to this context-free grammar. So after we parse the expression, the last thing we need to do is we expect a semicolon to end out every statement. And if that's done, then we can return this new data type, a variable statement of a variable update. This is what we just defined in the previous file, and the two things we have passed in are the name of the variable we're updating, and then also the value, which is the expression that when evaluated tells us what the new value for the variable should be. And turns out, since we've architected things cleanly, that's all we need to do for the parser as well. So you're seeing that by using a well-architected pattern, making these incremental updates to the language is actually very fast. Versus there's a lot of overhead. It took us several hours to just be able to evaluate mathematical expressions because I wanted to be able to explain all the core concepts and structure things in a scalable manner. And so now that we went through that brutal work, it's much easier to add these way more complicated, or at least seemingly way more complicated things into the programming language. But it turns out it's actually, I'm not going to trivialize it, but it's not that difficult. It's everything you already know how to do. So the last thing we need to do is go to our compiler, and we need to be able to emit the correct set of instructions when we encounter this type of statement. So you have this emit function, which takes in a statement type, and it'll spit out all the instructions it needs to evaluate that statement. I just happened to open the file to this exact part of the method, which is convenient. But we now have a new type of statement, which is a variable update. So when our statement is a statement type of a variable update, then we can pull out the name of the variable and the expression. So the first thing we want to do is make sure that the name of the variable exists. So you can't try to update a variable that hasn't already been defined. So what I can do is use our slot lookup table, and I can get an optional integer. So I'll look up into this slot table the statement, the variable's name. And so if we'll get a null, which is the absence of an integer if it's not in that table, which means it hasn't been defined. Or if it has been defined, we'll just get the slot variable, the slot number that we've already pre-reserved earlier in the evaluation of this program for that particular variable. Because we're going to need to evaluate the expression and then write it to the correct slot. So if the slot is null, that means the variable does not exist in our mapping, so it hasn't been defined. So we can just error out. Failed to update a variable with as name before declaration. Cool. Otherwise, all we can do, first we need to emit all the instructions that would evaluate the expression that we're using to update our variable. So I'm just going to call the same emit function that we're already in. We're using recursion. And I'm going to call, or actually we're not going to, we have an expression. So we're going to call this function below, which emits the instructions to evaluate an expression. And we have this list of instructions we're working with. And then after that, the only thing we need to do is emit a store local instruction,
with the correct slot. So what this will do is it'll spit out a set of instructions. That set of instructions, when evaluated, will put the final value of the new variable onto the top of the stack. So all we need to use is this store local, which will take whatever's on the top of the stack and write it to one of these local slots. And which local slot we write it into is known by what we did on this line right here. So all I have to do is add to instructions. Is a store local with the correct slot. And that is everything we need to do to add support for updating variables. Let's go ahead and hop over to our main file so we can test this out. And there is one thing we need to do for our pretty printing. When we have we're pretty printing a statement, we're pretty printing a variable update statement, then let's go ahead and print that out. Use the prefix padding. Print out the variable name that we're updating, and then we can pretty print the expression that we're evaluating to specify the new value for that variable with one more indent. And so you might be wondering, do I need to update the machine instructions, this machine right here? The answer is no, because we're not introducing any new variables to the machine. So if our machine's built correctly, which I hope it is, we'll find out shortly, we did not need to touch the machine at all for this. So now, let's go ahead and run this without even updating the input program to use this new statement. Let's just make sure we didn't break anything. Everything looks good. That same that same program being a list of statements, still evaluates to 32. So we haven't broken anything. That looks good. And oops. Now what we can do is let's go ahead and get this. So we have x equals 5 plus 2. Let's say x equals x times 2, and then x equals x plus 1. So that's two variable update statements. So we start with x being 10, then it should become 20, and then it should become 21, and so we'll end just by putting x's value on the top of the stack. Let's see what happens if we run this. Interesting. Did I do? Ooh, okay, we have a compiler error. Sorry, I missed that earlier. We actually did have a compiler error, I missed it. And so it's complaining that the variable is defined as, oops, I used the wrong variable name. So in our compiler, instead of local, our table of mappings is called locals, pluralized. See if that fixes it. And we're getting a complaint that we expected a semicolon following an expression statement. I'm using invalid syntax to put in my own language. Sorry, I'm getting confused with how I would do it if I was writing in Kotlin. We need to specify that this should become update x to x times 2, and similarly update x to x plus 1. Apologies. Okay. Now we see our program here starts with a variable declaration of x to 5 times 2. Then we have a variable update where we say x becomes some new value, which is the previous value of x times 2. And then we do that again with an x plus 1, and then we print out the variable x. And so what's interesting is because you might be a little confused, how are you allowed to reference x when we're updating it? It's because you know, by seeing how we implemented this on the other side, to evaluate the statement, we just emit the set of instructions to evaluate this right-hand side expression, and then push that final value into the local slot associated with this variable x. So in here, whenever we're evaluating this right-hand side, it's just using whatever the value of x was at the time we walked into evaluating this statement. So whatever x is defined after all the previous instructions here is the value of x that's going to be used when resolving this expression here. And so now I can see that we correctly evaluate this to 21. And what's happening, we can look that we see we initially get the value for x onto the stack, and then we store it in the local slot 0. Then we're going to evaluate x times 2. So we load that local slot onto the stack, push a little into, multiply those to get 10. Or sorry, multiply those two to get 20. Store that back into the local slot for 0. So now variable x is equal to 20. And then we load that value back onto the stack, 20, push a 1, and evaluate that. That gets us a 21 on the top of the stack. And so then we write that into the variable for x. That's the second variable declaration update. And then the last thing we do is load from that to put it on the top of the stack so we can see that our stack ends with this value 21. So this is now cool. We now have the ability to update a variable after we define it. But like, let's say in my program that I wanted to keep updating x. So like maybe while x was under 100 or something like that, I wanted to keep adding a 1 to x. And you know, what we see, the final value of x would be 100, but under the code that we see generated, we'd see these repeated variable updates where you keep seeing x being assigned to x plus 1. And so what we're going to do now is add support in for branching. And so what we've seen so far is that our compiler will spit out a series of instructions that are executed top to bottom. And this is cool, but it's somewhat limiting in what we can do here. Sometimes, based on whatever the value is on the top of the stack, it'd be cool if we could actually change the instructions we're executing. So maybe if I have like a 50 on the top of the stack, I want to do some other work that counts down from 50 to 0. But maybe if I have like above 50 on the stack, I actually want to keep counting up. Something like that, just fictitiously, for example. So we actually need to be able to break out of this control flow, where instead of reading top down, we'd like to be able to break out and, based on some value that's on the stack, jump somewhere else on our list of instructions. And so this is called branching because you are branching out of where you are in the, sequential execution of instructions. So let's go ahead and think about how we would implement that. The other thing I should go ahead and do is commit all of our changes first. So I'll make this commit message, add support for updating variable values. Okay, go ahead and push this. And this is nice because now we don't have constants, we have true variables, and the value backing a variable can vary, it can change. So let's go ahead and just jump into a random file that we can just use for taking some notes here. So we've been using if statements a lot in building the compiler, which is a functionality of the Kotlin Programming Language, and we're trying to get to something similar in our tiny language. And so we kind of see the structure is we have like the word if, and then in some open parentheses we have some expression, and if we enter that, then we have some number of statements. It's like statement star, if we're thinking about it in grammar form. And the parentheses in the first line are literal parentheses versus the second line I'm just using as like syntax. But I guess I could just get rid of this if I wanted to make it clearer. But so I think we understand inside the if block, you could have a bunch of statements, and we already know what statements are. Like we have a expression statement, a variable declaration statement, or a variable update statement. That makes sense. And we also know what an expression is. Like 5 times 2 is an expression, and just like the result of some mathematical computation. But the way we're using the if statement in the Kotlin programming language is the expression we're putting in the condition to decide if we enter that block or not. Block being what happens between these brackets, and it's just a list of statements. is not really a number. We're not saying if 5 you do this. We're using something that results to a binary outcome. So binary means there's either 2 outcomes, and it's either true or false. So if some expression evaluates to true, we should go in here and execute this set of statements. And if this expression up here evaluates to false, then we should skip over this and just keep executing the instructions or the statements, i.e., more precisely speaking, that follow that block. So it's called a conditional because we only conditionally execute those statements within the curly braces. Curly braces you can kind of see in programming languages, it's called a block. But in our programming language, TinyLang, right now, our expressions just evaluate to numbers. And so we can say if x times 2 or 5 times 4, 5 plus 3, 10 minus 2, doesn't really mean anything. What we might want to do, and I think is a good bridge, is get some sort of truth, i.e. getting these binary expressions by introducing comparators. So, our expressions right now just support like 5 times 2, for example. It's not really saying true or false. But what if I said if 5 times 2 is less than 4? Then we know 10, we could evaluate these expressions. 10 is less than 4 is false, so we wouldn't enter this. Similarly, we could have the greater than sign. And in this case, 5 times 2, 10 is greater than 4, so we should execute these number statements. So what we're going to do before we actually get to introducing this if statement is add the concept of comparison to our language. And the way it's going to work is it's just going to be another operator. We have plus, minus, multiplication, division. We're going to have less than and greater than. And you're going to wonder then, how do we bridge the fact that the first 4 operators for math take in numbers and spit out a number, but the greater than and less than, they also take in numbers, expressions, but they don't spit out a number, they spit out a yes or a no. It is either true that 10 is less than 20, or it is false that 10 is less than 20. And so how can we encode the fact that some expressions evaluate to numbers, but other expressions evaluate to truth or falsiness? And it's also tricky because everything we've built our language around makes this natural assumption that all expressions do just boil down to numbers. So the way we can actually fit into that mold is by making these comparison expressions also evaluate to numbers. So pretty much what we're going to say is that 1 or any positive number is true, 0 or any negative number, let's just say 0 for simplification, is false. And so pretty much if I evaluated the statement 5 is less than 4, if I wanted to evaluate that, the result should be 0. So if we found a way to encode this into our language, and I had a program whose program had one statement and it was just this expression statement, then it should put out a 0 on the top of the stack. Or if I said 5 is greater than 4, this is true, so it should put out a 1 onto the top of the stack. And so we'll be able to see that when we use these two operators, the greater than or less than sign, if we use them, we'll represent truth by just using the number 1, or false by using the number 0. And so then looking forward ahead, once we have that built out, if we had a statement like this, we would then evaluate whatever comes in here and see if the number is greater than 0. And if it is, we'll interpret that to be truthful. And if it's not, we'll interpret it to be false. So in this case, under the hood, we'd evaluate 5 times 2 to 10. We'd put that onto the stack. We'd evaluate 4 as 4, put that onto the stack. We'd pop them off to evaluate the comparison. We'd see that 10 is greater than 4, so we'd throw a 1 to the top of the stack. 1 represents yes, truth. And then this if statement, it'll look at the top value of the stack to figure out if it should branch into these statement list or if it should skip over. And if it sees a 1 or any positive number on the top of the stack, it can go ahead and treat that as, hey, whatever expression appeared in these parentheses logically was a yes. So representing yes with a 1 and no with a 0. So before we can even think about the if statements, let's go ahead and add support in for this new less than and greater than operator. And I'm going to skip less than or equal to and greater than or equal to because it's just a little more complicated, but you already have the idea, and I don't want this to get too long. So the other thing that we're going to have is we're going to have new instructions for the language we compile to. our language that we're compiling to has instructions that are represented in this file right here. And right now we have, the four instructions, for addition, subtraction, multiplication, division. We're going to add 2 new ones. The first one's going to be a less than. Oops. And the second one's going to be greater than. And so what the less than is going to do, it's going to pop the first the top 2 items off the stack, and it's going to check if so if we have the items B and A on the stack, so if we had B and then below that on the stack we had an A, it's going to pop B and A. It's going to check, is A less than B? If it is, it'll push a 1 to the top of the stack because that's truthful. It is less than B. And if it's not, it's going to push a 0 onto the stack because we said 0 represents false. Similarly, greater than is going to do the same thing, just inverted. So it's going to take the top 2 items off the stack, compare them. If the second the top thing is greater than the top thing, then it's going to spit out a 1 to represent true. Otherwise, it's going to spit out a 0 onto the top of the stack to represent false. So that's the new instructions that we're going to support in the language that we compile down to enable these new comparators in our language. Now you know that we're going to do the same exact process we've done now 2 times in a row. We're going to do it a 3rd time to add support for this in the language. So you know we need to start with our token definition. And now we have 2 new tokens, less than and a greater than token. So we'll define token types for these. Then we need to go ahead and head over to the Lexer and actually parse these tokens. So when we look at each next token, we already check all these single character tokens that have complete meaning. We're just going to add 2 more to that list of tokens we checked for. So I'll say else if the current current character is equal to a less than sign, then we should spit out a less than symbol. And similarly, if the current token is equal to the greater than symbol, we should spit out a greater than symbol, a greater than token, sorry. So that means we can now read the raw input into these tokens correctly. And so now the next thing we need to do is go update our parser. And let's jump back up to this grammar because our expression that we've been working with up here needs to change a little bit. So we talked for several hours about how precedence is baked into the rules we have here. So now, let's just look at an example. If I had 5 plus 2 less than 6 times 3, we know that we need to evaluate, 6 times 4. We know we need to evaluate both the 6 times 4 and the 5 plus 2 before we evaluate the less than sign. And so we know that to evaluate a comparison operator, we need to evaluate the 2 operands before we can then look at the final result. And so we're actually seeing that this is happening such that addition, in this case, should be evaluated before this less than sign. So in terms of precedence, this less than sign is the weakest of all operators we've seen so far. It is weaker than addition and subtraction. And that's not included in the PEMDAS you learned, but we know this is true because intuitively we know this is saying, is 7 less than 24? But if we're not careful and we evaluate this, we treat this operator as tightly binding, then it's going to evaluate this 2 is less than 6 first and return a 1, which doesn't really make sense. So we need to make sure that we bake it into our grammar such that these comparison-based expressions have the weakest precedence. And we know that we get the weakest precedence by moving things further up in the syntax tree, in the parsing structure. And we know we did that by baking in the rules to be at the very top. So now, we're going to have a new rule above expression, and I'm just going to call it like C expression. It means that it's an expression which supports comparison. And what that's either going to be, it's going to be an expression, and then after the expression we're very familiar with, and now to add support for this greater than or less than sign, we're going to say, okay, after you have one expression, you can have at most one either less than sign or greater than sign. And if you have that, then you have to have another expression afterwards. And I'm going to add one more piece of syntax that I don't think we've seen before, which is the question mark. Question mark means it's optional. So let me use correct parentheses. So we're saying for our new type of expression that we're using is called a C expression, which supports comparison. And it's either going to be a regular expression that we've seen so far, and that's all, or it's going to be an expression followed by a less than or a greater than symbol, followed by another expression. And this question mark means that this whole thing is optional right here. So, if we just had 5 plus 3, that's still a valid expression. So that means that when we parse things, the only way you get this less than or greater than sign in the parse trees if they're at the very top, where all the additions, multiplications, subtractions, and divisions happen below it in the parse tree. And we also know that, intuitively, you should only be allowed one of these operators. And so that's why I'm we don't want to support 1 less than 2 than 3, because that's more than one expression happening, more than one comparison. And so that's why I'm using this question mark sign, which says it's optional, but you can only have 0 or 1. You can't have any number of these. So that way we can only support either an expression like the number 1 literally, or an expression like 1 less than 2, but not 1 less than 2 greater than 3, because that's not really an expression. We support one of these operators. And then similarly, you'll see, if you think about this, that we need to update our factor. We don't need to update our factor term, because if we updated factor, where this term right here, where it points back to an expression, to use a C expression, then you could game it to have multiple comparisons in a single expression. Because what you could do, if I mapped that expression, I was just on the C expression, is I could do 1 less than 2 in parentheses, greater than 3. And that's still that's not something we want to support. Only for an expression, you can only get one of these things. And then what does need to change is that in a statement, if we're using an expression statement, we'll say, for now, you can use a comparison expression. So that's the only place where you can use an expression. If you're defining a variable, we don't support this greater than or less than sign. It has to evaluate to just a literal number. Or if you're updating a variable, we'll just say for now that it has to evaluate to an expression with no comparison in it. That's up to us to decide. We could allow it. We could let our language be really flexible and say hey, you can assign variables to a comparison expression, but then the programmer themselves needs to know that under the hood, it's just going to evaluate it to a 0 or a 1. I'll leave that alone for now. So then our parser, we need a new function called parse C expression. We have a private function, and it's to be called parse C, this comparison-friendly expression. And this is going to return an expression itself. And let's see what happens. First, it's always going to expect at least one expression. So let's get that first expression. Then, if there's no comparison afterwards, we're done. But we should check, after this expression, is there a comparison sign, a greater than or less than sign. So if we can match a token type of less than or a token type of greater than, then we should pull off the operator. We should figure out if we saw a less than or greater than. So I can get that token that we just skipped over by calling this previous. And then I'll parse another expression, because that's the right-hand side of the comparison operator. And then I will say if we did enter this block, then our final expression, we have two different expressions. We need to join them into a binary expression. And the root of the binary expression is going to be either a greater than sign or a less than sign, depending on what the person put in their program. So I'll just say working expression. I'll reassign this variable is a binary expression, where the left-hand side is whatever we parsed first. Then we're going to feed in the operator, which is a less than or greater than sign. And the right-hand side is going to be equal to the second expression we parsed. And then out of here, we just return that working expression. And so if we never end up entering this if statement, we'll just skip over it and return the single expression we parsed out. So that should make sense. And then our parse expression statement, because the other thing we changed in this grammar was for the expression statement, it now no longer parses a regular expression, it parses this C expression. So I need to go ahead and update that as well. So instead of calling parse expression from the parse expression statement function, we'll call parse C expression. And again, we could have updated all references to parse expression to parse C expression if we wanted to support that in our programming language. I'm just going for the approach of the fewest changes possible to paint the idea of, hey, we can support comparison operators in certain types of expressions. And so the last thing, that's everything we need to do for our parser, is we need to hop over to the compiler because we define these two new instructions for our machine, the greater than instruction or the less than instruction. So our compiler, when it's translating and sees a less than or greater than sign in this binary tree, it needs to emit that instruction for the operator. So in our compiler, we have this function that we built earlier, and now you can see why I pulled it into a separate function. It's just so easy to jump to. This function instruction for operator. So if we have a statement 5 less than 6, the parse tree will be a binary expression type where the operator is a less than or greater than symbol, and then the left childs are the two expressions we're going to be comparing. So now we just need to say if we have a token type of less than, if that's the operator at the root of some subtree, then we spit out the native less than instruction that we just defined for our machine. And if it's a greater than, then we spit out a greater than instruction. Cool. And so I'm going to make the claim that this should be everything we need to do to get this working. So let me hop to the main. Actually, let's just like run what we had previously and see if it even compiles. So I went through that pretty quickly. Okay, we have a issue on 77 of the Lexer. Current character is the word I should be using, not current token. And do we have an issue? Can't tell. Oh no, okay, everything works fine so far. So we haven't changed anything there. But now let's go ahead and try this thing out. So let's make a new program, and all we're gonna say is, let's just start with something really simple. 1 is less than 2. This is true, so I'd expect that at the end of this program we have just a 1 on the top of the stack, because that represents truth. Ah, shoot. Oh, I forgot a semicolon. See, that's the compiler catching syntax errors in our program, and that's cool. It means we're recovering against bad input in our compiler, which is something a compiler is supposed to do. And so we see this source 1 less than 2 spits out a single expression statement, our parse tree, and it's a binary operator. So we have at the top of our tree, our single node's a less than operator, and the two children are number literals 1 and 2. And so to evaluate this, we see that it pushes the operands onto the stack, a 1 and a 2, and then it emits this less than instruction. And so if we had some machine, which we do, I already updated the simulator in the code before I cut to this video, our machine, if it sees a less than instruction, should pull the 1 and the 2 off, compare them, sees that the 1 is indeed less than the 2, and should spit a 1 onto the stack to represent truth. And that's what we're seeing right here. And so if I switch that to a greater than operator, I'd expect to see a 0 on the top of the stack. So if I said 1 is greater than 2, oops, and run this, I should see a 0 on the top of the stack. Cool. And let's go ahead and try a little bit more of a complicated thing. So let's say let x equals 5 times 2, and then c is x times 4. So that's 5 times 2 is 10 times 4 is 40, less than 10 plus 20 plus 40, which is obviously bigger than 40. So we'd expect a 1 on the top of the stack here. Oh, and I think I forgot a parentheses at the end of that. I did. Or a semicolon, sorry. And I can see that we get a 1 on the top of the stack. And so then the other thing, because I didn't update in our grammar, the other places where we had expression references, I didn't update them with C expressions. So if I come over here and try to do something like this, like if I try to do 5 less than 4 less than 4, so if I just did 5 in parentheses is less than 4, this is valid. And I just need to add a semicolon, which I keep forgetting to do. It's valid, the semicolons just don't really do anything. 5 is less than 4, so I'd expect the 0 on the top of the stack, which is what I see. But if I try to do a comparison in here, so 5 is greater than 3, because if I hop to our grammar, because I made the conscious choice right here to say that a factor term, if we have an open parentheses, can only map to an expression, not a C expression, there's no way for this expression term, i.e. what comes inside of the parentheses, to ever have this terminal greater than or less than up here. So that was a very intentional choice, because now if I run this program, it should give me a complaint. Yep, and so that looks good. Similarly, I said, I don't want us to be able to assign variables to the result of an expression that uses comparison. So if I say let x equals 5 plus 4, we're saying, just for now, this could change, and it will change if we were to expand our programming language more. All of our variables are going to be numbers. So we want to try to avoid someone, even though under the hood we're representing these truths, the true and falses with numbers, we want to be careful to avoid someone trying to accidentally or unintentionally capture a true or false into a numeric type of variable, then this should fail, and that's why I didn't change the grammar there. So, did I put the semicolon on? I did put the semicolon on this time. Nice. This one should also complain. Cool, so that also complains. Okay, sweet. So let me go ahead and commit what we have right here. And we'll say added basic support for comparison of integers. And now we can actually proceed to figure out how we want to go ahead and get this if statement in here. Okay, so this is where things start to get cool, because I really like the if statement, because we've seen like 3 times in a row, we know the traversal of what you need to do to add some new language construct, but this one's slightly different. It's not just adding a little bit of syntax and then using the same set of instructions under the hood we already had available. We are going to add a new instruction, but the way we deal with that instruction is also fundamentally different than the types of instructions we've added so far. So the syntax we're going to go with is actually going to be similar to what Kotlin uses, just by choice of myself. We could have gone with whatever, but I like this idea of the word if, and then in parentheses you have some expression. we'll use a C expression because we want comparison to happen, to be supported. That's actually why we just added the greater than or less than sign, was specifically for the expression in determining if an if statement should be entered or not. You have parentheses wrapping this expression, then you have curly braces. And inside those curly braces is any number of statements. And if the C expression that we parse and evaluate is greater than or equal to 1, we interpret that as true, so we will then generate the code to evaluate all of those statements. If we don't, then we need to skip over all those statements and evaluate the next statement in our program. So far, the machine we've built executes instructions top-down. Our compiler spits out a list of instructions, and our computer is just intended to read them top to bottom and execute them, and it just works on the stack. All those instructions are doing is, for the most part, stack operations. So some manipulation of either adding a number to the top of a stack, or performing some arithmetic with some value that's on the top of the stack, or moving between a stack and a local for the case of variable usage. We're going to need to break out of this paradigm. We're going to need to add a new instruction to our machine's instruction set that we're compiling down to that lets us jump to an arbitrary instruction address. So right now our compiler will spit out a series of instructions, and where's my mouse? There. So these instructions, this first instruction we're just say is at address 0, then this second instruction is at address 1, third instruction is at address 2. We're going to be using 0 indexing for instructions. But basically, our computer's going to have to keep track, it does already keep track of what instruction is currently executing. So it starts off, it'll look at whatever instruction's at address 0, execute it, and then increment its counter to address 1, and then it'll say, okay, now I need to execute whatever instruction is at address 1. And it just keeps doing this thing where it'll look up the next instruction to execute it, and then increment its counter by 1. And so that has the effect of just running top to bottom down our program until we reach the end of the set of instructions. What we're going to want to do is add this new function, this instruction to our instruction set called jump. And jump will let you jump to any arbitrary address in memory. So instead of all that instruction will do when the computer executes it, it'll do nothing, but its counter that it's using to keep track of the next instruction it should execute, it'll just update the counter to whatever the argument to that jump instruction is. So if the very first instruction in my program at address 0 is jump to 5, then all that's going to happen is the computer will start at address 0, look up the instruction, it'll see that the instruction at that address is jump 5, so it'll just set its counter to 5, the program counter, which keeps track of the next instruction to execute, and then continues. And so then that instruction's done, then it'll do, okay, now it's time for me to execute the next instruction. And so it'll say, let me go look at my counter. My counter says 5. 5 is the address of the next instruction I'll execute. So it'll jump to address 5 and work from there. So we skip through addresses 1, 2, 3, and 4 in that process. So jumping will always jump. We're going to add actually a conditional jump, because we're going to eventually use jump to maybe skip over all the statements that are in the block of the if statement. And we're going to want to skip over them if our condition's false. So I'm just going to build this using a jump if false. We could have added another form of conditional jump, like jump is true. But let's go ahead and add a new instruction to the machine. And it's going to be called jump if false. So data class jump if false. And it's going to need to be a data class because it has an argument. This instruction has an argument. It's not taking anything off the stack, or it will. It'll actually, what it'll do is it'll look at the top item on the stack, it'll pop it off. If it's a 0, it'll jump to whatever address is specified by this target parameter. Otherwise, it'll just keep working, and that instruction will be effectively have done nothing. So it'll skip to the next instruction. So that's the new instruction we're going to add. Now, let's go ahead and formally specify our grammar that we're going to be using to add support for the if statement. So now, in our types of statements, we have a variable declaration, we have an expression statement. I'm actually going to change this expression statement from C expression back to expression, because Actually, we can just keep it. Doesn't really matter. That's semantics. Or we have a variable update expression, a variable update statement. The next thing we're going to add support for is an if statement. And so that'll be the syntax that we just discussed is the word if, then an open parentheses, then a C expression. We're using C expression because we hope that the user uses some comparison. They could just simply put if 5, and since 5 is greater than 0, it'll evaluate to true. But it's up to the user. That's a semantic constraint of our language. We're not going to enforce that it has to have a less than or greater than sign there. We'll just say, hey, like that's what it's intended for. If you want to use it for something else, that's fine too. Maybe if you just wanted to check if a variable is greater than 0, then you could just put the variable name in as your C expression. Rather than, you could say either the variable name or variable name is greater than 0. Either works. Then after this expression, in the close parentheses, we'll have an open bracket. In the open bracket, we're going to have statement start, so any number of statements. And we'll know, because we'll just keep checking, while we don't read the next thing, which is a close bracket, we should expect another statement. So we'll call the parse statement. And so that actually means you can have an if statement within an if statement if we've done this correctly. And then lastly, like all other statements, it has to end in a semicolon. So now the first few steps will be easy. The new part that we're going to see that's a little bit different is in the compiler. But the Lexer and Parser is pretty straightforward. So for the Lexer, we have a few new tokens actually. We have the if keyword, which is a new token, and then these curly braces, which are new tokens. So let's go ahead and jump over to our token representation. And we're going to have a open brace, a close brace, and then an if. So these are the new token types we'll support. Then what we'll need to do is hop over to the Lexer. And in our list of one-line checks, we will just check for these new characters, these new tokens we just added. So if the literal, or if the current character is a open brace, then we'll just add a open brace token. And if it's a closed brace, we'll do the same thing, but a closed brace token. And then for the if, that's a word, so we're going to have to hop up to where we parse words out, and if just gets added to the list of things we check for. So if the literal word that we parse out is an if, we're not going to return an identifier with type if. We're going to add a token whose type is if. So that's all we need to do for the parser. Same thing we've been doing previously. And now, that's all we need to do for the Lexer. Now before we can build the parser, we need to add a new data class that represents this if statement we have built out. So I'm going to hop over to the statement class that we're using to model our statements. And I'm going to add a new one. And it's going to be called an if statement. And so what this is going to take in, to represent an if statement, we need the condition that chooses, and that's an expression that'll choose if we're going into the block of statements or not. And then the body is what we usually call what we conditionally execute. The body is just a list of statements. And itself is a subclass of statement. So that's the data modeling. Now we can update our parser. So if I jump back to the parser, what we need to check is whenever we reach, if we're parsing a statement, did I skip past my logic? Ah, yes, I did. Parse statement. So if we're parsing a statement and we see the word if, then we are parsing an if statement. So what I'm going to do is if we match a token type of if, then I'm going to return a call to this new function we're going to make, which is a parse an if statement. Following the same practice of each non-terminal, and we haven't really spelled it out in the grammar explicitly, but we could have. We're just going to follow the same practice though, where each non-terminal rule we'll make a separate function for it, and so they can call each other. And we have this thing that we call mutual recursion. So I'll make this private function for parsing an if statement now, and that's going to return a statement, and the type of statement it will return is precisely the if statement we just defined in the statement class. So for a statement, the very first thing we would want to do, we've already consumed the if, so we want to consume the open parentheses. And if we don't, we'd say expected after if. And after we've consumed the open parentheses, we need to parse out the expression, and that's the condition. So the condition is an expression itself, and we get this by parsing an C expression. And then after the expression, we'll expect the close parentheses. Oops. Okay, and then after the close parentheses, we expect an open brace. And then what we're going to have inside the open brace is we're going to keep checking. While the next token is not the close brace, that means we should have a statement to parse. So while the next token is not a close brace, and then I'm also going to be careful to check that we're also not at the end. In case you could have a bad program where the program has the start of an if statement and then nothing afterwards. There's no close brace, but it runs out of statement. It runs out of statements, and we should crash in that case, but we should be aware of it. So I'm just going to check that we're not at the end. Then I would parse a statement, and we need to keep track of all the statements that we have that end up being in the body. So I'm going to say the body is going to be a mutable list of statements. And it's empty to begin with, but each time we look at the next token and it's not a close brace, that means there's another statement. So we'll just add it to body. So to body, what we'll add is we'll call parse statement. That'll pull up the next statement and it'll add it to this list. Eventually, we will find a close brace, or we'll be at the end and we're out of here. So then now we should just expect that a close brace is there, so we'll consume it. Okay, and now lastly, the last thing we need to do is just return the expression in the body as an instance of an if statement. Okay, so that's all we need to do for the compiler. So, sorry, for the parser, apologies. We're going to jump to the compiler, and here's where things get a little interesting, because we're going to learn about a new concept called patching, which is so simple once you understand it, but so cool and powerful in my opinion. So, when we're emitting all the instructions here, we have this function called emit. It's going to take in a statement, and one of the possibilities is that our statement now is this new thing we defined, which is a if statement. And so here's how it's going to work. Basically, we have a condition. We're going to want to go ahead and evaluate the condition. So that part's easy. All we do is emit all the instructions that are necessary to evaluate what comes inside the parentheses. So recall that the machine just is working top down. So if we emit all of the instructions needed to evaluate the condition, then by the time our program runs through those instructions, we have at the top of the stack will be a number, and if it's 0, we interpret it to be false. If it's positive, we interpret it to be true. So what we'd like to do is, if we look at the top value on the stack and it's false, we'd like to jump and skip past all of the statements. Otherwise, the next instruction will just be all the instructions for all of these statements. The tricky part is we are wanting to use this jump if false, but jump if false takes in an argument because it needs to know where to jump to if the expression is false, or if the top value on the stack is false in our case. And until we spit out all of the instructions for all of the statements in the body of the if statement, we can't know where the last instruction will be. So pretty much we'll have, like, if I just... Oh god. There we go. So basically we'll have some instructions before the if statement. Then we'll have instructions needed to evaluate the condition of the if statement. This is just the ordering of instructions in our program. Then we'll have a jump if false instruction. And so if we get to here and we look at the top thing on the stack and it's false, then we should skip what comes next. And what are we skipping over? It's going to be the instructions for each statement in the body of the if statement. So everything that comes between the braces, we'll spit out all the instructions for that, and then afterwards, here is the target jump location. So the issue is we're going to write this jump if false, but until we spit out all the instructions for evaluating each of the statements in the if statement, we can't know how many slots in the memory, how many instructions that will take until we actually evaluate all of them and emit the instructions. So what we're going to do is this thing called patching, where we know that right here we're going to have a jump is false, and we don't really know where we're going to jump to yet. So we're just going to write a random number. Then we're going to go ahead and emit the instructions for every statement that appears in the body. Then we're going to check how many instructions have we used so far. So like, what is the next free instruction address? And that is where we should jump to, because we know from here to that address, all of those are all the instructions that we don't want to execute because we did not match the condition. So what we do after we emit all of these instructions is we patch this instruction right here, where patching is the action of updating the argument that we originally used the dummy value for to the correct argument. So it requires us to retroactively change things, and that's fine because this is just the compilation stage. So we guarantee that by the time the compiler finishes we guarantee that by the time the compiler finishes all of its work and emits all the instructions, that everything is correct. It's a correct one-to-one representation, correct one-to-one translation of our source program in TinyLang to the instruction for the instruction set we're compiling down into. But in the process, we can do whatever we want. So we can omit wrong instructions if eventually we get back to the right instructions. And that's exactly what patching is about. I'm going to keep this comment in here, just I think it's useful if you want to read the code yourself. It's a little bit different than everything we've seen so far. So basically, we've been keeping track of all the instructions so far, just sequentially, in this list of instructions. So I know that if I emit a jump if false instruction, it's going to appear at the last index in the list of instructions we have so far. So let me just capture that index. So the jump instruction index is a number, and it's just going to be the number of instructions we have so far because everything's 0 index, so it's shifted by 1. So when we come back to patch, we'll know, hey, this is the address where a jump if false instruction is, and that's the address of the instruction you should update. So then we'll just emit this jump if false instruction. And we don't know where we're going to jump to yet. That's the whole concept of patching. So we're just going to specify a random number. We could literally say whatever we wanted to. Could say 9s, could say -1. We can just leave it at 999. It doesn't matter. We're going to replace it. So it doesn't matter what we put there. Now, for each statement in the body of the if statement, so for each statement in the body is a list of if statements. So I'm going to use a for each loop. I'm going to say, for each of these body statements, which itself is a type of statement, emit the instruction for that statement and add it to our list of instructions. Then
figure out where we are. So where we are is after we've spit this out, what is the next available address for instruction to go? And that's where we'd like to jump to. So then I can say the real jump location is wherever we are now. And so what this means is I can then go to our list of instructions, and I'm going to revisit the position in that list where we originally put that jump instruction, which is jump instruction index. And what we're going to do is we're going to replace it with a new jump if false instruction. I typed that right. Jump if false. And we're going to jump to the real jump location now. And this is the concept of patching. And I think it's really powerful because it's so simple when you see it, but it's so counterintuitive in the moment. How can you know where to jump to? So you have to omit this jump instruction, but you don't know where to jump to because the number of statements you have to omit instructions for is of an unknown length. So you can just figure it out by going ahead and saying, hey, I'll write a dummy instruction here just to reserve that spot in the list of instructions for our target program, and then I'll revisit it once I actually have the answer to that. And so this is called patching, and that's very powerful. So if I've done this correctly, everything should work. So what we can do is jump back to the main file, and we could give it a program, but we also want to make sure that we have support for our pretty printing if we have a if statement. So let me go ahead and do that. Print the condition. And then we will print each of the statements in the body. Okay, so the first thing I'm going to do is actually not change our source program to make sure that everything works. This is a valid program, let x equals 5. I see some compiler errors. My mouse will move. Unexpected on line 48 of the Lexer. I forgot to use the else if here to continue the chain of if else's. A few more. Lexer 61. I should be using single quotes to match a character. That's just a nuance of the Kotlin programming language. A string is any number of characters. A character is a single letter, or special letter here. So you differentiate the two with a single quote versus a double quote. Only one other issue. Line 45 on main. I've been pleasantly surprised. I definitely made some mistakes here. I thought it'd be a lot rougher in this video, so I'll take it honestly.
condition. Oh, I need to print these statements condition. Okay, now okay, nothing crazy happening. This program works fine, and nothing's actually in the stack afterwards. That's fine because we evaluate 5, and then to write it into a local, the store local pulls whatever's on the stack and writes it, so our stack's empty. Let's do something interesting. So let's try to take advantage. So let's say, let's define x to be 5. Then let's say, if x is less than 5, let's say update x to x plus 10. And then let's put x on the top of the stack so we can see what its value is. And this also has to end in a semicolon because the if statement is a statement itself. So now, let's see if this works. I'm a little concerned. Oh, unable to parse a factor. Okay. Let's see. So if we trace this, I'm going to pause the video and see what the issue is, just so I don't ramble on my thinking. I actually think I know exactly what the issue is. I think in our logic for parsing the if statement, I don't think we correctly asserted that there should be a semicolon at the end of the if statement. And so if I jump to parse if statement, yep, I checked for a close brace, but I don't consume a semicolon to end the if statement. We also, for what it's worth, we didn't need to add this requirement. We could have made an if statement, because it already ends in a curly bracket, and that's a unique token. That could have been a clear differentiator or clear marker that it's the end of an if statement. I like the consistency of just ending all of our statements with semicolons, so I'll just keep that in here. But I think that was our issue. Okay, sweet. So, this is cool. First, let's just check the outputs. We're saying if x is 5, then take if x is less than 5, update x to x plus 10. So we're actually not going to enter that block. And so then when we print x, x should just be 5. So that looks correct. Let's go ahead and verify the other condition. Let's set x equal to 4 so that we enter the block and see what happens. Okay, so now I'm seeing x starts with 4, it's less than 5, so we enter and execute every statement in the curly braces. There's only one statement in the curly brace, and it says update x to be 10 more than what it currently is. So that evaluates to 14, and then the last statement is just putting x onto the stack. And so that's exactly what we're seeing happen here. We can see that we have a variable declaration, then an if statement. The condition is a binary less than x and 5, and the body is just a single variable update. And to evaluate the new value for x, we do a binary plus of the current value for x, which is 4, and then a number 10. And so I can see if I look in, this is the instructions for the let x equals 4. Then these two instructions right here are getting ready. Sorry, these three instructions I can just say are evaluating the condition of the if statement. So it's putting x onto the stack, it's putting 5 onto the stack, and then it's invoking the less than operator. And now we can see if the condition's false, we'll jump to target 10. So if I count, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the condition's false, we skip to this instruction right here, and that's the instruction for just putting x onto the stack. So you can see we correctly have the instruction encoded in there to skip over. In our case, these are the instructions that represent the body here. So in our idea of patching, we had our list of instructions, we had this already in the program, we put a jump is false with the target as 999 as a placeholder value. Then we
evaluated and admitted all the instructions necessary for the body of the statement, which is just used for, and then we checked how many statements did we actually emit, or how many instructions did we emit, and then we went back and patched this to be 1 plus that. So this last instruction in the body was target equals 9, the 9th index, or sorry, the position 9, and we're saying we're going to skip to the next one after that, which is position 10. So that looks cool, and that's really cool. And then the very last thing we should do is we said that the body of an if statement could have any number of expressions. So let's just go ahead and add one more. Let's say we could also do update, or let's say we could do a variable declaration. Let y equals 5. And so we can do something cool here, where we could return x plus y. And so let's go ahead and run that. And what I see is I expect, since 4 is less than 5, x becomes 14, 5 is 9, we return 19. But let's look at the interesting case. So the brackets, everything that happens here may or may not execute. So what happens if I don't execute this and then get to this final statement where I have x plus y? Well, x just evaluates to 4, since the very first statement in the program was saying let x equals 4. Y, if we skip out of this if statement, if we never match that condition, there is no value for y. So this program is actually invalid, and we can see what happens by just changing this. Let's make this a 9. And basically, modern programming languages would not even let you run this program. The compilers would be able to see y is not defined in every possible output path of the program, therefore they won't spit out any code. In our case, I'm being a little less restrictive here. I'm not covering every corner case with our compiler. The code will compile because the compiler to generate all the instructions will have to emit the instructions for every statement, and one of the statements is a variable declaration for y, and you can kind of see it's using slot 1 for y. So because the compiler just works top down for all the instructions to figure out what it might need to emit, independent of what actually gets emitted, it does reserve slot 1 for y. And so when it sees that x plus y statement, it says, hey, I already have evaluated y before in a variable declaration statement, and I used slot 1 for it, so I'm just going to emit slot 1 here. But it's not actually picking up on the fact that that variable declaration for y might not actually get hit. So the compiler itself works fine and spits out these instructions, but our machine that simulates this is going to crash with saying undefined local slot 1 because nothing has ever been written into that local slot. And so that is pretty cool. So first off, let's pat ourselves on the back. We've added so many features to this language. We have the ability to evaluate complex mathematical expressions. We have the ability to define variables and update them. You also have comparison of expressions. And we also now have conditional code that may or may not get executed based on the result of some other expression. Something that we're missing here that our language doesn't have, that other languages have, many languages have, but not all of them, is the concept of scopes. And scopes are interesting. So pretty much right now, our programming language that we define, all variables are accessible anywhere. So if you define a variable, what we just saw in our example is if you define a variable within an if statement, that variable is accessible even after the if statement returns. And we saw how that can be very risky because you don't know later in the program if you're referencing some variable, if it was actually defined or not, because you may or may not have entered that if statement. So many programming languages have the concept of scope, where inside these curly braces, it'll open what's called there's a global scope. You start with one scope when you run the program, and all variables live there. And then every time you open a new curly braces, it's called a block, is what I called it earlier, it'll open a new scope. And in that scope, any variables that you define are only valid and usable in that scope.
and then when you pop out of the curly brace and end that scope, it throws away all the variables that belong to that scope. So then what you have is when you're looking up a variable, you'll check the current scope you're in, and then you can check the parent scopes and keep going out. Because remember, you could have if statements in it, if statements. So there's a chain of scopes. And if you're looking up a variable and there's no scope that has that variable, then you have an undefined reference. And so that actually enforces safety and protects against the degenerate case I pointed out in this example, because right here, in these braces, you would open up a new scope. The variable declaration statement for y would create a new variable in this scope for y. And then when we hit this close bracket and pop out, that scope is gone. So therefore, when we evaluate the next statement, we know that this x belongs to the global scope that was created when we first started the program, but there's now no active scope that contains y, and the compiler will see that and it'll crash because it knows that y was conditionally defined, so it shouldn't be available everywhere. And that's pretty powerful. That's also why in certain programming languages, Kotlin included, if I have a variable outside of an if statement, or like a variable defined somewhere, and then within a block you can define a variable the same name, and it won't yell at you. The compiler will say this is valid, because every time you're opening a new block, it creates a new scope. So if I have variable x in my global scope, and then I enter an if statement, and define a variable the same name x, that variable x lives in the inner scope that's associated with the if block, not the outer scope. And because of that method I talked about earlier, where you would just look up a value, you would check the current scope and then keep walking the parent scopes, it would check the innermost scope and see, hey, does this variable x exist? And it does, because you just defined it in that scope, so it points to that local x, not the one that was defined before you entered that block. But that's a little bit of a digression. But this is really cool. Our programming language now is not just a toy, it has actual conditional execution, which is really powerful, and it's getting to be more and more complex and more like real programming languages. I should also... Oops. What is happening? I should also commit what we have so far. And I silently updated the machine so it can evaluate this conditional jump instruction. So let me go ahead and add support for conditional if statement. Sweet. And isn't it crazy? That's 68 lines of code added, 7 deleted. So few lines of code just added something so powerful to our compiler, because the baseline work we did to get the evaluation of mathematical expressions carried so much of the structuring and foundational work that it's not trivial, but it's significantly easier to then go and add new features to our language. So we've added more and more features to our programming language, and it's definitely become not just a toy language. It still is somewhat trivial compared to the languages you may have worked with out there, but there are enough features where you could write sufficiently interesting programs now. And so we talked about if statements, and that's like conditional execution, meaning based on some condition, i.e. what was ever in between those parentheses, we may or may not evaluate some code. And so there are two other types of conditionals we talk about, which are called while loops and for loops. And pretty much the if statement we saw makes one pivot point. So it checks one condition. If that condition fails, it skips past a series of statements. There's another type of conditional called a loop, where it'll keep doing some set of instructions while some condition holds true. So the most common of these is called a while loop. We've probably used it in our compiler here, and we've used it in the Kotlin side of things to build out our compiler. And I could add that in here, but we're not going to learn anything new, so I'm actually going to choose to skip it. The foundational you've seen of being able to jump over code is not really different. You could imagine, and I'll actually leave that as an exercise, if you want to extend this language, to go ahead and add support in for while loops. And for loops are just a different way of expressing what compiles down to a while loop. So if you program before, anything you can do in a for loop, you can do in a while loop. So I'm actually going to skip over those, and this video is getting longer than I expected it to, but there's one thing I want to add that I think is very different than everything we've seen so far, and that's called functions. And you've seen me use functions all throughout the implementation of this video on the compiler side, but let's actually try see how we can build that into our language natively. And we're going to take a very simplified view of functions. If you have a background in programming, you will know that functions get complicated very quickly, and programming languages that are out there allow for a lot of complexity around functions and what they can and can't do. And that's actually, I think, where we start seeing big inconsistencies between programming languages. Like, most modern programming languages have support for everything we've described so far, but then you get up to higher order languages, and for example, some programming languages will let you assign a function to the result of a variable, and others won't let you do that. And so, like, I'm not going to get into the weeds because I'm making the assumption that there's not a deep background in programming needed to watch this video. But if you have programmed in enough languages, you'll know that the semantics of how functions behave between different languages is not consistent at all. And so we're not going to try to go for the most complicated approach. I'm actually going to take a very simple approach to functions. Our functions are going to be pretty stupid in the grand scheme of functions in modern programming languages, but it should help paint the picture of how we would actually add this to our language. So I had a notes file earlier in this video. Yeah, it's in a folder called notes. So I'm going to make just one more notes file, and let's talk about the functions we're going to build before we actually jump into the code. Okay, so we've seen functions declared in the Kotlin Programming Language. I kind of like how they're declared there, so we're going to keep something that looks somewhat similar in our programming languages. So we're going to say functions can only be declared at the top level, and what that means is you cannot declare a function within another function, and you couldn't declare a function like in an if statement and hold on to it. Like, one of the statements, we said like our program is a list of statements. One of the new statement types will be a function declaration statement, and that's how you'll define a function. But from any other way to get a statement in a program, you cannot define a function. So an example of that would be the if statement we just executed. We know that if you match a condition, we executed some number of statements. The statements in an if block, we're not going to allow you to declare functions there because it's going to complicate things quickly. And that's not a top-level declaration, because that's not the series of top-level statements that make up the program. That would appear deeper in the syntax tree when we parse things out. So it's not. That's how we make the distinction between top-level and non-top-level. So the syntax will start with the literal word fun, which is just short for function, and then we're going to say you can name a function, exactly what we saw in Kotlin, and then we're also going to say a function can take in any number of parameters. If it doesn't need any parameters, it doesn't need to take it in. And I'm not going to explain too much about functions because you see me use them all throughout this video, so I'm only going to explain how we're going to adopt them for our language here. So let's say you can take in a number of parameters. And they're going to be in a comma-separated list within parentheses. After that close parentheses, we're going to expect an open bracket, and then a close bracket. And what comes in between the open bracket and close bracket is going to be some number of statements. We'll use like statement star. You could have 0 or more statements. And we've seen in our implementation of the compiler that a function does not actually have to return anything, but it can pass a value back to whoever called it. For our case, we're going to just require that a function has to return an integer back to whoever called it. And the reason we're going to do this is because eventually when we update our context-free grammar, the way you're going to call a function when we bake it into the context-free grammar is it's going to be a type of expression. And so every expression we've worked with so far evaluates to a number. Even like the true and false, like the less than or greater than signs, we've encoded that such that they return numbers. So if you want to do like let x equal some expression, and that expression is a function call, it would be really complicated if we needed to check like, hey, does this function actually return a number or not? So for the sake of this tiny lang programming language, we're just going to say every function has to return a number. And the way it's going to do that is it is going to have to use this return keyword, something similar to what we've seen in Kotlin, in our Kotlin compiler side of things. we're going to require that the programmer of the language, when specifying a program, needs to make it explicit that they are ending the function at some point by using a return keyword, and following the return keyword, we'd expect an expression and a semicolon to end off that statement. And so if someone calls this function with name, passes in the correct parameters, then they should get back something, and that something is going to be this expression right here. How we get that something is going to be up to whoever's programming the language. So a simple example of a function might be like add, and let's say it just takes in a and b, and because every variable in our language is a number, we're just going to assume that a and b are numbers. We're not going to do any strict enforcement that like you're not passing in like a function call where a is like 1 less than 2, because technically it could work because it evaluates to a number, but we'll leave that out for now. We could be a lot more rigid and a lot more prescriptive, but I'm just trying to paint the picture of how we would actually get about there. So I don't want to spend too much time diving into the nitty-gritty and covering every single piece of exceptional behavior or find ways to explicitly break the language. But it is a good exercise, and if you are developing a real compiler, this is the exact type of thing that you need to have an attention to detail for. So I'm not going to trivialize that. I just think for the sake of this video, I'd run 100 hours if I tried to make sure I explicitly call out every possible edge case that there is. So our simple program of add might just be no statements and a simple return a plus b. And a plus b is a valid expression. And the other interesting thing is within this body, the body being the list of statements that composes a program, you cannot access any variable except for the parameters that you were given or variables that you declare. So let's say I had a program, or let's say before this I had some like let x equals 5. Then in here, if I tried to return x plus a plus b, this would crash. This function, when you call it, is not going to have any understanding of the environment or the world outside of it. It's going to get its own little isolated piece of a machine where all it has access to are the parameters to start with, or if you define any variables within the body of the function, then it does have access to those. So if I said like let x equals a plus a, and then I returned x plus b, this would be valid. And so if I call, add of 5 and 3, then this would be a valid program. But then the other thing is all the variables that are defined within a function get thrown away when that function returns. So pretty much whenever we invoke a function, it gets its own little separate environment, and it can do whatever computation it needs to do, or a series of computations. When it's done, it hits a return statement, and our machine will have to take that value, throw away all the scratch work that the function did and all the variables it defined, and then return that value by putting it on the top of the stack because it is simply a type of expression. So we said that the body of a function can be just a list of statements, and those take on the form of statements that we're already comfortable working with. So you could actually have an if statement part of here. So I could say if a is less than 0, maybe we just want to return right away, like return 50. Then this would work. But you have to guarantee, we're going to say that like a function has to hit this return keyword somewhere. So if you make it to the end of the function, there's not a return keyword, there's something wrong and it's not a valid program. So then let's talk about, that's defining functions. Let's talk about how we'd want to invoke a function. So we're going to make it very easy to determine, because we want to make things as easy as possible when we're parsing out in our parser file. If like I just say like add, then it's unclear to it's for us on the implementation with the compiler side, it's very tricky to know if add is the name of a function or the name of a variable. So we have to like peek ahead and see what follows add to actually understand what's happening. We're going to simplify this by saying if you want to call a function or invoke a function, you are going to have to explicitly say the word invoke. So I'm going to say invoke, then a function name, and then you're using open parentheses, and pass in expressions for each of the arguments. So if in the case of our add function up here, I need to pass in 2 items. But we'll just say it's, it's going to be argument 1 and argument 2. So a few things to remark here. If I'm calling a function, that function has to have been declared higher up in the program before we get there. So if you define a function later in the program, modern programming languages will actually recognize this and say like, hey, it's not defined before you reach this, but later in the file it is defined. In our case, our compiler, as you've seen, is just reading top down on the syntax tree. So if we reach a function we haven't seen previously, then we're just going to assume it's not defined. We're not going to try to read ahead and see like, did the person specify this later in the file, just because it's going to make things harder, and we're being somewhat lazy here. So in order to call a function, it has to have been declared further up in the program. Then, assuming that the function is declared, you must call it with the right number of arguments that it has in the function declaration. So our add function right here is defining 2 variables. So that means if we want to invoke it, we need to call it with 2 variables. And we're actually not going to do, we're going to parse, we're just going to find, we're not going to worry about the semantic correctness of the program. The parser is just going to get a parse tree. So if I called add with 1, 2, and 3, the parse tree is going to see that there's a function call, the function name's add, and there's the function arguments, there's 3 arguments, and it's 3 different expressions. And that's going to be a valid parse tree. So according to the context-free grammar, which we'll update shortly, this will be a valid program. But when we actually go to execute it and compile and translate it down to instructions, that's when we need to error out and be like, hey, you're calling a function that only needs 2 arguments, but you're calling it with 3 arguments. It's kind of unclear from the compiler's perspective what the use of that 3rd argument is, so it's just going to crash. The other thing is that function calls themselves are expressions, so you can use them anywhere that a regular expression is allowed. So, if I'm declaring a variable, if you read the context-free grammar, the right hand of this side is just expecting some expression. So I could say let x be the invocation of our add function with 1 plus 1 times 5 and 6. Or, yeah, 5 works as well. And so, I mean, our add function is kind of trivial because you can already just do the plus operator, but I'm just using that as sake of example. But the other thing to remark here is that the parameters themselves that you're passing in are just expressions. So you can pass in expressions here. The compiler will need to evaluate those before it invokes the function itself. So I believe this is a decent enough specification of our functions. Oh, there's one other thing I'd actually like to mention, is that a function is totally free to call another function. So if I declared another function called other function, and it takes in just 1 parameter, let's say, then I could actually return a plus some function invocation, because we already know function invocations are expressions, of add. So this other function is calling another function add, and it's just going to pass a and a. That's just an example. And this would be totally valid here. So functions are free to call other functions, but what functions cannot do is define another function as part of their body, because that's not top level, that's nested. It's belonging to a function. It's not one of the top level statements that we parse for our programs. So we've talked about functions cannot be nested. They cannot be assigned the variables themselves, but invocations of functions can. Functions only operate with integers as input, and it can only return an integer, and a function has to return an integer. And then the other interesting thing that is worth just restating is that functions don't capture variables. They can't see anything outside of the body of the function. So if I have defined a variable above a function, and in the body of that function, it has no awareness that that variable exists. So with that, that's a good enough specification for a function. Let's talk about how these are going to work. So what we're going to need to do for the language we're compiling down to is add a new type of instruction that is called, we'll call it call function. And so if you're calling a function, there's 2 things you need to pass pretty much. There's the name of the function you're calling, And then there's also the arguments that you're passing through. And so what we're going to say is that to call a function, you push all the arguments onto the stack, and then you will call this call function. And so with call function, you pass in the name of the function you're calling, but then instead of passing in the arguments themselves as instructions to the operation that we're compiling into, we're just going to say how many arguments we've put onto the top of the stack. So in our case, if I was to compile this program and we got to this line right here, then what I'd do is I'd evaluate arg1, because it's an expression, put that value onto the stack, evaluate arg2, because that's an expression, put that value onto the stack. So now I have on the stack, I have whatever was already on the stack, I have arg1 and then arg2, and then I'm going to emit this call function. And the two things I'm going to pass in is add, because that's the name of the function, and then I'm just going to put in the number 2. I'm not going to say, hey, here's what the values for arg1 and arg2 are. I'm just going to say, you're going to call this function, and this function is going to be called with the top 2 values that are on the stack. And so then what the machine that we're compiling down to is going to do is it's going to pop those off of the stack and then change the program counter that we talked about for the implementation of the if statement to be wherever the instructions for this add function are. And so then the last thing we need to bridge is, how does this add get our functions? Like, how are we going to compile that? And so what we're going to do is, we've been working with these locals that map out names to slots on this local. Our machine, when you call a function, is actually going to get its own new fresh set of locals. And so if I had local 1 assigned to some variable, local 2 assigned to this other variable, when I call this add function, add is going to get its own brand new set of locals. So local number 1 is not associated with any variable anymore. And that's why we're going to say, like, this add function can't see what's outside of it, because it gets its own new set of locals. And so how we're going to pass the parameters over is we're actually going to say the first parameter will be assigned to the first local slot, and the second parameter will be assigned to the second local slot. And then our compiler can then say, hey, like, if you reference A, we know that we already assigned A to the first local slot, and when you reference B, we already assigned that to the second local slot. And so then when you return out of a function, we clear all those locals we just generated and restore what locals existed at the time we called the function. And so that's kind of a mouthful, and we're going to see what that actually looks like when we implement the compiler. But this is pretty much, if you read into this because you get curious, it's alluding to the concept of frames. And so a frame would be, in our example right here, is we have a global frame right now where every one of our variables is assigned to some local slot. And when you reference a variable, we just look up in this table what number slot did we assign to this variable. And that's how we interchange it. So the programmer just says, I'm defining this variable x, and whenever I reference that variable x, you should look up whatever the value of it is. Under the hood, we're saying, okay, when they defined x, we assigned it to this numbered slot, and so whenever they reference x, we know we can just look at that same slot. And so when we call a function, we're actually not going to throw away all of those mappings. We're going to say, hey, that's a frame. The frame captures the state of the program at the time we call the function. We're going to push that aside, build a new frame which is fully empty, so our function add has its own little environment to play around with. And when add is done, we're going to take add's frame, throw that away, and then restore the frame we originally had. And similarly, we saw that we could have a function call another function. So pretty much this process can happen any number of times. So if I have a top-level code that calls some function A, then I take all of the frame of our program, which represents the mapping of all the variables that our program has used up until now. I move that aside. I take a new clean slate frame and use that for A. Then let's say A calls some function B. Then at the time that happens, I take all the frame for A, move it away, get a clean slate of locals, and give it to B. B does its thing. When B returns, I throw away that frame and restore all the locals that we had for function A. And when function A eventually returns, we then throw that away again and restore the global frame that we were using at the time we called the function. So pretty much whenever you are in the body of a new function, you get a totally new mapping of locals. And the way we pass parameters through is that we bridge the gap by popping the machine does this, we don't have to do this, it's in the specification of the machine. The machine will pop the number of arguments off the stack that's specified by the argument to the call function instruction we just defined, and it'll assign those to locals in the new frame for that function. And so then when it jumps to the function bodies, the address in the code where we put all these statements for the body of the function, that'll have its own clean slate where the only thing it knows at the first statement in the body of the function is all of the parameters that were defined. That's a mouthful. Let's go ahead and start the implementation now. All right, so let's start by implementing or defining, the new instruction that we need to support in our machine. So the language we're compiling down to is this abstract language that we've invented. I don't think we've given it a name or anything. And in order to support the function based on the specification I just outlined, and I should also pause real quick. I made a lot of shortcomings and assumptions there. This is intentional, and I know some of that might seem arbitrary, and I try to explain things as I go, but it ends up just simplifying a lot of the implementation side while still showing you the high-level architecture of here's how a compiler might implement a function in the real world. So a lot of things I'm choosing may sound arbitrary, like why does a function have to return a number? Like, why do we have to use the return keyword explicitly? And to call a function, why do I have to use the word invoke? These are all very things that might seem very odd, but when you actually go to implement it, you actually might not even be able to appreciate how much easier it is to have some of these explicit requirements, because it simplifies a lot of the work on the compiler, parser, interpreter side of things. So there's a reason for it. It'd be exhaustive for me to explain that for every single decision I make without actually just going and showing the implementation. So it's kind of it's difficult for me to order, but if it's too confusing, tell me. I'd love to hear that feedback. Even after you watch the next section, I'm very open to feedback. I want to get better here. But let's go ahead and hop into our instruction file. So these are all the instructions our machine supports. So we're taking in a program in text and we're spitting out a list of these instructions right here. And then we have this class called machine.kt that will simulate execution of these instructions for this real machine based on the specification we outlined. So we need two things here. The first is we're going to need a call function. And this is a new type of instruction you can emit. And we said the two things you need to specify to call a function is, number one, the name of the function you're going to invoke. And then the other thing is how many parameters is it going to use. And I'm going to call this arity for consistency with what you might see in other computer science classes or terminology. Basically, you can think of, in computer science, arity refers to, I guess, the number of arguments or operands something might take. So we've been dealing with binary, ARY is the suffix there, and bin means two. And if we were talking about ternary, it'd be if something has three. And so this here is used if we're calling a function, saying how many operators do we expect this function, i.e. parameters here, this function to expect. And so what we talked about is what happens when you call this function is it's going to look at this second parameter, the arity, and that tells the machine the top, if that number is 3, it means the top 3 items on the stack are the 3 arguments to this function. So you should pop them off and store them into in the new frame, new locals for the function to actually use. Rather than, it wouldn't make sense for us to pass through the arguments here because it's an unknown number of arguments that a function might take. And so that would require us to have, in our language that we're compiling down to, we're trying to make the operands for instructions that require arguments be as minimal as possible. And so it's easier to say, put the actual values of the arguments on the top of the stack, and then to jump to a function and call it, you use this instruction and just tell it how many items you put to the top of the stack, and it'll handle, the machine itself will pop those off and correctly assign them to locals for the body of the function to have references to. And then that's the call function. So this will let us call a function. The other thing we need to do is add a return instruction. So if you're in a function and you hit this return, then it means we should have taken, like, if I say return x plus y, it means I should have in the compiler evaluated x plus y, put its value on the top of the stack, and then the compiler should emit this return instruction. What the return instruction will do is back you out of the current function you're in. So we talked about how when you enter a function, we give it a whole new set of locals. And so what it needs to do is it needs to wipe all those away and restore the locals that existed at the time you called the function. And then the last thing is it actually needs to move the instruction, the pointer of what the next instruction is, back to where we were when we called this function. And so a return is just going to be a simple instruction with no operands that handles this. So under the hood, the machine itself, when it sees this call function, it'll actually keep track of, hey, I was at this address, maybe I was at the 50th instruction in the program. And so that way, when it sees the matching return statement, it says, okay, I'm now exiting the function. I already kept track of that I was on address 50 when I saw the call function, so I should jump right back to address 51, the next instruction, to continue execution of the program. We're not going to worry about that because I've intentionally said we're not going to look into the specifics of the machine, but under the hood, you should know that's what the machine will do. But from us, we're just compiling down to this more simpler language, and that's the language of the machine itself. And so what I was just been talking about for the past few minutes is what the machine itself is doing under the hood. And you kind of need to know that to understand like how we should compile things. And it's kind of important to understand, like, hey, if it sees the return statement, like, should it take in an argument of where to return to in the code, or is the machine itself going to handle that? And we're going to go with the latter. The machine itself is going to handle that. So we're just going to have one more parameterless instruction called return. There's an instruction, and we're going to let it have the same overriding, the same toString function, so that when we print the syntax tree, it's not like some ugly thing and it just says the word return. Cool. The other thing that we want to do is, I guess I can just do it in this file. Let's map out what a function declaration looks like. And so I can do it before, I can do it at a new file, or I could do it here. I'll just do it here. Actually, let's try to be somewhat correct. Let me just make a new file. And it's going to be function definition. And here I'm just going to make a simple representation of when we declare a function, what is it going to encode? So we know that to define a function, there's three things. Number one is the name of the function. We need to keep track of this because when we see subsequent code invoke that function, it needs to have a way of knowing which function it actually wants to map to. So we're just going to use name. Then it's also going to take in parameters, and those parameters are just names. So when I define in the example program the function add, I just gave it named parameters a and b. So we want to keep track of what those are. And then the third thing is the actual body of the function, i.e. the series of instructions that would encode the compiled behavior of the body. So when you specify in the program, you give a body of a list of statements. When we compile it down to a list of instructions. Instructions being the atomic little operators that we just looked at in the other file that our machine actually understands. So I'm going to say that a function definition is literally just going to be the three of these. It's going to be a name of the function, which is a string. Then it'll be the parameters to that function, which is going to be a list of strings. And so in our add case, it would just be a list of A and B. And then the third thing is the body, the instructions that we need to execute to actually represent our program, or the body of that. We'd actually say that the list of instructions represents the translated body of the function that was specified as the list of statements that appeared between the curly braces. Sorry, I'm jumping over my words a lot here. I feel like I've been doing better about not using filler words, but I also tend to speak too quickly sometimes when my thoughts race ahead of my mouth. Apologies for that. I'm probably too late in the video to apologize for that. So that's what we're going to define. This is a function definition. What I probably should have done before this is let's go update the grammar for our language. So I'm going to back out of this. Let's jump to our parser, because the top of that file, yes, this is where we've been keeping track of everything. So, a few things need to change here. The first thing I'm going to do is this statement term. Kind of like 4 different types of statements here. I'm going to break it into different rules. What we're doing where we're just ORing a bunch of stuff together works, but it might be a little easier if we make it more explicit what each of these types of statements is doing by just naming them as non-terminals in the context-free grammar. So I'm going to move this down here. Say this first statement is a variable declaration statement, and that's this. I can get rid of the ors. Then I'm going to say there's an expression statement. And so I'm just giving these names. I'm not changing the context-free grammar's meaning at all. I'm just making these easier for you and I to read. Then there's also the variable update statement. And then the last one was the if statement that we just implemented. And so I can make this now easier by saying a statement is either a variable declaration statement, or it's an expression statement, or it's a variable update statement, which I have a typo in, or it's an if statement. And I'll go ahead and bring these on separate lines just so it's easier to see. But the idea is there. At least I hope it's there. Let me fix that typo. Okay. So I've not changed anything. I've just made this grammar a little bit easier to read. And so we're going to say that there's now another type of statement, which is going to be a function declaration statement. And a function declaration statement is going to be what we just discussed. So you're going to start with the literal string fun, which is just short for function, some identifier, which is going to be the name for that function, followed by an open parentheses, followed by the parameters of this. And so we're going to have to make a new rule for params. I'm just going to call it params for now. And I'm saying it's a question mark, which means it's optional, because we saw that a function doesn't have to take in any parameters if it doesn't want to. It's when we finish your comma-separated list of parameters, you end with a close parentheses. Then we said you have inside brackets, you have a list of statements. So it would be a open bracket followed by any number of statements followed by a close bracket. And so you might be wondering, we said previously that a function declaration in the body has to have the return keyword somewhere. So we do need to make sure that happens, but that's actually not the job of the parser. That's going to be the job of, once we have the parse tree and we're compiling it, then we need to check one of these statements should be a return statement, which we haven't defined up here, but a return statement, we can add it. A return statement is a type of statement. Return statement And a return statement's easy, because it's literally just, it's going to be the word return, and then followed by some expression. It can be a comparable expression. You could do 1 less than 2. We'll say that's fine for now. We talked about that, like, technically we said every function returns an integer, so this works to return a comparable expression because those boil down to integers, but it's not necessarily intended to interpret those as integers. We'll just let it slide for now. Who cares? And so then the other thing we needed to do here was define params. So params, it's going to be just a comma separated list of identifiers. So it won't be a comma before the first identifier. So we'll just have one identifier, and then any number of comma followed by another identifier. So I can encode that by saying in parentheses comma identifier, and then I'm going to use a star because a star means it can happen any number of times. So if there's just one identifier or one parameter, it'd just be that name. And then for any other one, it had to be a comma to delimit between the two identifiers. And then recall that I used the question mark up here to make this optional. So if there's no parameters, you would just omit this entirely, and you wouldn't even need to match this rule in parsing out the context-free grammar. And so that will give us the ability to define. So that's a variable declaration statement. Now we said that as part of an expression, you can evaluate a function. So I could say, instead of saying 1 plus 2, I could say 1 plus an invocation of a function that returns an integer. So we need to update it so we can actually call functions. This lets us define functions. We can't do anything with them. So let's make sure we actually update our grammar to support calling functions. And so what that might look like here is at the most granular level of an expression, you might say it is a invocation. We'll just call this a invocation. So in function, invoking the function is a valid expression. And so then we can define that as an invocation is going to be equal to the literal word invoke followed by an identifier, which is the name of the function we are trying to invoke. And then you have to have parentheses. Even if there's no parameters to that function, you have to have parentheses. And between those parentheses is going to be an optional parameters. So if the function has no parameters, you wouldn't put anything there. But if it does, you need to specify them. And so params is not going to be a list of identifiers that's comma separated. It's going to be a list of expressions. Because I could call a function, and if that function takes in one parameter, I don't have to put in a literal 5 or an a. I could say 5 plus 2 times 4. And we want to be able to go parse it, evaluate, spit out all the instructions to evaluate that parse tree, put that value on the top of the stack. And so that way when you call the invoke function instruction, you call it with the function name and then the number 1. And the machine itself would pop that top value off the stack, which is the evaluated expression of whatever you want to pass in for the value of that argument. And so params is just going to be a comma-separated list of expressions. So the same thing we just did below for defining the... Oh, I should give these different names, shouldn't I? Let's call this... These are arguments to a function, so let's call these args. And so a function declaration is going to specify args, actually. And then here, this should work. So now we're saying that when you invoke a function, you pass a comma-separated list of expressions, not actually identifiers. Because identifiers is just when you're defining the function, say, this function expects 3 arguments, and I'm just going to call them A, B, and C. Versus when you're calling a function, you say, I know that function takes 3 arguments, A, B, and C. I need to pass in values for each of those. Those don't have to be literal values. They could just be any expression, whatever. As long as I evaluate the expression to get a value, then it is a valid argument to that function. So this should be our correct grammar update. And we've added a little bit of complexity here, but we've actually only added a few new keywords. So let's go ahead and update our Lexer to go ahead and scan and be able to invoke those new and detect those new keywords. And the few things we've added is just like this function word, fun, we've added Comma is now a terminal here. We never had commas appear in our language before. We've added this invoke keyword. When you want to call a function, you have to say the literal word invoke. And then when you want to break out of a function, you have to say the literal word return. So those are the new things we've added. And that looks to be fine. Maybe I don't think I missed anything. We'll see when we come back here. So I'm going to back out of this. Clear this. Now we just follow the same set of processes we followed over and over. So we start by adding the new tokens that we have to our grammar to our token type enumeration. And that would be the function keyword if we're defining a function. Then you have an open parentheses, which we already have defined. Then the arguments are comma separated. And so we already have delimiters, but we need to represent the commas now. And that'll let us define a function, but then in the body we also need a return statement. So we want return to be a separate token type, not an identifier. So we get a return type. And then to call a function, the only new syntax we need is the invoke function, because the name itself is an identifier, and the parentheses are already used. We've already added comma, and it's a identifier. It's a comma separated list of identifiers. So that would just be a invoke. Okay. Yes. Now we'll head over to the Lexer. Oh my goodness. Let me pause it while this... Sorry, fire truck was driving by. And now we'll go to the Lexer. And we know exactly how to do this. So we have... So the word fun, invoke, and return are all words, but the comma itself is a one-character match. So we can just match that really easily. So if we scan the next token and it's a character, and it's a comma, then just return a comma type. Use the same logic we've been using. And we just need to make this an else if to continue the logical massive if else. And this is not the most idiomatic way to do this in Kotlin, but it uses the simplest syntax, so that's why I roll with it. And then scan identifier is how we distinguish between identifiers and reserved keywords of the language. So if the literal is fun, if we're defining a function, was the first one we added. Then it was invoke if we're calling a function. And then the last one was in a body of a function we need to return. So if it was the return word. Oops. Okay. And that's all we're going to need to do for the Lexer. And so now we want to move on to the parser, but there's two things we have to do first. We have two new types of statements. We have a function declaration statement and a return statement. And we also have a new type of expression, which is an invocation of a function. So we need to go ahead and add those to our statement and expression data model classes. So we can, when we parse and encounter one of these new keywords, we can populate a new data structure and add it to our tree somewhere. So we can start with the statements. So we now have a function declaration statement. And the function declaration statement, it's going to look for a name, the name of the function, and then parameters. And the declaration doesn't specify the type of the parameters because each of the parameters is just an integer. That's all we're working with in this language so far. You're seeing in Kotlin that a type, there's many types. Type could be an integer, it could be a string, it could be a collection, a list of something. We've seen maps too. So that's a future extension you could add to the programming language if you wanted to, is to type your variables. And that'd be a great exercise to take up. So parameters is just going to be a list of string, and that's going to represent the names of each of the parameters, and the types just by virtue of specification of the programming language is just integers. And the body of the function is a list of statements. and itself is a type of statement. And then the last one, oh my goodness, sorry, police car drove by. Gotta love living in New York City. The last type of statement is now return statement, and return statement passes an integer, and the integer will just be an expression, because it could be return 1 or 1 plus 2, or it could return the invocation of another function. So we've just genericized this into an expression. I keep beating this down because there's a fundamental distinction between a statement and an expression and where you can use each. And by baking this into the context-free grammar, it makes verifying correctness of programs and code generation significantly easier. So for a return statement, you're returning some value, and that's an expression. And a return statement is itself a statement. So those are the 2 new statements we've added. And we also have a new type of expression, which is a function invocation. So I'm going to hop over to our expression definition. These are all the expressions. And so right now an expression is either just a number, or it's a mathematical expression, or it's a variable reference. And a mathematical expression we represent as binary. It can be a combination that can go with arbitrary depth, referencing both variable expressions and number literals. So the last one, because functions all return integers, it makes sense that a function call can be used wherever an expression can be used. So if I wanted to use a plus b, b can be like some number literal 5. A could also be the result of a function call because functions return integers. We'd want to support that in our language. We'll call this one function call, and to call a function, you specify the name and then the arguments. And the arguments is not a list of identifiers, because the identifiers are used to define the function and make sense of the body of the function when it references parameters. For calling a function, we have some number of expressions that we might put on the stack. And this itself is a type of expression. And so now that we've defined our new statement types and our expression types, we can go ahead and now go to our parser and parse these into these data structures and include that in our parse tree. This would be in the parser. Okay, we already updated our grammar. It's crazy how complex our grammar is getting too. I guess when you have several hours of video, it should. Okay, so we're going to go ahead and define first this new function for parsing out a function declaration. So 2 things we need to now parse are function declarations and also function invocations, and this new return statement. So we'll make a private function, parse function declaration, and it's going to return a statement. The type of statement it'll return is the function declaration statement we just defined in the other file. So the first thing when you are parsing the function declaration is you should see the word, we would expect the word fun. We're going to skip over that in this function because the caller of this function will consume the word fun. As we've seen this pattern used elsewhere, it'll make sense in a second. If you're curious why I'm skipping the fun parsing, it's because we're going to only call this function after we consume the word fun. So if we see the word fun, then we will take that out of the list, and we know that we should be parsing a function declaration statement. So the thing that follows fun is the name of the function. So let's go ahead and parse that out. It's a string, and we expect an identifier to follow. So token type of identifier. And if it's an error, function needs a name. And then we pull out the literal value, which is just the string. Then so we have the word fun, we have the name of the function, we have an open parentheses now, so we should just pull out the open parentheses. Expected. And then after the open parentheses, we're eventually going to have a close parentheses. So I'll go ahead and do that. But in between, we should expect possibly a comma-separated list of identifiers. So we'll use a while loop. While we don't have a close parentheses, that means there is some identifier left to parse. So while the next token type is not a close parentheses, then we would need to add to a list of parameters whatever comes next. So I'm going to actually come up here. And outside of this loop, let's define a way to keep track of all the parameters of the function. So we mutable list of string, mutable because we're going to be adding to it, and it starts off empty. And so while we don't have a close parentheses, we should add to this list a whatever identifier comes next. And then if we do that, we can enter another loop. So if we have an open parentheses and the next thing that follows it is not a close parentheses, that means there's at least one argument. So we've parsed out the first one, but now there might be a series of comma followed by more identifiers. So we'll use an inner loop to accomplish this. A loop inside of a loop might be a little weird to wrap your head around, but if you look at how we define the grammar, it kind of makes sense. So while we have a comma after the identifier, then we should expect another identifier to parse out. So I can actually just copy the same logic. Oh, and I actually need to change this. We actually want to consume the identifier, but pull out the literal value from it. And so this will let us parse out all the secondary arguments, if there are secondary arguments. And then eventually we'll see there's no comma, so we break out of this while loop. And then we'd expect a close parentheses. Then we consume that here. So that, after the close parentheses, we've now defined all the parameters of our function. Now we'd expect braces, curly braces, and inside of those curly braces, we'd expect a list of statements. So what I'm going to say is I'm going to consume of open brace, and then we know there's going to be a closed brace. In between it is going to be a series of statements. So while we have not encountered, while the next thing is not a closed brace, and we should also check that we're not going to hit the end of the input. So this is defensive programming. Suppose someone had a program that was just one statement and it was a function declaration statement and we got here. And let's say their program was invalid and that they had an open brace and that was the end of their program. Then if we tried to consume tokens past the open brace, which is where we're at right now, we'd crash because there's nothing else left to consume. So we can be defensive by checking that we're not already at the end of the input when we do so. So it's simple enough to reuse the function we already had earlier. So the next token's not a close brace, and we're also not at the end of our input. That means we should be able to parse a statement. And so I want to parse this. I'm going to keep entering this loop for every statement that's in the body. So the same way we had a list of parameters and then added to it within the loop, we're going to have a list of statements. We'll call this the body. The body of the function is a list of statements that just starts off empty. And so every time we enter this loop, we're just going to add to the body this call to parse statement. Cool. So that's how we would parse a function declaration once we know we have encountered a function declaration. You might be wondering, when do we call this function? You might naively want to put it in here because we said, hey, parse function declaration is just a type of statement. So if we see the token type of fun, that means it has to be a function declaration, so we just call it function. It turns out this is incorrect because recall what well, let's actually just take a look and see when we call this parse statement function. So the very first place is at the top level of the program. That makes sense. Then we said it was within the body of a function declaration, you have a list of statements. But we said that here, you don't want to be able to define a function when you are not at the top level scope. And so we said you can't define a function as part of another function. So this parse statement right here should not be able to parse out a function declaration. This one right here totally should be able to parse out a function declaration because this is your top level parse function that we call to parse out the entire program. Similarly, if we're in the body of an if statement, between the curly braces, you have any number of statements, but we said you cannot define a function there. So you'd want to block it in this case. So pretty much, if I added the check that you might hypothesize in this parse statement function, it would incorrectly allow you to define a function in places that we specified earlier you should not be able to call a function. So we don't want to change parse statement because where it works is totally fine. If we think about it, this call right here, the top level call, is the only place where we'd actually like to be able to parse a statement. Sorry, parse a function declaration. So what I'll do is just make a cheap wrapper. And so I'm gonna say this is gonna parse top level statement. And so I'll make a new function, parse top level statement, and it's gonna return a statement. And this is where we'll check. If we match the token type of a fun, then we can call this parse function declaration statement. We'll just return the result of it. Otherwise, you parse the regular statement that the remaining statements that we've already seen. So what does this accomplish? Is it means in the top level list of statements that make up the body of your program, we support defining a function. In the other call sites where we don't intend you to be able to declare a function, we no longer make that possible because when we call parse statement in these other call sites, it has no check for a function declaration. So it wouldn't match this, it wouldn't match this, it wouldn't match this. It'd go into parse expression statement. And you can see that it would call parse the expression. And if you look at the context-free grammar, there's no way you could match the token type of fun in this parse the expression function. So this is actually how we make true of the specification I said earlier where functions should only be allowed at the top level. Some of the things we'll make true are not going to happen at the parse level. Some things will. This is an example of something we can easily verify at the parse level. An example of something we're not verifying at the parse level is the mismatch between if you try to call a function and you specify variables, if you specify an incorrect number of parameters, or if you're in the body of a function, you're referencing a variable that doesn't exist because it exists in the global scope. So that's something we're also not going to be able to verify in the parser. That's something that'll happen in the compiler stage. So there are some things we can verify in each of these stages, just as the same way we could verify even more granular issues in the Lexer. All three stages, the Lexer, parser, and compiler, will perform different checks to filter out incorrect programs. So a program can only be valid if it makes it through all three of those checks. Cool. So then the last thing we need to do, or two other things actually. For parsing a statement, you need to be able to parse a return statement. That's now a type of statement we define. So I'm just going to go ahead and make a new function for that. So parse return statement, it itself is return a type of statement. And so the only thing for parsing return statement is you would expect a expression, sorry. You expect the return keyword followed by some expression. So let's parse out the C expression, comparable friendly expression. And this was earlier, we said we could have prevented this in the grammar because, we said a comparable expression returns like a true or false that we're just coalescing into a number. And so if we wanted to ban that from even being possible in the programming language, we'd just call the regular parse expression, not the parse comparable expression, because the parse C expression is the only route that will check for the greater than or less than sign. In this case, we're just going to let it happen, whatever. And after that, we consume a semicolon. And once we get that, we would just return a type of the return statement. And all that gets encoded is the expression that is the value we are to return. And so, same way, I'm not checking the return keyword, because I'm going to check that from our parse statement. So right here, when I enter parse statement, if I match a token type of return, then I should just return whatever the function we just called. Okay, the last thing now we need to do is support invocation of functions, and that's a type of expression. So, if I scroll down here, we have parse expression statement, parse the expression, term, we're looking for parse factor, sweet. All right, so we're adding a new case for parse factor, which is case for, and that's going to be a function invocation. So if we match the keyword invoke, and this is why I'm choosing for our language to use this keyword invoke, because it makes it so easy to check right here. Because if we just said you could put in the name of the function, it'd be identifier. And then this logic right here would have no idea if we're parsing out a variable expression or a function invocation expression. It'd be a lot more involved, because we'd have to look ahead to see, like, hey, are there parentheses followed, like, are there some parameters? So it's easier to just use an explicit keyword. So that's why I did that. So if we match a token type of invoke, then we are going to parse out a function. So the first thing is we need to figure out the name of the function we're calling. And so we'll just use the same consume. We consume an identifier. And then we pull out the literal from that. Let me scroll down so my base isn't in the way. And then, so you invoke the name of the function and then parentheses, which is a series of expressions. So I'm going to consume a token type of open parentheses. And we also know there's eventually going to be a close parentheses. And then in between is where we may or may not have arguments. Because you can call a function that has no arguments. We guarantee that a function has to return something, but it doesn't actually have to have any arguments. You know, the function could just trivially return like the number 7 or something. So while we check the next token type, we're not going to consume it, so we're going to use the check. Close parentheses. Then there is a function, or there is an argument. So the same way that we had a list that we added to, we're just going to do the same thing for here. And the arguments is a list of expression. And so the first thing, if we don't have a close parenthesis, we have at least one argument. So let's just add that. The second thing is if we have a comma afterwards, then we have more expressions. So while we have a comma, then add to this args list another expression, whatever expression comes after. And then we consume the close parentheses, and then finally we return this function call expression with the name and the arguments. And that is all we should have to do for our parser. The next thing we're going to need to do is go ahead and now actually change our compiler to walk through this tree, figure out if there's any issues. Examples of issues would be a function that doesn't have a return statement, or calling a function that hasn't been defined yet, or defining a function that's already been defined. So you can't use the duplicate name, you can't use duplicative names the same way you can't define a variable that's already been defined. So let's hop over to our compiler and take care of that. So let's go ahead, hop into the compiler file. And so the first thing I'm going to do is actually just a slight rewrite of something we already built earlier. So previously, we were just keeping track of our locals in one map that was visible to this entire file of the compiler. And every time we wanted a new local, we looked at this next local slot variable, took that, incremented the number, and then used the number we just caught to assign some named variable to the local slot we just acquired. And so this works because locals were just scoped to the entire program, and it's going to be slightly different now because we're breaking out of this norm. Previously, once a local was assigned, it was available forever, and our program was just a sequential list of statements. Now, when we go into a function, things are slightly different because the locals that were defined outside of the function, we're going to say aren't going to be visible within the body of the function. So if I define some variable x and then I'm in the body of a function, x should no longer appear in that locals. But then I don't want to throw it away. I couldn't just like clear out this map because when I break out of the function and hit that return statement and go back to the calling code, x should reappear here. And so that also means when we are traversing the statements that are in the body of the function, the parameters of the function and all the variables that are defined within those statements should be available in this locals. And so really at any time when we're walking on this tree that represents the parsed program, instead of having global locals, we're going to have some context. Like if I'm emitting a variable evaluation statement, the context of if some variable exists is not easily resolved by looking at this global locals. Instead, we're going to make this into a class and pass that around to the function. So nothing changes right now. I'm just going to say that instead of locals and next local slot being something that all the code in this class can just check, we're actually going to explicitly pass in a reference to some context, and the context is just going to be the locals in the next local slot. And the reason I'm going to do this is it's going to set us up for easier implementation, because a little spoiler ahead, not to get ahead of ourselves, is whenever we are within the body of a function and we're emitting all those statements, what we'll do is when you enter a new function, we'll just create a new instance of context and pass that one around to all these functions we already have instead. And then when we're done, we'll swap out the context back to the context we were working with before. And so that'll actually really easily allow us to implement our, emit the instructions for the body of a function without needing to just totally wipe out all the context that existed before and restore it. It'll be much easier to do that if we just have it as a variable. So that's enough rambling. Let me just go ahead and do it. So instead of these two fields living at the top of the class, we're going to wrap that in a class itself. And it's going to be private, and we're just going to call it, let's just call it local context. And the reason you'll see this in compilers being called context is because I think it's pretty self-explanatory, but let's say you're evaluating the statement a plus 5. When you're looking up the variable reference for a, the context of where you are in the function truly matters. If you were within the body of a function, a might refer to a parameter of that function or a variable that was declared in that function's body. And so the context of where you are really matters. Similarly, if you're just working in the global scope in the top-down list of things we've been iterating over thus far, then that's also something very important where I would need to check was some variable x defined before this. So our data class local context is just going to take in exactly what we had here. It is nothing more than the locals that are validly defined in our current context, and then just whatever the next slot is going to be there. And so what we need to then do is in our compile statement, we need to make this context. So we define it as a class. What we're going to do is actually make global context. We can just call it main context, and it's just going to be an instance of a local context. And so now what I'm saying that is, if we look at every place, we can just go see next local slot. So let's take the example of a variable declaration statement. Right now, it's architected, so we'll just read this top level field next local slot. Instead, what we're going to do is wire through the current context as a parameter to this emit statement, and the emit statement will then look at the context itself. And so that way, when we're dealing with a top-level variable declaration statement versus one that happens in the body of a function, it's going to be the same exact code. We're going to call this same emit statement, but the context parameter that we pass through is now going to be how we distinguish between if we're in the global scope or within the scope of a function. So to do this, what we're going to do is, when we're walking through the top-level statements that make up our program, we're also going to wire through the main context everywhere. And so right now, this isn't going to change any behavior because it's the same thing. Like, we have a single context, so there's no difference between us wiring that one context all the way through as parameters to each of the emission functions versus those functions just accessing the top-level context. But it'll make things easier, you'll see very shortly, when we actually have to deal with the function bodies. So for each statement, we call emit. So this emit should now take in a context parameter. So we type local context. And so then we also need to pass through this emit to each of the calling functions. So everywhere where we might emit instruction, we should wire through that context as well. And so here's our first case, the variable declaration, where things need to change. So instead of looking at the top-level locals function, you'll look at the local context that's passed through here. So instead of saying locals, I'll say context.locals. And this emit call will need to wire through the context that it's passed in. And to get the next local slot, we'll need to look at the context as next local slot, not the top level to the entire file. Okay, that covers variable declarations. Variable update would need to look at the context locals. And when it calls this emit right here, it's going to need to pass through the context as well. Okay, that looks fine. Let's go to the if statement. This call to emit will also need to pass through the context. And this call right here will also need to pass through the context. So everywhere we're calling emit, we pass through the context. And then we have our other emit function down here, which also now needs to accept this context. And so right here, we have two more calls to emit, so we'll need to wire through the context there as well. And that's the end of the file. Okay, cool. So that's pretty AA, meaning the behavior is not changed by doing this. But now, as we actually get to look at the body of how we implement functions, it'll make things a lot easier. So let's do that. So the first thing we're going to do is walk through all the statements of our program and look at all the function declaration statements. And so we'll actually register those into a map. So we'll walk through the program twice. First, we'll only care about the function declarations, and we'll register those. And then we'll actually look through the rest of the regular body of the program, which is going to be a bunch of like function invocations and variable declarations and the such. And I know we said earlier that we're just going to walk down the program from start to end. So if I called some function A, but A was defined later in the file, it wouldn't work. I'm actually going to say it's not that difficult to just make it work, so any function can call any function in the file. And that's more realistic of a modern programming language, so we'll just go ahead and do that. And so the reason that works is because now if we deal with all the function declarations first, then it doesn't matter what order when we actually walk through all the statements. If the function declaration happened after some function invocation in the statements, it wouldn't matter because we already did one pass where we looked at all the function declarations, so it would already be registered. So In our compile function, we're going to first now walk through each of the statements. So we're going to register function declarations. And we're going to, usually this is called a signature. So the function declaration is the name of the function and the name of its parameters. That usually in programming language is called the signature. So we'll just be consistent there. So I'll just iterate over, each of the statements. And what we'll say is, if the statement, we only want to care about the function declarations for now. So if the statement that we look at is a function declaration, then we can call some register signature. And so let's go ahead and make that register signature function. Register signature is just going to take in a function declaration statement. And what this will need to do is pretty much for a function signature, for now we're just going to keep track of the name of it and then also the name of all of its arguments. And so that way, when we actually go to look at the function invocations, we can actually just look into this mapping that we're going to build right now and see like, hey, this function with this name does or doesn't exist. If it doesn't exist, broken program. If it does exist, then actually look at the parameters, see how many parameters there are, and then see how many parameters the function's being called with. And if there's a mismatch, then we also know it's an invalid program. So this will help us enforce some of the semantic correctness of our language. So I'm going to make a private val of function parameters. And this is going to keep track of a declaration. So it's going to map a string, which is the name of the function, to a list of strings, which would be the named arguments to that function. And it's a mutable map. And to start with, it'll just be empty. And so then for this register signature, every time we get a new function declaration, first, we're going to want to check, is this function already defined? I.e., if there's already a function in the mapping with this name, it means that there's two functions trying to register the same name, which isn't allowed, so we should error out. So I'll literally just check if function parameters contains the key, which is the function's name, then we can just error out. Duplicate function declaration. Okay. Otherwise, let's keep track of all the parameters we've seen so far. So we're going to build an empty list. And then the ordering doesn't really matter here, but we'll be consistent. I guess actually the ordering does matter. Does it really matter? No, the ordering doesn't really matter, because just for what we're going to use it for now, we're just going to verify the number of parameters in the function declaration is going to equal the number of parameters in the function invocation. Show So iterate over each of the parameters in the function declaration, and the current parameter will just be a string. And so the reason I'm doing it like this is because we actually need to check. If I have a function declaration where I define variables A, B, and C, that's totally fine. But if I have variables A, B, and then an A, that's not allowed. You can't have two parameters with the same name because it's ambiguous when you reference which one you're referring to in the actual body of the function. So we'll block that out here. So and we're going to use a little bit of syntax. So I'm going to say if the scene parameters add of the current parameter is not true, if it's false, then we're going to error out. And so this add function right here will add something to the set, and it'll return true if it was able to do it, or false if that item was already in the set. And so I'm just using this, if it returns false, then it means there's already an item in the set. So we already have defined this parameter name earlier in the comma-separated list of function parameter names. So we'll error out there. Otherwise, if we make it through here, we have a set of all the parameters of the function, and we already have that by virtue of the statement, and that one is ordered. And so I made a mistake in what I said 2 seconds ago. The ordering is going to matter, because even in the function declaration, when we reference A, B, and C, it matters because when you call the function, the ordering of the parameters does matter. So 1, 2, 3, the 1 should map to the A, the 2 should map to the B, and 3 should map to the C. So we actually do need to respect the ordering there. And so for that, I'll just refer to the actual statement's parameters is actually a list. So now I'll just update our function parameters, this tracker that we have up here. I'm going to say for the function with this name, go ahead and keep track of all of its parameters. Okay, so that's all we need to do there. I'm going to bring this to the top of the file. And so now we're going to walk through statements, the function signatures. We're going to walk through all the function declaration statements one more time. And the reason we are doing this is that now that we've registered all the declarations of functions and just have a high-level understanding, now we can actually go through and admit all the instructions for each of the functions that would compose their bodies. And so the reason we do this specific ordering is because now within the body of a function, if a function invocation happens, we can already check and verify the semantic correctness of, does this function even exist, and are we calling it with the right number of parameters? And so we're going to keep track of all the functions now that have been declared. And so I'll make a new global state, which is just the functions. And it's going to be a map of string, which will be the name of the function, to the actual definition. And that'll be an empty map. And recall that we defined a function definition in this file right here. And so the function definition is the name, parameters, and the instructions. So I'm literally going to copy this code right here. Oops. So we're going to parse the function bodies. So we're now doing two pass over the functions, and this is our to-do. But the last thing is now that the third time when we walk over all the statements, we're actually going to filter out on, now that we've walked through and done all the function declarations, and done all the bodies, we want to skip that again when we're walking through all the rest of the statements to emit those instructions. So for these, it's going to be if the statement is not a function declaration, then we'll emit the instructions. Okay. Cool. And now we can build out this parse function declaration. And so we'll be consistent. We've been emitting instructions. So we'll just say emit function declaration and pass through the statement. And so now we need to build out this new function, private function, emit function declaration. And it's just going to take in the statement. So we actually need to walk through the body, make sure that everything's correct, and then emit all the instructions for that function. So the first thing we're going to check is just make sure that the function ends with a return statement, because that was one of the things we said for semantic correctness. We need to ensure that every function ends with a return statement. If it has a return statement somewhere in an if block, that's fine too. We're not going to go down the route of checking every single path that the code could flow through. We're just going to say you can have that return statement anywhere else, but the very last statement has to be a return statement. So that way we guarantee that every function does have a return statement. So I'll literally check if the statements, so I need to look at the body. And I'm going to get the last statement, or null, if the function body was empty, that's invalid, because we said every function needs to return something. So if it's not a return statement, then we should error out. Okay, now we need to walk through all the statements that are the body of this function and emit the instructions for them. So to do that, I'm going to make a list of all the instructions, and we'll just pass that through our emit, and that'll add all the instructions to some list for the body of the function we're parsing through right now. So the body of the function is going to get compiled down to a mutable list of instructions, where instruction is the granular low-level operation that the target language that we're compiling to does understand. And so what we would like to do is walk through the body, and for each statement in the body, just call the emit. But to do that, we actually now pass in a context. And so that's the new thing we just added to the calls to emit is a context parameter. And so now we're in a function declaration, we actually get to make a new context, because the context is now changing. I.e., for all the statements that we're about to emit instructions for, the only variables they should have access to are ones that are defined earlier in the function body or parameters themselves. So let's go ahead and make a function context, which is just going to be an empty local context for now. And the first thing we need to do is for each of the parameters in the function's declaration, we need to put those into specific locals. So that way when the body references those, like if I define a function with parameters A and B, if the body refers to A, we need to have assigned that to a local already. And so we will walk through all the parameters. And declare a local for them. To do that, you can literally just check, does the function context already have a local assigned to this? And we already checked this earlier, but we'll just be safe again. And error out duplicate param definition. Otherwise, let's get the next slot. So from the context, we'll pull out the next local slot. We'll increment that so that the next time we need to get a variable, it'll have the next number. And then the last thing we'll do is actually make an assignment for the variable. So in the locals, which is the map of names to numbers, we'll map the name of the current parameter to the slot we just returned. Okay, so this defines it'll reserve all the parameters in the declaration, a specific local slot. And we're doing this in order. So if you have parameters A, B, and C in your declaration, we're being very cautious to say A gets the first local slot, B gets the second local slot, and C gets the third local slot. The reason we have to do it like this is that the machine language that we're compiling down to, we said that whenever it sees a function invocation call, it's going to pop if you saw a function called to this function this hypothetical one we're just discussing, it would assume that the first item on the stack is C, the one below it is B, and the one below that is A. And so when we're calling the function, we're going to push the arguments onto the stack in order. And so then the machine's going to have to pop those off in reverse order, and it is going to actually put in the values to the local context slots. So it's going to say, first local context slot, I'm going to put in whatever the third from the top argument on the stack was. The second local context slot, I'm going to put on whatever's on the second from the top position on the stack. And for the third local context slot, I'm going to put over whatever was on the top of the stack. So now that we've created our local context for this current function and reserved slots for all the parameters in the function, it's easy enough to just go ahead and walk through the body of statements, walk through all the statements that compose the function's body and emit their instructions, passing through this new local context. So I'll just walk through for the body for each statement in the body. I will just call this emit function with the current statement. I'll pass through our function instructions because it's going to admit all the instructions into a list. And this is, we're just going to say each function's, we're just going to figure out what list of instructions would compose its body. We'll talk a little bit more about that later and how that ends up in the final program. And then the last thing is we need to wire through this function context. And so now, I know I've said this again, but just to reiterate, when we're calling emit and we're looking at one of the statements that's in the body of the function, because we pass through this function context and not the main context, if for example, if it looks up a variable in a reference or goes to define a variable, it's running to this functions context. And so that's how we guarantee that in a function, the only things at starting time you see are your function's parameters, and anything you add goes just in the scope of that function. And the moment you return out of that function, we stop using this function context. And so all the variables that previously existed in the main context become visible again. So now that we've gotten the body, we just need to add it. We need to keep track of it in this variable we have up here. This functions variable we have up here should map the name of the function to the actual compiled body of that function. So I will say functions, get the name of the function, and we'll make a new instance of this function definition that we just saw in the other class. And so the name of the function is, we already kept track of. The parameters is already kept track of in the parse tree. And then the interesting thing is the instructions is what we just made right here. Because we passed through this function instructions, which was an empty list to the submit statement, and it kept on adding all the instructions as it walked through each statement in the body. Okay, so that's good. Now, so we've, in our top level compile statement, we go keep track of all the functions and parse out and emit all the instructions. So we've compiled all of our instructions that represent the function declarations. Now in these regular statements, we have to handle two new things. The remaining two things we added to our context-free grammar are number one, the return statement, and then number two, a function invocation. And so let's go ahead and start with the return statement. So when we call emit, we check the statement type. We handle the expression statement, the variable declaration statement, the update variable statement, and the if statement was the previous thing we added. Now we'll check if we're handling a function declaration. This is not possible to reach. So what's interesting is we know that we're not going to call this. We know that, like, we know by virtue of what we call this that this code right here is not really reachable. Actually, I take that back, because if you had in a statement, this code actually is possibly reachable, because if you try to declare a function in the body of a function then that's not at the top level, so it shouldn't be allowed, but you would reach this code right here. So here's actually where we'd error out. I can't remember if we actually enforced that in the parser, so maybe it actually is unreachable, but let's assume the parser didn't enforce this. The compiler will enforce that you can't try to declare a function if you are in the body of another function. And the other statement type that we added is a return statement. And so similarly, if we are in the body of a function, a return statement is totally fine. But if we are at the top level, a return statement should not be fine. Our context, however, is only keeping track of if we are, is only keeping track of the locals, but it doesn't actually help us understand if we're in a function body or not. If are we in the top level, or are we in a function declaration? And so the state is supposed to pass through, the context is supposed to pass through all the state that the compiler needs to know to emit some particular instruction. So something useful we would like to add here is precisely if you are in the body of a function or not. So what we can just add is function body, and by default you're not in function body. And so when you actually are emitting a function declaration, the context you build up here, we should actually specify that, yes, now you are in a function body. Otherwise, we just let it default to false for the global scope. And that's when we make our main top level context right here, that'll get false for is function body. So then when we actually encounter a return statement, we will just check if the context that we get passed in says we are in a function body and it's not true, then we should error out. If we're not in a function body, then you can't just have a return statement at the top level. Otherwise, we just trivially emit whatever the operator was, operand, to the return statement. So return followed by an expression, we need to emit all of the instructions for that, to get that expression's final value on the top of the stack. So we make one pass through context, and then after that we put out a simple return instruction that we just defined, and that's one that the machine natively understands. Cool. So that gives us the function declarations. The last thing we need to do is we added a type of expression, which was a function call. And so here is when here's the emit statement that gets in an expression. So we'll just add to the bottom of this list. We've already handled the types of expressions you could see are number literals, a binary expression, or a variable reference. We'll just add one more now. If we're dealing with a function call, then we have to do the same thing. We need to verify semantic correctness. So first we should get all the parameters for the function that we are trying to call, so we can check that, hey, this function expects 5 parameters. Are we actually calling it with the 5 parameters in this function call expression? So to do this, we'll get the parameters that are defined, which would be in the function signature. How the function is defined, these are the parameters it says it's going to expect when it's getting invoked. And we already kept track of that in this top level function parameters variable. So we pass in the name, and if that top level variable function parameters does not have a function with the name, that means we are attempting to invoke a function which has not been defined anywhere in the file, so we should crash. Scroll that down. Okay, now we need to check is the parameter size. So this is the number of variables in the parameter as defined in the function signature. So the function says I expect this number of variables. Let's check, did the user call it with that number of variables? So the expression keeps track of the arguments as a list, and we'll just check the size of that. And if it's not equal, we'll error out. Otherwise, what we need to do is we can't just emit this call function instruction. We need to emit all the instructions that would get all the parameters onto the top of the stack. So we'll just visit each of the expressions and then emit this call function. So for each of the arguments, emit the instructions that would get us that when evaluated would put that operand on the top of the stack. And then after that, we have a guarantee that if you run those instructions, you'll have the arguments on the top of the stack. So now we can emit this call function instruction. And so the two things is we call the function with its name, the string name, and the machine also needs to know how many arguments should I pop off the top of the stack to assign the locals. And that generally should get us there, but there's one other thing we need to address. And so previously, when we compiled this function, this program, pre-functions, what we would do is just take the input list of statements, have one list, which was all the output instructions. We'd walk through all the statements and spit out a series of instructions to this list. And then we returned out of this compiler a list of instructions. And that list of instructions was remarkably powerful in that we had the guarantee, assuming we built the compiler correctly, that if you ran through on a real machine those list of instructions, it would execute the program that was represented by this list of statements written in a higher level language. And that's the essence of a compiler. So what's interesting is we now have different lists. We have one list which represents the global scope of all the statements that make up the body of the program, except function declarations. And then for each function declaration, we have a separate list of here's all the instructions that you need to invoke whenever that function's called. And so we're kind of cheating a little bit. We're going to cheat a little bit for right now, because in actuality, a compiler should just spit out one final list of instructions where everything was in that final list. And so if you were to call a function, you would just jump somewhere in the list of instructions that represented the address at which the body of the function started. For now, just to verify that things are working as expected, we're going to make our compiler return two things. The first is going to be a list of instructions, which is the compiled set of instructions top down for everything except actual function declarations. And then the other thing we're going to return is a actual translation for each function, a mapping of the name of the function to the statements, to the instructions that represent its body. And this will bridge the gap, because right now the native instruction that we compile function invocations down to, if you call a function, it's going to emit the invoke function with the literal name of the function. And so then if we have that in a mapping somewhere else, we can assume our hypothetical computer could look it up. It's a little bit of oversight, or a little bit of an oversimplification on our end, but for now we're just going to do that to make it work. So right now, our compiler returns a list of instructions. We're going to change that so it returns something called a compile result, where the result is still the same list of instructions that represents the body of the function, the body of the program. And then it's also going to take in all the function declarations. And for that, that's going to be a mapping of the name of the function to the compiled body, which would be a function definition. So now we return a compile result. And so the only thing that really changes is we don't return instructions. We are going to return a compile result, which would be the instructions, and then also the functions that we made up here. This mapping that we populated into, every time right over here, in this loop right here, that we saw a function declaration, we went through and compiled the body into a list, and then threw that list in this mapping over here. And so I've updated the machine already to handle this. And so this should be everything we need for the compiler. Let's hop over to the main. Oops, I was not meant to show the machine because I said we're not going to deal with it for now. But in main, now when we call the compiler, we actually don't get a list of instructions. We get a compile result. And so when I call the instruction, when I feed that into the machine, I would need to pass in the two things. And so I've behind the hood updated the machine so that it accepts these two things and uses them correctly. So this becomes result. And so we'll say result.instructions, and then we'll feed into the machine the results instructions, but then also the results functions. And oh, the other thing we need to do is update our pretty printing, because we have new statement types and expressions that we have to handle. So if we're printing out a function declaration, oops, need a quotation there. And then we'll need to print out the parameters as well. For each of the parameters. And then we need to print out the body. So for each statement in the body, we'll pretty print that statement with extra indent. So that's how we print out a function declaration, and then the return statement is super easy. If it's a return statement, oops, this should have a statement prefix. Then we can just literally print the word return. But we also need to print out the expression as well. But we already have a function for printing out that expression. And so we can just pretty print the return expression with higher indent. And so that pretty print call calls this pretty print call, which handles expression. And the new expression we have that we also need to pretty print is a function invocation expression. Print out the name of the function we're calling. And then we need to print out the arguments. And so for each of the expressions, arguments, which are themselves expressions, print those with just higher indentation. Okay, so this should be everything, because I made the changes to the machine off screen. So what we need to do is compile it. I'm very scared to compile it, because I think we're probably going to have many compilation issues. But let's go ahead and see what happens. I'll spend a few minutes working through those. Okay. Oh man, that's a lot. Okay. Mutable. Okay, compiler line 10. We need a mutable map there. That's easy to fix. Then, oh man, I have to keep compiling. Compiler line 19. Okay, that's just a simple typo of instruction should be capitalized. And it should probably just be singular, not plural, I think is the class name. And then 43, there's, okay, so 19 and 43. That's the fix for 19. 43. Statement, not STMT, because that's referring to this statement, the current item in the list of statements that we're iterating over. Okay. 51, 58, 51 and 58, unresolved references. 51. Ooh. I should have seen what it was complaining about. Oh, I think we just need to look at the body is a list of statements. I think we would just do that. We'll see though. Function context locals should be pluralized. All right, so let's see how those fix. Contains key. Okay, so 58 was the issue. Should be, there's another issue. And then 61, there's some issues where it's expecting invocation. Okay, 58, let's start there. Contains key. 61, okay, context. Okay, this should be function context. And all of these should be function context. Okay. It's like the least fun part of writing this stuff. It's fixing all the small issues. Okay, 63 unresolved. 63 and 164. Function context. Is name not recognized? Ah, yes. It should be parameter. Okay, 104. What was the issue? It pointed out instructions.add. Maybe it wasn't 104. Let me just rewrite.
getting there. Expected a possible integer, got it actual. Oh, it's a typing issue. Okay, so it doesn't. First off, it doesn't recognize locals, and then second off, it's getting the wrong type. Ah, wait, what line was that? Damn it. Sorry. 164. Not 104. Okay. Ah, this should be context.locals. And I bet that'll fix, because we wired through the context parameter. That was legacy code that was accessing the top level context before we had passed that through. Okay. Compiler 178, and then we're done with compiler. Instructions, this should be plural, I believe is the issue. Oh. Actual type is instruction.call function, but instruction was expected. But a call function should be an instruction. I think we might have a issue in our definition. Yes, we did not say that a call function is a type of instruction. That is fixed now. Alright, then we just have some issues in main. Okay, unresolved reference compile result. Did I call it something else in the compiler? I called it a compile result. I guess we can just move it into its own file. Let's see if that fixes it. Okay. 79, 60. This is just a typo. Padding has 2 Ds. 60. Did I forget the return statement or something? Not sure what was complaining about there. 60. Oh, identifier. Unresolved reference identifier. Huh. Oh, that's in the parser. Oh, it should be caps locked. Okay, 2 more issues. No return on line 76. Oh, this would be a real issue. And I actually just... I'm not sure we actually need to return anything from parsing a function declaration. Yeah, there need not be a return statement here. Oops. Because it writes into that state, it doesn't need to return anything. Expected. Oh, maybe I am wrong. Oh, sorry. This is... I thought that was the compiler. This does need to return a statement. It should return a statement of a function declaration statement. Ooh, let me cut the video for a second and figure out where we define this. Okay, that would be in statement. A function declaration takes in name, parameters, and body. Name, parameters, and body. Okay, that should fix that.
down to the final error. Parser line 210. And this should be args, not arguments. Ooh, takes a village. Okay, I don't see any compiler issue, but I do see an issue in the program. I can't remember if we just had a bad program in there. Let 9 equals 5 if x is less than 5. Then we define y. Ah, yes, this is an intentionally bad program. Okay, so if I've done this correctly, we should have support for functions. Let's go ahead and try to write a program that has functions. Okay, so let's go ahead and try write a function or a program that actually uses functions. Things compile, so we know we haven't regressed too much, but we actually don't know if the functions work yet. So, and since functions can be verbose, all my programs so far have been on one line, but we can use multi-line strings in Kotlin. It's totally allowed. So let's define a function, a really trivial function add. Takes in, let's say it takes in a and b, and it just returns a plus b. And then let's try invoke that. So let's say let x equals the invoke of add, and let's call it with 2 and 3. And then we'll just emit x to get that value of x on the stack, and let's print that out and see if this works. So if this works, I'd expect 5 to appear as the final result of our program. Hey, okay, it's cool. So if we observe what we have here, we're seeing in our pretty print, we're seeing a function declaration named add with 2 parameters. It parses out the parameters. The body is simply a return statement whose expression is a binary addition of a and b. And this looks cool. And then we have a variable declaration, and its expression value is a function call with args 2 and 3. And the last thing is we just put x on the top of the stack. So you can kind of see that the final thing our program spits out is it pushes the operands onto the stack, 2 and 3, and then it emits this call function instruction. It's saying the function we want to jump to is named add, and you should pop the 2 arguments off the stack in reverse order to figure out what should go into the local context. And then we can see that we are having a variable declaration where we just store whatever's on the top of the stack, which is the result of this function call, into local slot 0. And to reference the variable, we print out local slot 0. So this is fine, but we actually want to also probably spit out the instructions that compose the function's body. That would also be useful to see. So let's hop back in the main and do that. So right here, we just pretty print each instruction, but let's also pretty print our declaration, our function bodies. Function bodies. Okay, so result dot, functions. For each of these. So for each of the functions that we compiled, we're going to want the name and the function definition. And we'll spit out the name of the function. And then we'll also put out the parameters, which would be function.parameters, and we'll join, it's a comma separated list, we'll just join it to a string, or it's a list, we'll join it to a comma separated string. cool. And then for each of the bodies, for each of the instructions, we'll get the index too. We can just print out the index and then the instruction. Okay. So now we should be able to see that our function body, so the function add, all it literally does is it loads from locals slot 0 and 1. So that means under the hood, we have the correct assignment that variable parameter A gets assigned the slot 0, parameter B gets assigned the slot 1. It adds them, so it puts the result of that onto the stack, and then it returns. And the return in the machine instruction will jump the code execution back down to here in our case, whatever was after the call function instruction. And then it'll guarantee that they'll also swap the locals back. So all the locals that we previously had were restored. So this is looking cool. Let's go ahead and try break it. So what if I had a third parameter here, and our function doesn't call it? It should not compile. So we can see function expected a different number of arguments than it received. That looks good. Let's go ahead and say we did call it correctly. Let's say this function said let y equal, but then it never had a return statement. This should also crash. So the function needs to end a return statement. That looks fine. Okay, we can trivially fix that just with return y. Let's try call this function that doesn't exist. Sweet, calling unknown function. Okay, so it looks like we guard against error state fine. Let's try one other thing. So what if we invoked a call to add to get the parameters to invoke add? So 1 and 1, and then let's say I invoke add again, 4 and 4. Found a different number of arguments than it received. Oops, that's because I forgot to update our declaration. And so this works totally fine, which is awesome because it's adding 1 and 1, which is 2. It should evaluate the function call to get the first operand, which is itself a function call, but that's fine because it uses recursion. And then it should add 4 and 4, get 8, and then finally it calls add again, and that one is the one that adds them together and should return 10, because 8 plus 2. You can kind of see that in the compiled instructions. We're pushing 1 on 1 on this stack, and then we're calling the add function. That puts 2 on the top of the stack. Then on top of that, we're pushing a 4 and a 4, calling the add function. That'll end up with an 8 on the stack, and then we're calling the add function again because we now have the two operands on the top of the stack, their evaluated values. We assign it to a variable and then just spit out that variable. And the last thing I want to prove to ourselves that we've done correctly is that we said in this function body we declare this variable y and we return it. Outside of here, I should not be able to reference that y. That should not be possible because it's using a different context. The scope is fundamentally changed. And yep, we see that you reference an undefined variable y, and that happens because when you exit the body of the function, the context, the locals restore, so there's no longer any y. Okay, sweet. So we've fully implemented functions, and this is really powerful. Our programming language is capable of doing interesting things. Let's also go ahead and commit it. support functions. Oops, I'll figure that out. So although our functions work, I'm not going to praise ourselves and pat our own backs and try to showcase everything we built, because we made a huge oversimplification with functions. So if you watch my last video, or if you've taken computer architecture class, two things probably should have stood out from you in the last section, and I called both of those out. It turns out we've kind of made some very big assumptions in how we are architecting the language we compile down to. And it turns out it's actually not that difficult to go back and make it more realistic and make the instruction set more realistic of the computer we're compiling down to. But I wanted to break it into two distinct steps because I think it would have been a lot to present at once. So the first issue is if I hop in to the instruction set that we compile our computer down to, this call function is taking the name of a method, which is a literal string. And if you've watched the last video, then you know that this isn't possible. We saw that every instruction, if it took an argument, then that argument had to be a number. And we also saw that there was a fixed number of bytes we could use to represent that number, i.e. zeros or not ones is the language computers speak. So this argument right here being English letters, it does not really make sense. And you might want to say, well, what if I just hypothesize the way to translate English letters down to numbers? Like maybe you let A equal 1 and then B equals 1, 1 or something like that. It wouldn't work because we have each instruction in our computer we saw used a fixed number of zeros and ones. The first half in the computer we built was used to denote which instruction. So maybe we'd say 1101 represented the call function instruction, and then the remaining numbers were used to represent the argument. If we tried to represent an entire series of letters there, we would run out of space very quickly. So that doesn't make sense. And this feeds into the second issue, which is that our compiler returns a compile result, but that compile result should just be a list of instructions. In the computer we had, we saw that instructions are just straight up zeros and ones, all stacked sequentially, and when you put them in memory and set your program counter to the first instruction's address of where you started in memory, usually 0, and let it run, the computer would be able to read just top down, and if there was branching, it would execute that. Versus here, we don't really return a list of instructions. We're returning a list of instructions, which is the top level program, but then whenever we want to invoke a function, we end up having to jump out of this list of instructions into some other universe, even though it kind of breaks our assumption that our program that we compile down into should just be a list of instructions. And so what we're going to do is fix that. We're going to change this so that our compile result does not return this functions at all. Our compile result is just going to return a list of instructions, and in those instructions, we will need to include the instructions that represent the body of a function. And so what that actually also means is I can remove this function definition, because if the compiler is not returning it, we never need to feed it to the machine. And so let's go ahead and just get rid of that class too. And so we started off looking at the machines and the machine's instruction set. So let's hop back there. What we're going to end up doing is making this call function to represent which function we're calling. We are going to load out our memory such that it has all of the code for each function body is just somewhere in this list of instructions. So to denote where a function body lives, you would just say, hey, if there's 100 instructions in our final result, maybe the body of this add function we just described starts at address 55. So treat address 55 to be the start of a function and jump there. So when we return this whole list of things, the way we denote a function is we tell the machine where it should assume the first instruction is for the body of statements that compose that function's definition.
So instead of denoting it by a name, because the computer literally can't understand text, and we're kind of making this high-level assumption because we're implementing the computer in software in another programming language, to make this more realistic, we're going to say that to call a function, you just pass in the address of where that function's body begins. And so pretty much what that means is when the computer sees a call function, it'll move the program counter to that address, and it'll just keep running top down. And the way it gets out of that back to where it came from would be the return instruction. And so we'll say that the machine itself, if you say call function at address 55, it'll keep track of where the program counter was before. Maybe we're at address 70, and it'll jump you to address 55, and when it eventually sees a return statement, it'll jump you back to 71, whatever came after the call function instruction. And the other thing we're going to add is, to support this, is just a regular jump function, which tells the computer, if you reach this instruction, actually don't do anything here, just jump me to another function and continue execution there. And so for that one, all it's going to take in is a target address. And it is an instruction. Not going to make the same mistake I made earlier. Okay, so the only thing we need to change really for the most part is the compiler itself. And so the way we're going to do this is, what we're going to do is we're going to walk through and we're going to emit, for each function that's declared in the program, emit all of the instructions for that function sequentially. So let's say I have 3 functions. I'd visit the first function, spit out all of its instructions. Directly after that, I'd spit out the instructions for the next function, and directly after that, I'd spit out the instructions for the function afterwards. After that, I will spit out all the instructions that make up the actual top-level statements that compose our program. And so then what we're going to do is our very first instruction is going to be a jump instruction, and it's going to skip over all the function declarations to the first instruction of where we're actually going to execute the body of our program. And then, as we spit out each of the function implementations, we'll just keep track of, hey, here's how many instructions it took to get this first function out, so we know where it starts. So then whenever we intuitively see a function invocation, we'll just know that, okay, well, that function started at this address, so you should just use that as your argument for jumping to the function. So what I'm actually going to do is wipe out these 2 variables we had earlier for function parameters and functions. And what we're going to keep track of, we still want to visit all the functions to get their signatures first. So I'm going to make a new class for that. And this class will take in the parameters for that function. So we still need to verify that there is consistency with respect to the number of defined arguments and how many arguments the actual caller passes through. And we still need to go assign those to locals. And then the address of the function. And then the other thing that's going to happen is I'm going to visit all the functions first. And so I will know by the time I visit all the functions, which functions exist, which address ranges they took up in memory. So I can build out a very easy mapping of function names to these signatures. I.e., this is what the function expects parameter-wise, and here's where we actually put it in our list of instructions. The tricky part, though, is let's say I have functions A and B, and let's say A actually calls B. And so if I'm spitting out the instructions for A, and there's a call to function B, I have not yet spit out the instructions for B, so I know that there's going to be a call instruction function, but I actually don't know where I'm going to jump to yet. And if you think about it, this is actually really familiar, and we've already dealt with this problem when we implemented the if statements. For the if statement, we evaluated the expression, and if we didn't match the condition, we said, I know I need to jump past all the statements that compose the body of the if statement. I just don't know where that address is going to be until I actually emit all the instructions for the if statement's body itself. And so the way we got around that there was patching, where we spit out a dummy jump instruction, came back to it, and then eventually replaced it once we actually resolved an address. We're going to do the same thing here. So let me save this.
And we'll keep track as we traverse our functions. We'll keep a mapping of function names to these instances of these function signatures. So function signatures is going to be a map of strings, which will be the function's name, to this function signature we just defined. And it's just going to be an empty map to start off with. And so let's actually start making some changes. So the very first thing we know is that we're going to spit out a jump instruction before we emit all the bodies of each function. We're going to spit out a jump instruction because we know that our compiler is going to compile down to this machine. The machine's just going to read that list of instructions and start executing it top down. So the machine itself is going to start execution at address 0. So at address 0, we don't actually want to start executing the body of the first function because that wouldn't make sense. We want to skip over all the function declarations. So what I'm going to do to very start is just add to this our list of instructions a jump instruction, and I'll just put in a random address. And then basically I'm going to visit all the function signatures to make sure that I have a track of them. Then I'm going to spit out all the instructions for each of the function's bodies. And after that, I'm going to actually spit out all of the instructions that represent the program itself, i.e. the top level statements that declare the program, ignoring the function declarations. So by the time I make it to right here, all of the functions have been spit out into our list of functions, into our list of instructions, sorry. So I can go ahead and patch that very first instruction. I can say that the very first instruction at address 0, we should replace it with a jump instruction, and we should jump to wherever we are now. Because that would then be the next instruction we'll write will be where it jumps to. And that's actually where we want to be because that's the top level statements that compose the body of our program. So that's how we get around that. Let me go fix the spacing here. Oops. Then, when we visit each function declaration, we need to, before we even visit the body of it and spit out all the instructions that represent its body, we need to understand that if I am visiting function A, I'm going to start spitting out its instructions wherever I am right now in the list of instructions. So I should actually create a mapping before I spit out all the instructions for this function. I'm going to create a mapping of, hey, this function with this name lives at this address that I'm going to start writing instructions to. And that way, whenever we see a function invocation, we'll just look at that map and be like, okay, the function started there, so that's the address that I should use as the argument to this invoke function expression. And invoke function instruction, sorry, not expression. And so what this means is that we're still going to be using the names of functions in the compiler, but those names of functions, the strings will actually never escape the compiler. That is literally just for us to use for bookmarking, but with respect to what we actually spit out of the compiler, it's not going to have any English string saying that, hey, this function lives at this address. It is simply a bookmark for us to know of keep tracking of how we should move around in the code. So before I emit each function declaration, what I'd like to do is set the function address. I'd like to record that the function with this name is going to live, its implementation is going to start wherever my next instruction that I write in is, that I'm going to write to is. So this set function address is not a crazy difficult function. We can define that. It's going to take in the name of a function and an address, which is a number, i.e. the position in our list of instructions that that function's body will start at. First off, we just go check. We need to make sure that we have that function. Let's get the function signature handle that we just defined above, and we can get that by just looking up in the map. And if we don't have a result, that means we're trying to
somehow define a function that we haven't seen, but that shouldn't really be possible because we've already populated this function signature mapping in the first pass through. That happens right here, this register signature. So it shouldn't really be possible, but we'll just go ahead and say, shouldn't be possible. Something's bad happens if we get there. But assuming that we do find the valid function signature instance, all we need to do is replace the address. So signature.address is going to equal the address that we passed in here. We got passed in as the parameter to this function. So now our process becomes, every time you're about to spit out, for every function, we keep track of where we're going to start putting its body, update our mapping so we remember that, and then write all the instructions directly adjacent to where we were. And then the next function will get visited and it'll do the same thing. It'll skip one instruction below, it'll record, hey, my implementation is going to start here, and then it'll spit out all of its instructions. And so then the last thing we need to change here is that whenever we are emitting a function declaration, we were previously creating a new list of instructions for each function. We're just going to keep one list now because our compiler is going to return one consecutive list of all the instructions. So I'm going to wire through, for the function declaration, I'm going to wire through the statement, but then also our instructions, this list of instructions we have. And so our emit function declaration gets a new argument. This mutable list of instruction. And instead of us making our own function instructions variable, we're just going to use this instructions that we get passed through. And then we don't need to return anything here anymore. Or we don't need to change anything in the mappings. We're just spitting out the instructions. So that looks good. Now, what we need to do is make sure we handle our function calls correctly. So whenever we got to a function invocation expression, originally we were spitting out a call function instruction, but we were using the function's name. Now we need to wire through the address. So a few things need to change here. First, this parameter doesn't exist anymore. We still want to verify that if you're calling a function, the number of arguments you're passing through is equal to the number of parameters the function defines. So let's get the signature instance. And it might not be in our lookup table, which would mean that you are calling an unknown function. And now we'll check if the signature .parameters.size is not equal to the expression invocation's argument size, then we error out. So you might want to say then, okay, the last fix is trivial. Whenever we call a function, don't just pass the name. Go to that table, look up the function signature instance, which we already have from above, and the function signature instance has an address, so we'll just spit it in here. The tricky part, though, this would work, but it's the same issue we ran into earlier, where if a function is trying to call a function as part of its body, but we have not yet spit out all the instructions for that calling function, so we don't know where it jumps to, so we're going to have to patch. So there's two cases. The first case is if the signature address is greater than 0, because by default it's -1, and so if we write in a real address, then it has to be greater than 0. So if it's greater than 0, then we can do what we want to do. And we pass through signature.address. Otherwise, we know we want to spit out a jump function, or sorry, a call function. We just don't know where we want to jump to yet. And so we can't actually resolve where the true argument is for this instruction until we've visited all the functions. So what we're going to do is keep track of all the functions, the pending function calls that we need to go back and patch. So we can represent a pending function call in a data class. It's going to be the name of the function you were attempting to call, the index, i.e. where you were putting out the dummy instruction that we need to then eventually go back and replace. And then when we do replace it, we are going to want to replace, the two things we'll need to resolve is you're going to be calling a call function instruction. That's what you're going to emit. And so we need to know the true address of where we're going to patch. And so we're not going to figure that, we're not going to put that in here because we don't know that at the time we queue a pending function call. But what we do know is the arity, the number of arguments. So we'll record that as well, because that's the other argument that goes into this call function instruction. And so then we'll also just keep track of all our pending function calls that we need to go back and patch. Function calls. It's just going to be a list of these pending function calls. Okay, so now if I hop back down to where we were, if we were trying to call a function and we don't yet know that it exists, then we need to create an instance of this pending function call and add it to our list. So I will say pending function calls add, and I'll make a new instance of a pending function call. And this is we know the function name that we're trying to call is in the expression. We know the number of arguments it expects. And so that's all we do there. Wait a minute. Oh, yes, we need to put in the index as well. So yeah, sorry, the arity. So this is the this is the address of where we are writing the dummy call that we'll need to go back and patch. And so then the arity is the last thing we need to put on. And so the last thing we actually need to do after this is actually spit out, add to our list that dummy jump instruction, that dummy call function instruction, so that eventually we can come back and replace it with a real call function instruction. And so I'm just going to say, we're going to put in a random number for both these arguments, because we're going to come back and fix it later. Okay, so then the question becomes, when do we actually go back and fix it? And we just patch right before we return our compiled result. So what I'll do right before I return our compiled result is call this function, patch function calls. And we need to give it the list of instructions because it actually has to go modify our final output. And so I'll make this private function now. So pretty much what we do is just walk over that list, and for each one figure out the real address now that we'll know it by virtue of being here in the program, and replace the instruction at that address with a correct call function instruction. So same instruction type, but with the real, instead of putting 999 as the arguments, we'll put in the real value. So for each of the pending calls, go figure out the signature of the function that we're trying to call. And we kept track of that in this mapping of function names to function signature instances. So I'll just go straight into that map, look up the function with the pending calls name, and if we don't find it, this shouldn't really be happening, but we'll have to just error out to be on the side of safety. Then what we'll do is, for the in our list of instructions,
we spit out a dummy instruction at some address that we intended to do the real function call out. So let's go into that specific index and replace it with a new instance of a function call, a new call function instruction. And this time, we've now know the signatures, the address from the signature, because by the time we make it to this part of code, we visited every function, so we know where each function's body begins in the list of final instructions. And then I also need to put out the arity as well. And this is all we need to do. So it wasn't actually that crazy, but I think I just wanted to separate it because it might have been a lot to process to do that as we implemented instructions. So we do need to hop back to our main file because we don't actually spit out function bodies anymore because our output from the compiler is now back to being just a list of instructions. And for each instruction, we can actually do this index. We're going to want to see the addresses of everything when we're debugging for each index. Cool. And then also when we in call machine run, we now just feed through the instructions. And I've updated machine off camera, so it's back to assuming that it just gets one final program compiled. So this should be everything. And so now, let me also just make this a little bit easier again. Let's call add with 5 and 10. And we're not even going to store it into a variable. Actually, sure, we can. Okay, so now we have our function. So basically what I would expect is the very first, if we could do this correct, the very first thing that we should see in our source program is a jump function. Then we should see, or sorry, yeah, it'd be a jump instruction. Then we'd see whatever instructions are needed to implement this body. And then afterwards, let's say that's address 10. The very first jump instruction that we start off our program with, the argument should be that. So it should jump to 10. It should skip over all the function bodies. Then whenever we invoke a function, we should be able to see that this add will know begins at instruction address 1 because there's only one function and that's the first one we visit. So we should see it try jump to address 1, using address 1 as the argument for call function. So if I run this, let's see if I have any compilation issues first. I think I saw some compiler issues. What was that? Fun. Okay, 21 has some issues of the compiler. This should be a mutable map. In 51 and 58 of compiler. This should be plural. Jump 7 lines down. Huh. Oh, yes. We just returned. Our compiler result is just a list of instructions now. Typo on line 22, and then line 64 has an issue. And then 64 had an issue. Instruction. There's a typo right here. Sig. There's also a typo right here. Pending call. And there's a typo right here. Wow, not my best performance on that line.
Oh, any more in compiler? More in compiler. Okay. Oh my goodness! And I made another typo on 64. I did. Okay. Val can't be okay. 70 and 93. This needs to become mutable, so I'll make it a var. (93) register signature. Oh yes, function signatures is the new name because we got rid of that old variable we were working in. (102) oh, function signatures. And it will be an instance of function signature now. Okay, main 27, argument type mismatch. Ooh, I forgot a wire through. Heh. I did for each index, which means we get each item and the index. So I need to also get the index. Oh, I flipped it backwards. Index is the first thing. Okay, and there's one issue in the machine file. I'm going to cut the camera and just debug that because I said I'm not going to show the implementation of the machine. We're going to assume that there is some physical computer out there that implements this instruction set, and because there is no such computer, because I invented the instruction set, I wrote software that simulates the machine. Okay, fixed a few issues off camera, but let's recall what our main program's doing. Defines this function. The function just takes the two parameters, adds them into a third variable, which returns that variable. Then we call that function, assign that function result to a variable, should store it into a local, and then we put the value of x onto the stack so we can inspect that at the end of the program. And so if I run this, okay, so now we can see that our compiler spits out just one list of instructions that is so much more realistic of a real program. And so you can see that the very first instruction is saying jump to target 7, and intuitively we can see this is where it wants to jump to, and it kind of makes sense. You can see that instructions 1 through 6 are the body of our add function, and I know that this is true because the very last instruction before is a return, so that seems to be correct. And we can see that the body of the functions, loading two locals, adding them, storing it into a variable, loading that variable to return it. And then we can see that our top level program is putting two arguments onto the stack, calling this function at address 1, which makes sense because the first address of the first function goes there, with arity 2, and eventually takes that result, stores it to a local, and then to put it on the stack, gets that local, and we get the final variable. Okay, let's just go ahead and let's try build a program that combines every feature of the language we've implemented so far. So
what we can do is I'll define a function. We'll just call it bump, and it's a random function, but it'll take in one parameter, it'll add one to it, and then we inputted if statement. So let's use an if statement. If x is greater than 5, then we can update x to x times 2, and then we'll just return x. And then let's call this function bump of 5, and then let's also call it with a variable. So oops, I should be using the invoke keyword. And then I'll use a variable update statement. So I can just say update b to b plus, I'll call invoke again. And I can use one final if statement at the top level. B is greater than 20. Update b to b minus a. Okay, so this is a function a program that should show off, I think, everything we built into our language. We have a function with parameters, local variable declarations. We use arithmetic. We use the if statement. We use the update variable. We use a return keyword, obviously, because we have a function. We have multiple function calls. And we kind of had a nested call flow because bump A is kind of, using a variable lookup, which is the result of another call to bump. And we also have top level state. We have top level variables A, B. So if I trace this through, bump of 5, A should call bump of 5. X becomes 6. Since 6 is greater than 5, it should become 12. So A is 12. Then B is bump of A, so bump of 12, X becomes 13. 13 is greater than 5, so 13 becomes 26. So B becomes 26. And then we say update B to be B plus invoke bump of 1. Bump of 1 is 1 plus 1 is 2, so it's 2. So B becomes B, which is 26 plus 2, so B becomes 28. And then if B is 20, which it is, we'll say B equals B minus A. So B equals 28 minus 12, which is 16. So if we've done this right, we should see 16 come out. Uh-oh. Oh, I have sorry, we're expecting 16, but I have an issue in my program and the compiler correctly caught that. And the issue is that we expected a semicolon following a variable declaration, which makes sense because I forgot to do that. Also, if statement should end in semicolons. And I should also put B's value onto the stack so we can see it. Few issues. Okay, so I see 16, so it's correct. But wow, look at how many instructions came out here, and we can see that the very first thing we do is jump to 15. So our bump function has this many instructions, and we still have 10 instructions afterwards. So this is really powerful. We have now built out a fully working programming language that actually is useful. To read our source code of this program, it's very easy for us as humans to understand what should happen here, combined with our ability to read this, and you also understand the semantic specification of the language. This, on the other hand, is impossible to read. I mean, you can do it, it's not impossible by any means, but it's way slower. You need to really trace out what's happening and try reverse engineer it and go from this low-level language to something closer to English or human algorithm specification to understand what's happening. So we have done something incredibly impressive, and it's awesome because this keeps on going. We can keep adding more and more features to our programming language, and it'll get closer and closer to higher level languages. I think for the scope of this video, we've covered everything I would like to cover, but I didn't expect it to take nearly this much time, but here we are. But I'm glad we were able to cover all this information. So it's my hope, if I've done a good enough job explaining, you understand the fundamental architecture of a compiler. First, we take the input and lex it into very granular tokens, which are the various terminals of the context-free grammar that represents our language. You understand that a programming language is formally specified by a context-free grammar, and that tells you the set of strings, where a string is some amount of text, that is considered to be valid under that language just by syntax rules, not by semantic rules. We saw that there was then, to specify a programming language, you needed to give a context-free grammar for the syntax, and then you also needed a semantic specification. So things like, if you reference a variable, that it has to have been defined earlier in the program, in the case of our language. We started with the Lexer, we chopped it up into tokens, which were the various terminals of the context-free grammar. Then we built out a parser, which took these tokens and built out a literal tree of parent-child relationships between various entities within the program. And we saw that how things get baked into this parse tree can really affect precedence and order of operations. We saw that when we took several hours to look at mathematical expressions only, and we saw that things that were lower down in the tree got evaluated first, so those technically had higher precedence. So in addition, in multiplication, we know that PEMDAS says that we should do the multiplication first. So we saw that we could bake this into our grammar and thus ensure correctness in our program by forcing those parse terms to be lower in the syntax tree. Then when we had a syntax tree, we saw how we could walk over that syntax tree to then generate code for a target language, which is lower level than the language we started from. So high level language, the higher level a language is, the closer to English it feels, and I guess subjectively speaking, the more easy it is to interpret it and the richer the feature set is. Versus lower level languages are closer to the hardware of the computer. They're less readable by humans, but they're closer to what the computer actually needs to execute. And so we built this whole concept of a compiler, which lets us specify a program in one of these high level languages that's really easy and intuitive for us to reason about, and we'll spit out a program in a lower level language that's actually understandable by a computer. And so I would be remiss to end the video right there, because something fundamental that is kind of weird and feels like meta or paradoxical in itself is that we wrote a compiler for the, first off, our compiler was a program itself, but then we also wrote the compiler in a programming language, and we had to compile our compiler, and then we also had to compile some program that could interpret the language that we compiled down into. And so I wanted to diagram out what that looks like so that we're kind of of the understanding of what we have built here, because it may feel weird that we used a different programming language to implement our compiler and it might feel like cheating, but it turns out this is just one of the high benefits of the wide availability of programming languages that we have. So I'm on this website, Excalidraw. It's going to be a little slow for me to draw here. Unfortunately, my iPad's just fully broken and the stylus won't connect, so that's a goner for this video. But at a high level, we can say, oh man. Okay, so we're going to use a few various shapes to represent different things, and I've made it here, but it's not the prettiest. So this little trapezoid right here, we're going to say it's used to represent some program that's expressed in some language. So I guess maybe you should use the letter P for some program, and it's written in some language. And so what the program does doesn't really matter to us. Some examples is maybe I'd have a program that sorted a list of input, and that program was written in x86, which is an instruction set that an older version of my computer happens to run. We'll just assume my computer runs x86. And in order for us to run this program, you need to have some physical machine that executes code, i.e. some machine whose instruction set is equal to x86. So if I had some program language, if I had some program expressed in some language, the only way I can run this program is if I had a machine that natively spoke language L. And so I'll use this diagram right here to represent accordingly. So this right here is the machine that executes code in language M. So it's just some machine exists, and that machine, its native language, the one language it speaks, is M. And so if I wanted to run this program P in some language L, I would need to find a machine whose native language is L. In this case, this would be a valid example. And so then if I stack this, I would need to see that for this to be a valid program that I could actually run, the language that the program is expressed in has to be equal to the language that the machine speaks in. And so this diagram right here means that we have a program P running on some machine L. And so our program could be anything. And in our case of what we built, our program itself is a compiler. So a compiler itself is a programming language, is a program. But we're going to represent compilers slightly differently here. We're going to use this T diagram. So the issue is, I guess I should do a little contextualization, is let's say I have some program, and in our case, I had a program that was written in tinylang, and I need to get it down to, and it was, let's say I had some program, sorry, I'm using that backwards. Let's say I have some program, and it's implemented in tinylang, and we never gave a name to the language we compile down to, but we can just call it tinylang TAM, stands for tinylang abstract machine. And the issue is we cannot stack this right here because there is a mismatch between the language in which the program is expressed and the language in which the machine runs hardware. So if we wanted to run this, we have two options. We either need to find a machine that can physically execute tinylang instructions, or we need to find a way to express this program in tinylang abstract machine instructions. And so the way we do that, and we kind of know this because this is what we built, is that we have a program which is a compiler, and the compiler will take in some program expressed in tinylang, and it'll spit out the equivalent program expressed in tinylang abstract machine syntax. And so to represent a compiler, we're going to use this syntax right here. And so this is saying that you have a compiler that translates from a source language into a target language, and that compiler itself is written in some expression language. So we just say M for some machine language. So in our case, we built in a compiler that's expressed in Kotlin. It takes in tinylang programs, and it'll spit out instructions for tiny abstract machine, TAM. And so what could happen is I would want to feed in some program expressed in tinylang, and I would get out that program expressed in tinylang abstract machine syntax. And the last thing, the gap, is that the program itself, our compiler, is expressed in Kotlin, so I would need a machine that speaks Kotlin. But it turns out we compile our compiler, so it turns out like our computer can't actually, my computer does not actually read Kotlin, but we'll just assume that there is some machine whose native instruction set actually is Kotlin. And so if I run this through, then if I run our source program is expressed in tinylang, and we built this compiler which takes in some program expressed in tinylang and spits out a program that is equivalent in TAM, and this program itself is written in Kotlin, and we have a machine that executes Kotlin code. And so the output of that is the equivalent program, but now written in tiny TAM. And so the original issue we started out with was that we had, I should have copied instead of moving things around. We had some program expressed in tinylang, but the physical machine we had only read TAM code, sorry. But after feeding it through this compilation process, we now have a program that is expressed, equivalent program expressed in TAM. And now since there's a machine that reads TAM, the two kind of match up. And so we now have a way of executing this program. And pretty much for this diagram right here, this is showing that for this to work, the source language that your program is implemented in must match the input language to the compiler translates from. And then also the language in which the compiler is expressed must be equal to the language in which the operating computer speaks. And if that's the case, then you get out something where it's your same original program, but it's expressed in a different language now. But I'm making a simplification here because my computer doesn't actually run Kotlin. My computer runs x86. And so this part right here is not quite true, but our program was expressed in Kotlin. So how did we end up with this equivalent T diagram? We must have ended up with something that actually looks like this. And we actually ran it because I had a machine that runs x86. So we wrote this program right here, but we actually compiled it to get this one right here. And so let's diagram what compiling the compiler looks like. And I know it's like a little weird to wrap your head around, but basically we started with a program that was written in Kotlin. Everything we wrote was in Kotlin, and our program was a compiler that would take in tinylang as the input, translate it to TAM. Then on my computer, what I didn't show, I had it hidden behind this script that I kept on calling run.sh, was I actually had a compiler that takes in Kotlin code and it spits out x86 code. And the Kotlin compiler I have on my computer is actually written in x86. So my real machine could run this program, and what I would get spit out on the other side, is the same program that takes in tinylang and spits out TAM, but instead of being written and expressed in Kotlin, it is now expressed in x86. So this triple T diagram, really interesting, is a visualization of how my computer compiled the compiler we wrote. And so then, to actually run this code, we compiled my compiler and got that compiler expressed in x86. And that is how we were actually able to run the physical compiler on my machine. And that way, we had an example program that was expressed in tinylang. We feed it into our compiled compiler, and we get spit out that equivalent program in x86. And so this is the full life cycle of everything we've done. It spits out, not that program in x86, it spits out that program expressed in the TAM language. And this is the full iteration of our compiler. But then the very last thing that happened is I wrote a simulator on my computer that would interpret TAM as if my computer was running TAM itself, but it wasn't. And so we generally see that a language is either compiled or interpreted. Sometimes it can be both. An example of something that's both is actually Kotlin, the language I was using. I kind of made some assumption that Kotlin was compiled directly to x86. That's not really the truth, but I think things would get really out of hand really quickly if I started stacking all these diagrams. But we're going to introduce a new diagram type, which looks like this. And this is an interpreter. An interpreter is something written in software that takes a language. An interpreter itself is written in a language, written in some language L, and it can interpret some program that is expressed in some programming language P, but I guess we can just call it source. We can use S. So an interpreter runs on some physical hardware, but it'll let you bridge the gap. So in our case, I had a TAM interpreter that was written in native x86, and then my computer itself is an x86 machine. And so when I stack it like this, then I pretty much have a machine that can run TAM instructions. So the very last thing I did was I spit out the final program that our compiled compiler gave us and ran it on this interpreter. And this diagram right here is how I was running some program in TAM on x86 hardware. And so we had actually a little bit of compilation and interpretation going on. And I know that's a lot to wrap your head around, because it is. It's a mouthful for me to even say it and think out loud. But it would be incorrect of me not to show that, because in our process, we actually took a compiler and used a different compiler to translate our compiler into a different input-output target. And we compiled our compiler such that our compiled compiler could actually run on my physical computer. Without that, we would just have a program, but it wouldn't actually be able to run if I didn't have a correct compiler for it. So we used another compiler to compile our compiler. That's a mouthful. But this begs the question of, like, where does the first compiler ever come from? So, like, we saw in my last video that you can program a computer by literally punching in zeros and one into the RAM of the machine, and you would get a program and it would run on your computer, but it was really hard for you to make sense of. And so then we kind of had this assembly language, which is what we kind of worked in this video, where instead of saying zeros and ones for every instruction, we would go somewhere between, where we know like 1101 is the instruction for add, so we just say the word add. And that way our compiled programs were a little more readable, where it'd say add 15 or push or pop or like jump. And an assembler would simply take that more readable program and translate it down to zeros and ones. And you can imagine that's not crazy difficult to accomplish compared to the compiler we wrote. But then, if you have an assembler, how do you compile any language without a compiler? And so it turns out that someone way back when actually had to handwrite a small compiler in assembly, which is insanely difficult to do. Our language isn't even capable of being used to express a compiler, but if you watch my last video, or have any understanding of the subject prior to watching this video, or even seeing the instructions that our compiler spits out, it's a insane accomplishment that someone was able to do that. And that pretty much paved the way, where once we had a compiler for some programming language, there's a concept called bootstrapping, which I won't go into in too much detail here, but it effectively allows us to use that compiler to compile our own language and keep letting that language get better and better until eventually you have these high-level languages. And from there, once you have one compiler that's actually capable, you can pretty much use that to implement any other programming language out there. So it's pretty meta that we use compilers to compile compilers, and that someone at the very end of that started that chain had to write a compiler themselves. But I think it's pretty powerful and one of those, like, this is really weird to wrap your head around. Let me take a sip of water. So, I am about time here. I'm going to end the video. I wanted to apologize because parts of this video were definitely rushed. For context, I'm switching jobs recently, and so I had a few days off in between and was really hoping I could get this entire video done in 48 hours, which is an insane timeline. And obviously that didn't end up happening. It took me a few weeks. But when I was sprinting to get it done in 48 hours, I was really trying to go as fast as possible, just because I would rather have gotten some video out than no video. But that didn't happen. So I feel like once I realized I was going to miss the deadline, I was able to slow down a little bit. But I do apologize because I feel like parts of the video at the start were very rushed. And it's probably honestly a good thing, because I really think I would have ran out of time to cover through everything. So I think it's not strictly bad. I didn't expect me to be at 11 hours already. But I did want to apologize that it wasn't as clear as I would have liked it to have been. And I honestly debated throwing away the entire video and trying again in a few months. But I figured it'd be better to push through with what I have and just note that for videos moving forward, to not try crunch them in a short time frame. But I hope this video is incredibly useful to you. I have had so much joy reading the comments on my last video, and getting emails, LinkedIn messages, Instagram DMs, you name it, has actually been so rewarding and really cool to see. And I never expected so many people to finish the video or make meaningful progress. I'm hoping this video is, I know it's a bit niche of a subject, but I'm hoping it finds appeal to someone. And if you make it all the way through and have feedback for me, please let me know. I think one of the most common pieces of feedback I got on my last video was that I used too many filler words. And I knew that because before I actually uploaded that video, I transcribed the entire 12-hour thing and was trying to do a distribution of words, and the word was just plaguing the entire transcript. So I hope I did a better job about it this time. My goal, I really like teaching, I really like making videos. It'd be a goal of mine to continue doing these. Obviously, it's a huge time sink to make 12-hour videos, but I think it's awesome to have long-form content that I wish I had when I was a student in CS. So if you have feedback for me for future videos, feel free to give it to me. Otherwise, I hope this video was useful to you, and I will be monitoring the comments as I've been doing on the previous video. If there's any questions, feel free to ping me. I actually realized I forgot to explain one thing, and that's in this video we did a lot of coding, and I was making commits at various points to checkpoint the code, and so that's actually available online. I'm making no assumption of technical background in this video, though I assume if you made it this far, you probably have a deep enough technical background. If not, congratulations on weathering the storm. But GitHub's a popular website for sharing code. I have put out all the code here, so I wanted to show how to use this site a little bit. So if you want to see, I'll put the link for this in the description, but the URL is github.com, my first name, which is Millen, dash my last name, Patel, and then /tinylang, the name of the language we created. And so if you come in here, all the files are in source, and you can hop to any of the files. I've included the machine. I said I was never going to explain any of the machine internals, but if you want to build this code and compile it yourself locally, then I figured it makes sense for you to have the machine so you can actually execute some of the programs that you compile. But you can see all the codes here. And something I did throughout the video was I tried to commit after every checkpoint. And so if you click to this file explorer right here is all the code as of now, which is the latest point in the video. If you actually want to jump back in time, you can click right here where we have commits. And you can see here's each of the commits I have. And so if I click on any of them, so add support for variables, it will show you, and this is such a cool view, show you the view of every change I made across all the files from the last commit, i.e. the last checkpoint, until this checkpoint right here. So this was everything we had to add support for variables. And another thing that I think is super useful to see is if you want to inspect every file at that point in time, you can just click this browse files up here. And so this will show you the exact code base of what it looked like at the point in the video that I finished adding support for variables. So that's here. I will also be monitoring this actively. There's a lot that can be added to this programming language, and I think it'd be cool if anyone wanted to try add more features. Feel free to submit a pull request, and I'll merge it in. And that's why I'm explicitly calling out this part right here where you can go and check, because I know if this repository expands in the future, it's not going to be captured in this video. So you'll be able to use the commit history to go back and see where I actually ended off in the video. And if you want to download the code, you can also do that. If you have Git on your computer, the link's here, or you can also just download a zip of it if you don't have Git, which is totally fine. Cool. That's now everything I want to talk about. Thank you so much to anyone who has made it this far in the video. I will also say that I want to continue documenting CS knowledge. I think one of the natural next steps is to talk about operating systems. I am way out of time in this video to do that, and 12 hours is going to be very tight for an operating system video. But I think what I'd like to do is invent a little operating system from scratch and write it and run it on a physical chip and show what the responsibilities of a modern operating system are and some of the introductory concepts, like how do computers, we've seen now a computer just reads top down one program. How do computers give the illusion of running multiple programs at once? How do computers actually take input in from like a keyboard or a mouse? And how do they actually spit that out to a display? If we have a computer with a bunch of programs running on the same time, how do we make sure that they can all run independently, and that if I have one program open, it can't try access data from another program? And a lot of interesting stuff happens at the operating system, and operating systems are really cool. So that's a video that I would like to make and people have requested. I've also seen several requests for videos around networking, which is also something very interesting. But yeah, if there's a preference for what people want next, feel free to let me know and I will absolutely take that into account. And with that, I hope you all enjoyed this. I hope you learned something from it, and I hope you found this topic as interesting as I do.